first be working? Okay. Uh, how do I show? I guess I can't do. Okay, and then I gotta go over here. Just setting things up, so if you're wondering what's going on. Okay, so I'll go over here. And this thing's running. And then I gotta go over here. Click this. This over here. And then turn that on. And turn that on. And then go over here. And share this. And then put the URL in. And then click done. And then click confirm. And then, oh, I got it. Gotta do that. And then click go live. Okay. And then pull this out. Cool. Okay. And then if I go here real quick, what's going on with this? Oh, turn that on. And okay, all of that's working. Okay. All right, cool. I think everything's working. Yeah, well, welcome. I'm trying to go live on a weekday. This is my first weekday stream, so hopefully people like that. I have it as a debate night, but you know, whatever anyone wants to ask, they can ask. So if anyone has a question or anything, or you want to talk about math or something, if you want to talk to me directly, feel free to join the Discord. And in Discord, there's a little icon to raise your hand, and then that way people can take turns or whatever. Although there's not that many people here, so I mean, anyone that wants to chat, just raise your hand and you can chat in the Discord. That's perfectly fine. If you have a question, feel free to type it in any of the places, and I'll try to read your question and answer it as best I can. And yeah, thank you all for joining. Yeah. Um, let's see. Go over here real quick. Can you tell us how to make a froggy apple crumble thumpkin? I wish I could, man. I don't know how to make that. I don't know how to cook that particular item. Uh, AI and math proofs. Yes, AI and math proofs are cool. AI is cool. Math proofs are cool. So both of those are cool things to know about. Um, let's see. Anyone in the Discord, if you have a question, I don't know how to. Hang on. Let me go over here to the Discord. Oops. Can I open chat? Ah, oh, it did it like that. Okay. Okay. Now I have all the chats open. Oh, I guess I could turn on my camera for the Discord. Can you do index transformations or index transform? I'm not sure. That doesn't sound familiar to me. You'd have to tell me what an index transform is. I know what a Laplace transform is, or a cosine or sine transform, or a Fourier transform. Fourier transforms are kind of the base transform that most people know. Maybe you're referring to like when you multiply two Dirichlet series, because that would be when there's like some type of index involved. If I was trying to make a guess at what you're trying to ask about. No audio on my end. There's no audio. Okay, hang on. I'll have to disconnect and reconnect. How do I disconnect and end? No, just disconnect quietly. Okay. Okay, is it working now? Yes. Okay. So it was just Discord doing a dumb thing again. Open chat. Oops. There we go. Okay. Hey, Doc. I'll be taking Calc 2 linear in the next semester, and I'm worried. What's your advice? Yeah, you got to do a lot of study, hang out in the tutor centers and stuff, explain calculus to other people. Calc 2 is interesting. As soon as you start doing calculus, you're really doing, fairly abstract math there. And so it just keeps getting more and more abstract. So before calculus, there's a lot of a lot of reviewing and caring about repeating and making sure that we understand our math or whatnot. But as soon as you start running in that calculus world, things move really quickly. It's like, okay, well, now we're going to do integrals. Okay, now we're going to do infinite series. Okay, now we're going to do three-dimensional graphing. Okay, now we're going to do there isn't a whole lot of time to repeat some of the old stuff. So you want to make sure to have your Calc 1 stuff really well understood, because you're going to be inverting all of those formulas, right? So that's kind of the presence of Calc 2. Sum index transform. Yeah, I'd have to have more specifics, man. I'm sorry. When you change the start and end values of sums, when you change the start and end values of sums, are you just talking about change the start and end values of sums? I mean, you can have a sum and you can start it at a value and end it at another value, and you can reorder it if you want. I mean, that's perfectly fine. Is that what you mean? Are you concerned about the notation? Oh, no video showing on the Discord. I got you. There we go. Yeah. Didn't have anything going on. Um, are you thinking about, is it the notation? Like if I reverse a sum, is that like a tricky notation you want to go over? Because we can do that. Um, let's see. Just give me a second. Let's see. So open this somewhere. So when you write a sum, right, you can write it, sum of, I squared as you go from, 1 to 50 or something. And so this means, right, 1 squared plus 2 squared plus 3 squared, dot, 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 plus 50 squared, right? Goes all the way up to 50. So it's 1 to 50. Now, here the notation is, fairly well understood, right? We get the I squared, we get the 1 to 50, and then we're going to plug in 1 to 50 for each of the I squared values. The right-hand side can be written in any order you wanted. So like you could write it as, 50 squared plus 49 squared plus dot, 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 2 squared plus 1 squared. So you could write it in the other order. If you write it in another order, the answers are the same, but if I wanted to write this in terms of this notation, starting at the 50, then that looks a little more complicated, right? Because if I write the sum, the question is, what do I want the first value to start at? Let's say I want it to start at a 1, right? And I want it to go to 50 again. So I want the I to start at 1 and go to 50, but I want it to produce 50 to 1, right? So you got to think about the first value. If I plug in a 1, I want it to be a 50. But if I plug in a 2, I want it to be a 49, right? And so that's not immediately obvious, but that's going to be something like 51 minus I squared. And so this and this are the same thing, right? So we can check this, right? You can just plug in 1 and you'll get 50 squared. Then you can plug in 2 and you'll get 49 squared. And then you'll plug in 3, right? And you can keep doing that and you'll get 2 squared. I would check the last one. What happens if I plug in 50? I get 51 minus 50, so I get 1 squared. And so we get the same thing. And so these are the same, right? So we can write that as a formula, right? 1 to 50 I squared is equal to the sum of 1 to 50 of 51 minus I squared, right? So those are the same. So that's what it sounds like you're talking about when you're talking about indexes, but maybe not. Let's see, when you change start. So the problem at my university requires finishing Calc 2 and linear to open Calc 3 for engineering students. I didn't see this in my first friend's major sheet, like the requirement to finish linear algebra. Linear algebra is very, very important. Honestly, seeing linear algebra before you see Calc 3 might be incredibly helpful, because Calc 3 does a lot of stuff that is basically part of linear algebra, but it doesn't want to go into linear algebra because that has its own set of complications to worry about. And so they just kind of give you a lot of formulas that are technically linear algebra formulas, but they don't tell you that, right? So, so that might actually be a lot more helpful for you if you have to take linear algebra before you take Calc 3. They are independent-ish, meaning that taking linear algebra should be fine. If you know Calc 1 and Calc 2, you should be able to take linear algebra without a problem. Some schools, they teach linear algebra as part of the calculus series. Some other schools teach differential equations as like Calc 4, right? So in general, you have, most schools have between 3 and 4 calculus classes, and those include the calculus stuff, namely derivatives and integrals, but then also, typically a little bit of linear algebra, multivariate stuff, and hopefully some differential equations. But other schools break those into other classes. So you take linear algebra and differential equations separately um, from calculus, right? Like when you have k equals 0 and you do k plus 1 and you end at plus 1 and in the sum you do k minus 1. Okay. I think that's similar to what you were talking about right here. Like when you have k equals 0 and you do k plus 1 and then you end at plus 1 and in the sum you do k minus 1. Yeah. So I'm not sure the particular sum you want me to take a look at, but I'd be happy to if you want to post a picture of it, or you can come to the Discord and post a picture of it. That's cool. Is there any analytic way to prove it? Let's see. No video showing some biology background. Do you think I could take pass fail stat course? So stats is so a introductory stat course is completely disjoint from calculus or linear algebra or differential equations. So if you take a stat course, you typically just need to know a little bit of algebra. Like you need to know your basic algebra, I should say. And that's really all you need for an introductory stat course. And it's because in most stat courses, they've taken all the calculus formulas and they've calculated them out into what we call tables. And so you have z tables and t tables and f tables and chi-squared tables and whatever. And so when you take stats, it's really just looking up stuff in those tables, So that's how stats works at an introductory level, and so that's perfectly fine. And for most people that want to be in like biology or something, and they want to know something about like what is a test statistic, or what is the probability of some hypothesis, right? These are these are these are perfectly fine things to learn about for those fields, and you can learn them in a stat class, and you don't have to have any calculus, right? No calculus is required. Let's see. Is there an analytic way to prove it? I'm not sure what thing you want me to prove, but I'd be happy to prove. Oh, Zombo would like to chat, so we'll go ahead and chat with Zombo. Oh. Hey, how's it going, man?
Hey, it's going pretty good. I've had this math question on my mind.
Sure. We can do
So so it so if I take the infinite intersection from 1 to infinity of the interval 0 to 1 over n, I
you'd have to. Sorry, you're breaking up, man.
oh, can you hear me now?
I can hear you
Hello?
now. Yes, I didn't hear.
Okay.
All I heard was like infinite intersection, something, infinity, 1 to something.
So if I take the infinite intersection from 1 to infinity of the interval 0 to 1 over n, I understand that it comes out to be the empty set, right? But my question is there an argument to be made that the interval becomes epsilon small rather than empty? Yeah.
So you're saying, sorry. So you're saying the set 1 to infinity, and then the set 0 to 1 over n.
Not quite. So, if I were to write this, let's see. Let me see. How do I turn my camera around? There we go. So if I do this. Actually, we'll do n equals 1.
All I see is a blank page.
Yeah, hold on.
No
Why
worries.
do you that?
Oh, the infinite intersection as n goes from 1 to infinity of 0, 1 over n, and that's the empty set. Gotcha. So there is no other way for this to be a different answer if 0 to 1 over n are
Oh no,
subsets
you
of.
broke up there for a second. There
Oh,
is what?
so there is no other way for this infinite intersection to be anything other
Uh-huh.
than the empty set if those
Okay.
intervals that you're talking about are subsets of the reals, right? Because the
Okay.
reals,
Yeah.
the definition of the reals is explicitly the collection of numbers that are ordered in the way that they're ordered on the number line, and they satisfy all the algebraic and arithmetic properties that we typically allow, right? Now, there
Right.
are other sets that are extensions of the reals. For example, there are the hyperreals. It's a different set. It's sort of like the reals, but it also contains infinitesimals, right? That
Oh,
may not intersect to an empty set under this condition, but you have to be careful. The intervals from that set are not the same as the intervals from this set, right? They're going to be separate
okay.
things, right?
So if this was dealing with hyperreals, it could intercept to something in epsilon small.
Yes. If you were talking about intervals of the hyperreals, then I'm pretty sure the infinite intersection of this would be non-empty. It wouldn't contain any of the
Okay.
original reals, but it would contain some of the hyperreals, some of the infinitesimals, as they're called. Yep,
Okay.
yep. Oh,
Interesting. I guess we didn't really talk about hyperreals in undergraduate stuff.
no, that's not typically an undergraduate class. You rarely find a university that's even teaching hyperreals because it's considered a fairly niche topic, right? When I was in grad school, a fellow graduate student of mine, a fellow graduate student and me had to convince someone to tell us something about hyperreals. So we kind of put together a class for like the three people that wanted to learn about it. So we all agreed to buy the same book and then go over it together.
Huh. Interesting.
Yeah. Um, wait, let's see. Four has. He's raising his hand. I should have asked. Did you have another question, Zombo?
Um, so I heard you say something interesting the other day, and it was that Texas is secretly blue.
Yeah, I think
And
that
I
they've been.
wanted to know.
I think they've been secretly blue a while. Although there's a lot of surveys that
I
seem to suggest this.
I think there's an increase in blue voters, but I've in my time here, I've never seen it pan out as much as I want it to.
Sure. Well, I mean, I don't know where you live per se, right? I'm just basing it off stats, not like personal experience. I've been to Texas many times. So I'm not going to base anything off of my like personal experience of Texas. I'm just saying that like in
Right.
surveys and such, right?
Yeah.
Like there's a reason that they're so heavily gerrymandered to give them like what is the insane like I forget what it is in like their state senate or something. It's some ridiculous amount of like 80% Republican. The state is
Mm-hmm.
clearly not 80% Republican, but the representation
No.
is, right? So like
Yes.
that's crazy. And so all their cities, like if you look at their maps, all of their cities have been gerrymandered to shit. Like the cities have been cut up into these little tiny pieces and they all extend out to these massive rural areas, right? Um,
Yeah.
and so that just seems crazy, right? But anyway, so that's the way Texas is. So if you're a Texas voter and you want to like round up the same people in your district, you have to go driving into these random rural areas that you've never been. That's like
Hmm.
where all your similar voters are located, apparently, right?
As
Um,
a North Texas individual, even though it's just anecdotal,
hmm.
I would say for every one Democrat Texas voter, I probably meet, five Republican Texas voters.
All right.
At least
I
that's based on my interactions with a lot of people uh, day to day. At least when I was working, like, say, retail, for example,
I mean I
that's typically how it would go.
sure, sure. It's just your like what is the lifetime number of people that you've met, right? A thousand people. Can you even name 1,000 people, right? Like the in general, our perspectives on things are heavily skewed to our personal
Yes.
experience, right? So we
Yes.
always have to be careful of that. Another question. Another question. I hold a degree in physics, but I never quite understood why we consider derivatives as fractions when doing algebraic calculations. Isn't just notation? True. That is very true, Joe Ao. Joe Ao. So there is a reason for it. So like if you go back to Leibniz day, right, and he had a function, and he called it f of x equals x cubed, he would use a little dot. You'd go dot, and that would be the derivative of f, right? And so the notation he used made things more complicated to explain, which is why we all decided that we wouldn't use that notation. We would use Leibniz notation, which is that you put this fraction thing in the front. And the reason that we do the fraction thing is because the derivative, in some sense, really does behave like a fraction, right? The derivative of a function, f prime, it's approximately the difference of what is happening for f divided by the difference of what is happening on the x-axis. And so this is sometimes referred to as slope, and you have a change in y over a change in x. And so we could write this more rigorously in terms of limits, but there's a natural fraction that's already happening when you're doing the derivative. Like slope is a fraction. So the fact that the derivative involves a fraction should be made clear, right? But that notation actually shows up to actually help, right? So for example, let's suppose I have a differential equation. So I have here, let me put it to you this way. I have a function, and I'm not going to tell you what it is, but I'm going to tell you that the derivative of it is equal to itself. So it is its own derivative, right? And so I've given you a differential equation here. Differential. And there's a question about how you would solve the differential equation. Well, it turns out that if you use Leibniz notation, this becomes a little bit easier to follow and understand. In particular, what you really have is you have the derivative of f, or the change in f, over the change in x, and you have f on the other side. And so this is a fraction, but it's not just notation. How would I solve this algebraically? Well, I'd put this change in x part to the other side. And so I'd have f times dx. And then you might say, okay, that seems a little weird, almost like you broke the derivative in half. And yeah, that sort of is what happened, but we've seen that notation before. When do we put a dx somewhere? Well, we do it when we're doing something like an integral, right? And that's exactly what you do here, is you say, well, I want to get rid of this derivative on the f, so let me go ahead and do the integral to both sides, right? So we do the integral of df, and then we do the integral of f dx, right? Um. Oh. I didn't. I didn't. What am I missing here? Uh. This is the derivative of this. This is. Hang on. Give me a second. You have d. Oh. This is why you don't do it with an f notation. Okay. So you have y prime equals y. So you do dy over dx equals y. So then you do dy equals y times dx. This has an x in it, and this doesn't have an x in it. So you got to move that to the other side. That's what it was. So 1 over y dy equals dx. Now you integrate both sides, and you have all the y's on the left-hand side, and you have all the x's on the right-hand side. And the antiderivative of 1 over y is ln of y. And the antiderivative of 1, essentially, for x is x. And now I can solve for y by doing an e to both sides. And so y equals e to the x. Now I left out the constant part. There's like a plus c or whatever. But the point is that I solved the differential equation, and I did it using the Leibniz notation. So the point is that the fraction, it actually has meaning algebraically. It literally allows you to solve it algebraically, right? Yeah. Yeah, it is cool. Yeah. So this notation's important. Yeah, we like Leibniz notation because it's more useful. Because what would you have done with y dot equals y? You'd be like, I don't know, like you want to get rid of the dot, but how do you get rid of the dot? It's not obvious how you get rid of the dot. Like it's not clear what you would do. But when you write it as a fraction, well then it's clear. You got to move the bottom part of the fraction to the other side. Right, then you got to put all the y's on one side and all the x's on the other side, right? So like, it makes sense over here, but this doesn't. This is not good enough to like make it obvious of what to do. Four has. You can come up if you wanted to chat about something. Oh, there were more questions. Jeez, I've been missing all these questions. Hang on. Would you recommend any reading materials to prepare for real analysis? Reading materials for for real analysis. So for an introduction to real analysis, certainly maybe something like Spivak is considered very good. That's considered a very good book to read through. It not only will refresh your calculus understanding, but it will give you a very clean introduction to like the beginning of real analysis, right? So I'd probably recommend Spivak's book. I don't know how much it is. How much is Spivak's book? Spivak calculus by, let's see, $61. Okay, it's a little pricey. Thrift Books. Is this? No, it's someone else. That's a little expensive. You might be able to pirate it somewhere. I don't know. Okay, let's see. When are you streaming times regularly? So my streaming times have typically been Saturday and Sunday. When I was just every Saturday and Sunday. But I've been trying to be a little bit more regular, and in particular, I'm trying to follow a schedule. And so my schedule is trying to be Saturday, Sunday, Monday. And so this is the Monday stream. And I'm trying to do streams of debate nights if people want to debate me on something, or streams of, ask me anything if you want to ask me stuff. And so tonight's a debate night, but, I mean, until we get a debate going, it wouldn't really, people can ask me whatever it is they'd like. Isn't the line at the F just a Roman numeral? Romanic numeral, like I, 2, 3, 4, 5, 6. Isn't the line at the F The line at the F. I'm not sure, man. You'd have to tell me. I don't know. I don't know what any of this means, but I'm here. Oh, thank you, thank you. Please stay. You know, Leibniz was more explicit. Yes, yes, Leibniz had better notation. This is calculus. Yes, it is calculus. Yes, we're doing a little bit of calculus right now. Let's see. Okay, so that's all the questions so far. Forhaz, I clicked the button if you wanted to come up. I mean, you don't have to, but if I think you have to accept the like you raised your hand and then I clicked the button, and then you gotta click that you want to chat, right? It won't just make you chat, right? You gotta say that you'd like to chat, you know. So, any other questions? Oh, F prime. Yeah, F prime's another notation. Yeah, so that was what this little prime symbol is. So no, they don't do that. They normally do this. They do F prime, F prime prime, F prime prime prime, and if you want to be annoying, you might do F prime prime prime. But at some point, you say, "Oh, screw it," and you just start putting in a number. The designation is that you use parentheses. So when you put parentheses in an exponent, that's understood to mean that you're doing a certain number of derivatives, right? So people don't put well, you don't use parentheses. So like if I do f to the 5, that means f times f times f 5 times, right? But if you do f to the 5 with parentheses, that means 5 derivatives of f. So like these are distinctive things. So the parentheses means something different. Notation like the first derivative, second derivative, fourth derivative. You could, if you want, you could write this. I've never seen it with Roman numerals before, so that'd be a first for me. But I mean, you can use whatever notation you want. Oh, Jetstream. Come on up, buddy. Here, I'll move to audience.
Hello, hello.
How's it going?
So far so good. I just got a
Awesome.
question. I've just been thinking about this.
Sure.
When it comes to obviously like elections, and I guess this is mostly about voting, right?
Mm-hmm.
Which one? Okay, do you know how when the alcohol was, I guess, in the United States specifically, it used to be for ages 18 and up, but then because of circumstances going on, they
Mm-hmm.
moved it to 21 and higher, correct?
Yeah. I don't know when that happened, but
Yeah, I
I think
forgot. It's like,
I think it really happened because of cars, right? Because it used to be that you could kind of drink and there wasn't like, you know, even if you got hella drunk, you still had a horse that was like, "Yo, I'm not gonna go off that cliff, dude." You know, so like drinking, I don't think meant as much. But as soon as we had cars, then it was like there's like a responsibility there that's kind of important. And then there were a lot of kids that were dying, drinking, driving. Um, and kids are just not as responsible. So at some point they raised the limit to try to curb the amount of death that was going on. So I don't I
yeah, so
yeah I don't know if it was the proper thing to do or whatnot, but
okay. So I was wondering about this a lot, right?
mm-hmm.
Do you think raising the age to 21 to vote would be better or worse?
Yeah. So in general, the typical argument is that if you can be enlisted in the army, then you should have the right to vote. And so the general stance is that if you can die for your country, you should have the right to vote. And so something like voting is such an important aspect of being an adult that it's not something you can, I think, take away from people, right? Whereas drinking is like this, recreational activity thing. And if it's causing a lot of harm to people, we probably need some rules in place so that, we don't like, just arbitrarily kill each other all the time. Um, so like there's the point is that the discussion there I think is on two different levels. You could be for or against either of those, and I don't think it's like you're being intellectually dishonest or something. So like maybe you're for 18 and up and drinking, and then you're for voting 18 and up, or against one and for the other, right? But yeah, the general mindset is if you can die for your country, you should be able to vote for your country.
Okay, okay. I mean, I guess also, I mean, I guess that just leads to the other question. Do you
Hmm.
think that being 20, they should move the age up to 21 as well for it, I guess, joining the military?
Oh, move it up to 21. Um, I don't know. I mean, that would be, I would defer to whatever the doctors say. So, like, if doctors said children need to be, like, they need to be considered children longer or something to that effect, or we need to extend high school to 21, we've been doing it wrong this whole time, or something to that effect. I don't know. Like I might be fine with some persuasive argument like that. I just feel that there's a lot of other things that are like what else are we going to move to 21? Like are parents still responsible for their children up until 21? I don't know. That doesn't sound right. Like when are you no longer allowed to employ someone until they're 21 because you violate child labor laws or something? That doesn't sound quite right. Okay, what if you want to get married? Are you allowed to get married at 19 anymore? Well, you'd imagine someone at 19 should still be allowed to get married if they want to, right? So, like, I don't know. There's a lot of things that I don't think we would feel comfortable moving up to 21. And so, in general, we probably shouldn't move stuff up to 21. We should be more so concerned with things that require 21 and moving them down, right? Um, and there aren't all that many, right? I mean, what is it? Drinking and is there anything else? I think renting a car. I think renting a car is the only other thing that has an age limit, right? Or being president. Being president.
Yeah, yeah, that's right. I believe so. It's just weird because I don't know, like adult, obviously we all know what adulthood is, right? But
Hmm.
it's like it's very political because every other
Hmm.
country has its own meaning of adulthood. Some are like at 15, some at 16. And so it's
Yeah.
like
Yeah.
it's it's strange,
It
and
is. It is. Yeah. It's
and what's
complicated.
ironic, exactly, yeah, it is
Yeah.
complicated for sure
Yeah, it's not
because
it's not an immediate thing. When someone's transitioning to adulthood, there's a little bit of complication that goes on. I think some of the better policies are those that make this transition a little more fluid, right? Or a little more like there's a gradient there, right? So, like for example, like when it comes to here's an example of a topic. We have something called medical privacy, right? And in a lot of states, most states in the United States, medical privacy is an all or nothing. Your parents have complete medical autonomy over your entire medical history and everything that it is you want or don't want to do. They own your medicine, and then the day you turn 18, they can deny you any and all access to any of their medical records as they see fit, right? And so that is such a harsh like kaboom, that we in some states like in California they've tried to be a little bit more progressive at that. So in California there's a more granular type of thing whereby effectively, and they have it broken down into categories, your medical privacy is like slowly bestowed to you as you become older and older, right? So in California, if you're 16 and you're doing, underage drinking or something, and you want to seek counseling, right? you're allowed to do that, and you're allowed to have medical privacy to do that, right? So if you don't want your parents to be told, you're entitled to that as a 16-year-old. Now, the stipulations of it are that you have to meet with a counselor, you have to be shown sound of mind and able to make your own decisions, and, at least make your own decisions up to the type of medicine that you'd like to, discuss, right? But the point is that someone has some medical autonomy. It's not just like your parents own your entire medicine and there's nothing you can do about it till you turn 18, right? So, I think laws like that are probably better than laws that are like all or nothing, right? I think transitioning people into adulthood is probably a better way to go, and so we need to make those things a little bit, easier to understand and follow, right? Yeah.
Yeah, that's understandable.
Yeah. Yep, huge gray area of how much it can truly affect. Yep, yep. As a neuro researcher, agreed the brain isn't even fully formed, and it's odd we choose 18 as adult age. Yeah, that's true, right? I mean, in theory, every single person's brain should be properly evaluated before they are given the title of adulthood through some psychology or maybe some type of test, and then they're given the certificate of adulthood, and then they're able to move on. But unfortunately, that would be too complicated, or we don't have the technology to do that, and hence we have to pick an age somewhere, right? So 18 seems like a fairly okay age. It's quite high in comparison to a lot of other countries, right? Other countries have a little bit slightly earlier age for adulthood,
Yeah, because I'm not, don't quote me on this, right? But
Mm-hmm.
I think 18 got selected as adulthood was when, I think they're like statistically looking at, how many people are in school, also how many are getting jobs. And I think around the late teens was when, I guess it's like the average was like in the 19 and 18. So, you know what?
Mm.
Boys making 18 and 18 is now called adulthood, at least in the US. I don't know about globally, but yeah.
Mm-mm. Yeah, I'm not sure. I'm not sure the history of exactly why 18 was picked, but um, yeah, you know, but a number was picked, right? You kind of want a number that's on the slightly higher end if you're trying to think about like you know self autonomy and responsibility and those types of things. You kind of want it a little bit higher, such that the majority of people will have that by the time they turn 18, right? As opposed to like putting it like right in the middle, like, well, here's the average of where responsibility is, and so then half the people becoming adults are basically morons. We probably wouldn't want that.
Yeah.
Let's see. The idea of the brain being fully developed at 25 is a myth, though. It doesn't even stop developing. Yeah, that's true. Well, I don't know. I would defer to a medical expert. The brain does have certain distinguished developing markers that are different than you would get in a general, like just a general brain. Like the brain from 25 to 55, yeah, it's always changing, but it's not going through development, right? Not in the same sense. Like the development part, there's physical markers that are part of that development, with particular hormonal markers as well as other things. Like when they look at brains, right? They can tell the age of the brain, right? So like those markers are certainly there. Right? What are you debating? Well, we're not debating anything at the moment. It's anyone wants to come up and ask something, they can. So, yep. How's trans policies in the U.S. regarding age? Yeah, so trans is going to be a complicated topic, right? Um, the general sentiment of like the Republican Party is that, you know, trans children are like these, you know, crazy kids making stupid decisions, and people are just running around trying to cut off penises or something. Like it's some dumbass argument, right? The reality is, right, that you typically are, you know, you're a parent of a trans person, and you have a strong interest in doing what's best for your child. So you meet with psychologists and medical experts and other people, and you know, everyone is having a sit down to try to figure out what is best for the child, right? That's the end goal, right? And most of the time, like nearly 99% of that diagnosis is simply doing things along the lines of either, you know, what do they call it? Just social transitioning, right? And then possibly even moving into like hormone therapy at the very, you know, at minimum or whatnot. The idea of like underage surgery or something. This is typically quite rare in terms of like literally the trans community themselves, right? Like the trans community having underage surgery is incredibly rare. But again, it's made at the best interest of the child, right? Depending on the type of surgery. And yeah, the most common surgery is going to be something like, you know, something to do with breasts or something to that effect, right? Um, so the point is that like I think in general we should be deferring to medical experts and doing what's best for humans. So if this is something that is beneficial to humans, then we should be doing it. There are plenty of you know, children that go through some type of a sexual change and have done so for, you know, hundreds of years, right? But had nothing to do with trans, simply because human beings are naturally born with lots of complexities. There's even a specialization you can get as a medical doctor on sex identification, because sometimes things pop out a little wonky, and you have to have someone who's like trained in all the different ways that things can kind of be a little weird. Like something didn't drop correctly, someone's got a couple of, you know, the same two different organs at the same time, you know, what are going to be the ramifications? Do we do a surgery now when they're, you know, a baby? Do we wait till they're a little bit older, right? These are all really complicated things to take into consideration, but as long as everyone is on the same page that the objective is to help people, you know, then I think that that's fine. I find it weird when conservatives argue so much for the autonomy of parents to make decisions about their own children, including indoctrinating them, right? Like they should be allowed to indoctrinate their children, and everyone respects their rights. But then when it comes to trans, they literally will go toe to toe screaming at people that parents shouldn't have the right to take their child to psychologists or counselors or anything like that, right? And it's like this is just so weird. I don't understand the conservative position on that of like pro parent rights and anti parent rights at the same time. That makes no sense to me. No questions today, but feeling like my college dream might be over. Lol. No, don't say that. What are you debating? Why 21 is the age for shit in the U.S.? Here, everything is 18. Well, the only thing at 21 is drinking. I mean, if you really wanted to drink, you can smoke at 18. Can't you smoke at 18? Yeah, I think it's just drinking. Drinking and again, renting a car, right? Drinking and renting a car. Maybe drinking should be at 18. I don't know. Let's see. Anyone else want to chat about something or have another question? Oh no, that's a bummer, Zeno. Sorry about that. Man. No way I found this debate live. You did. You did find it live. It is live. You can join now if you want. You can join the Discord, and if you want to chat, you know. You don't have to, though. Do keep in mind that Instagram will shut down in 7 minutes, and then it will take me a few minutes to put it back online. So anyone on the Instagram, you have to be careful of that. Or just, you got to know that. Could you do a video on the lambda operation and another on Divergo equations? Okay, I mean, I could try. Most of my videos are me explaining a concept. I'm not sure what the lambda operator is or the Divergo equations are, so you have to teach me something. Is long division like doing surgery? Yeah, that was a funny question. I remember that video. Can you explain to me forcing in model theory? Forcing? I'm not sure what forcing is. Do you mean, can I explain to you what force is in like Newton's idea of force? Like force is mass times acceleration? Is that what you mean? Like how that works or whatnot? Or yeah, let me know. Yeah, if anyone's in the Discord and you want to debate or like you want to chat, just raise your hand and then I can click the button. And you can chat with me if you want. Yep. I guess I'll go ahead and dismiss that one. Any thoughts on free will? Yeah, I don't know, man. I feel like I have free will. Like, and that's probably my strongest piece of evidence. I feel like I'm in control of my decisions. So, you know, that seems like pretty strong evidence. I don't know if anyone else has free will, but I feel like I got free will. So, and I really don't know how I would prove that or demonstrate that in any way, but you know, it's a pretty strong feeling. I feel like I got free will. Then again, I can be presented all kinds of other things that like I thought I was in control of, you know, how my legs work or whatever, and then some doctor does some weird shit and my leg doesn't do the thing that I tell it to anymore. So, you know, that I can see lots of evidence of me not being in control of things, right, with respect to me. So maybe I'm not in free will. So, you know, maybe I'm just in denial of the evidence or something. But yeah. No, forcing the way to prove something is independent from other axioms or something like that. Oh. Yeah, I'm not sure. So I guess when you prove something is independent of other axioms, typically that means that you prove that the axiom is consistent with the other axioms or its negation is consistent with the other axioms. And that's what the definition of like independent of the axioms means, is that both it and its negation are consistent with the axioms you have. So sometimes that can be rigorously checked, especially if you have, you know, formulaically defined axioms. Typically you should be able to like systematically demonstrate that, or you may be able to systematically demonstrate that. Like you can demonstrate that this is consistent with each of these axioms. If you're consistent with the axioms and those axioms form a consistent system to begin with, then then you'll also have an additional consistent system. So that's a so you know that you have a meaningful extension, I guess, right? Can I teach you gradient divergence and curl and how they're used? Oh man, off the top of my head, Geez, I don't remember those off the top of my head. So those are like two integral things, um, and they're two different integrals, and they're used in two different purposes, right? And yeah, and they both have a formula, and they've been given a name. One of them's called the divergence, the other one's called the curl. I'd probably have to go read up on them to give you a better explanation. I know that they have some lovely real world interpretations, dealing with like, you know, vector fields or whatever. Wait, are we still arguing free will? I thought that argument was dead. Oh, I guess. I don't know. I just said I feel like I got free will. I don't know if I do. Let's see. Cool. Should a theoretical physicist spend significant time learning math like a math major, proofs, abstractions, or is it ultimately a waste of time nowadays? Um, it depends. I mean, well, so theoretical physicists, they sort of kind of do proofs, kind of like a mathematician, um, but it's a little bit more complicated for them, right? You know, they're trying to they're trying to find consistency with prior models or consistency with new models. So like you have, the standard model, and you want to make sure the standard model is consistent with your new ideas or whatnot, right? Um, okay, so Instagram's about to go down, so I'll have to pop it back up. Give me a second. Oh, add link. Man, I hope Instagram updates this at some point and we don't have to do a new stream every hour. It seems kind of weird. I don't know why they do that. Let's see. Why is calculus always the example of hard math? I mean, it's kind of hard, but too boring. That's funny. So, I mean, I can, I have like my books here. Let me see. Downloads, hobby book list. So, browsing. Oh, geez. I gotta click Bobby's book list. Okay. So here's my book list, right? So, these are my math books, right? So like this is the beginning of math, right? You have the beginning where you do like arithmetic, algebra 1, algebra 2, and this is like your stuff we learn as kids. We hopefully want to make it through algebra. Some people do algebra in college, that's fine. And then you go into more complicated stuff. This is like an extension of algebra. You start talking about trigonometry and functions and whatnot, typically a book or two, and that's kind of the beginning of math. Then immediately after that, you do calculus. You got a little bit of calculus. You talk about like Stewart. Sometimes it's a 4-part class or whatnot. And then you got a couple of advanced topics talking about either differential equations or linear algebra, and then maybe a little bit of statistics is what people do on the sideline, right? And so this is kind of all the start of mathematics. You kind of learn some of these basic classes, and then you begin real math, right? So to begin real math, you start going through all of these topics, right? So I always find it funny when people think of like calculus as like hard math. I mean, it is hard. It's very challenging. I shouldn't downplay it. It's very challenging. It's just there is so much more math than calculus, right? You have, logic and category theory and meta mathematics and non-standard analysis and topology and, real analysis, complex variables, number theory, analytic number theory. You got like this stuff just goes for on for ages. And then maybe at some point you want to become a researcher like me in polynomial research. So you start getting all these books that are very specific to polynomial research and you start looking for all of them. So anyway, there's a lot more math after calculus is what I'm saying. And when I say a lot more, I mean a lot more math after calculus. Lots of math.
Yes. For me, when I graduated engineering, I think the last math that I took, I think it was either linear algebra or differential equation, either or. I mean, but yeah, basically calculus one. To explain to other people who, don't really take math like that, right? In different majors, I guess. Calculus one is like the first level of hell, if that makes sense.
The first level of hell. It's the first, in some sense, it's like the first, new math topic. So a lot of people remember school of like learning math and you're kind of repeating math over and over again. You're repeating arithmetic, you're repeating this, you learn about pre-algebra, then, pre-algebra, pre-algebra, you learn about lines again, then you learn about lines again, then you do quadratics and you learn quadratics again. And it's like, and there's this long repetition, and that's kind of what math curriculum is like through most of, middle school and high school and whatnot, right? But when people are put into a calc class, they've typically experienced such a large amount of repetition, and then it's like for the first time ever they're being presented just a completely new topic in math, and for a lot of people that's like pretty that's like a real complication just immediately thrown at them, right? Because they're like, whoa, this is like, why aren't we like redoing fractions again? It's like, well, because we're moving on to a new topic. It's all new. Let's see. How deep should I go with my learning of math if I'm a business student? Well, it depends on how far you want to go. Like, do you want to be a Nobel laureate in economics? Well, you probably want to take a lot of math. If you're just trying to like, run a small business or something, you probably don't need all that much math, right? I think the highest math. So a lot of times we take calculus and we condense it down even more into a one semester class for different fields. So most schools have something like calculus for business majors or calculus for biologists or calculus for whoever, right? And these are typically like one semester crash courses that kind of do a little sprinkling of all the calculus, right? But you don't have to go through the 2 years of like rigorous calculus. And so that's typically fairly good, right? Like if you're a business major, you would take business calculus. That's probably all the math you need. If you want to be a really, really good business person that like is doing all the math. So like not, in other words, there's a difference between being the business person that hires the finance person, and then the finance person gives you presentations and you want to be able to understand what they're saying, right? There's a difference between that guy and the business person that wants to do the finance stuff in the back, right? So if you want to do the finance stuff in the back, then you probably want to be very good with your math. But if you're fine hiring people to help you, then you just want to be able to understand them, right? Are you familiar with McKinsey Sugar system? No, that doesn't sound familiar to me. Yeah, you can tell me about it. Teach me. Let's see. This calculus first time around when everything clicked together, blue noggin, smooth off. It was so cool. Yes, I agree. Yeah, calculus. Calculus is pretty cool. We like calculus. And nowadays we get like the really refined calculus. Like, I mean, in Newton's day, taking calculus was equivalent to doing 5 years of intensive study, doing all this, complicated, like, math gets refined over the years, right? And it gets condensed and refined and condensed and curated and made very clean, and all the best examples are put forward. Like, people just don't even understand the level of, like you get to live in a time where the quadratic formula is able to be explained to you in symbology that makes it so much more easier to understand than people of the past. Like, the Greeks literally could spend weeks fighting about some triangle because they had no notation or graphs, or those concepts didn't even exist in their head. They didn't even know that they didn't know what they were even missing that could have made it easier for them to do the algebra that they were attempting to do. Am in a pretty difficult course. We spend a lot of time analyzing case studies, which requires us to understand a lot of numbers as well as mirroring in economics. Should I invest in math books? Um, yeah, I don't know. I've invested in so much math books. It's like my number one expenditure. Let's see. It is an axiomization of classical mechanics. Pretty cool system. I saw a little bit of it in a class about model theory. Oh, that's awesome. Yeah, that's very cool. Yeah.
Yeah. So it's just me. I guess going on a rant. When it comes to math, right? Math, when I was in school, you always hear that one student and that one kid like, oh, how is this going to help me in the future? Blah blah blah. Blah. Oh, I hate math. Blah blah blah. Blah. And
Yeah,
it's,
yeah.
I guess you could say it's understandable because I mean, for me, again, I always want to be like an engineer, and
Mm-hmm.
Bobby always want to be like like a mathematician. I guess we kind of figured like, yeah, math is going to be in our life if we want to continue our dream, right?
Yeah,
But
yeah.
in general, math is used every day, but not as
Mm,
not nothing above like calculus one, but in everyday life, math is like math helps, it helps you with information, it helps you process things better and keep it with logic. That's basically what math is supposed to do. Make sure your logic is sound.
mm-hmm.
That's why like when it comes to like random debates and when people give me questions, right? I'm
Mm-hmm.
able to, articulate and understand the process of the rebuttals if it makes sense or not. Like, oh, if you're saying this, then why are you saying that? Because you believe it or not, a lot of people in like, you know, when it comes to like debating, right? They either, you know, will contradict themselves later on or, go about whataboutisms. And it's
Mm-hmm.
like, it, I guess that's like, some way how people do debates in general, but it doesn't, it makes the topic stale. So is this something that I kind of, use math? Like, okay, if I do like this, I could follow the next step and the next step. But usually, from what I know, people who are like kind of really good at math, they usually know how to like, I guess, process and then articulate what they're saying. So it can help. It helps in mysterious ways, you know.
Yeah, certainly. Yeah, I would always just remind students, right, that math feels more useful whenever you're presented a problem in real life for you to use your math and you actually try to use it. So many people just just think of it in terms of arithmetic. When you go to the store and you're like thinking about prices and someone something's like, "Oh, it's 10% off." And you're like, "Oh, it's 10% off," right? You may know how to calculate that explicitly. You might know how to estimate that approximately. You might have done that calculation many times and you understand that process. But the point is that for some people, some people see the 10% off, and for them, it's a estimatory calculation that they're aware of that they can do, and they probably do it in their head, and they have an idea of what is happening with that phrase. There are many people that see the phrase 10% off. They don't spend any time trying to do that calculation. They don't think about it, and so for them, they then uh, look at arithmetic or something like that, and they say, when is this ever going to be useful to me? Yet they're presented these problems in real life, and then they don't tackle them with the skills that they acquire in the math class, right? And so I always encourage people, when those problems show up, don't don't run away from them, right? Like that's your opportunity to practice the math. That's the opportunity to use the math. um, so anyway, yeah, that's always been my little spiel to people. Let's see on.
Yeah, I would say one of the things that I disliked about math, not math in general, but in math classes in schools, is that you gotta do what the teacher tells you to do in a specific way. I remember specifically, right? I was in Pacific junior year high school. There was I think it was like the first or no, okay, it was definitely the first math test because the next math test is I had to follow the teacher instructions. I don't know how many questions there were, but there was like at least 25, at most maybe like 40.
Mm-mm.
I did a math test and I got all of it right, correct? And when everyone was leaving, right, the teacher stopped me and told me he gave me my test, and it was an A. I'm like I kind of knew it was an A, 'cause I'm like I know what I was doing, right?
Mm-hmm.
But the issue that the teacher had is that I didn't follow his steps. I
Mm-hmm.
did it my steps, right, my way.
Hmm.
And at first he thought I was cheating, so he told me, "All right, I'm gonna give you 3 questions. And I want you to do it on the board." And I did it, and it was right. And he was like, "Okay, all right." So obviously I'm not cheating. I know what I'm doing, but he
Mm-hmm.
told me, not to do that again because he needs to know that I'm following his way, I'm following his directions. And of course, I'm like, you know what? Sure, I guess, but that's like one of the things that I don't like about math in schools because, you know, the way I see it is like math is there's many ways to solve, a question, right? But in real life, you could do any way I guess you can. Obviously, the best way is, the fastest, again, that's the shortcut, but the fastest way, right? But for
Mm-hmm.
some people don't, want to take that route. They want to go the longer route or go their own route. As long as you understand what you're doing, you should be fine. But school is kind of like, it's either this way or no way, So it can get discouraging. Like, okay, that's annoying because the reason why I did my way because my way was much faster than his. Not saying that his way
Mm-hmm.
was wrong. It was just I'm like, why am I doing all these calculations when I already know what the answer is gonna be? So I'll basically like skip 3 and 4 and go all the way to like 1, 2, and 3, all the way to 7. And so yeah.
Gotcha. Um, all right. On the flip side of standard math curriculum, say you would like to create a prodigy, how would you go about raising a young mathematician? Should we stick to the standard curriculum, math comps, or leave the kid kind of on their own and let them develop? I know Euler and these great physicists of their time spent ridiculous amounts of time on just something like arithmetic, for example. Um, yeah, I don't know. So you want to make a prodigy out of nothing? Typically, a prodigy. Typically, prodigies do well when they're well funded. Um, the stories of like not having good resources available to you and being a prodigy, those don't normally become famous or anything. But if you have a lot of resources available to you, like people to help you and you know, tutoring centers and whatever else it is that's needed, then someone that is a prodigy could that could be cultivated pretty well, right? I'm not sure how to like make a prodigy. I guess if they're really, you're just assessing if they're good at math at a young age, right? You just got to assess if they're good at math at a young age, and if they are, then you have to encourage that, you know. Um, so yeah, yeah. I'm not sure. Let's see. Oh, other questions. It is a axiomization of classical mechanics. Cool thing. Okay, K through 12 math is the most fundamental problem-solving skills that can be taught. Sure. I mean, maybe. I don't know. I do. Anytime I'm presented math stuff, I do it all the time, simply because it's available to me to do. So like, you know, I'm interested in, you know, installing solar panels. So I'm like, okay, well, you know, how big are solar panels? And how big do they have to be for this, that, and the other? Or is there another way to deal with solar panels? And so I look up a bunch of numbers. Like, how does this work? How does that work? How do you calculate this? What would be the way to figure out, you know, the total amount of energy that you could get, you know? So like the point is that like if there are things that you want to know, um, you know, then there is you can spend the time to try to figure that out and learn about it and solve it, as opposed to like not solving about it, right? Um, so so yeah, I don't know. Yeah, I'm just saying that like I mean I'm a mathematician obviously, but I feel like I do lots of math that isn't part of my job, right? Because like I'm going to do calculations on things just to figure other things out. Like, well, you know, uh, based on the amount of error correction of a particular thing, of a particular process, how long will it take for some particular thing to happen, you know, or you know, it what is the relationship of these two other things, or so you know, I've solved plenty of things in complicated ways. Like figuring out relationships of like GPS coordinates. That was something I did the other day. I wanted to know how GPS worked, and I wanted to know the trigonometry of it. And so I, you know, spent some time just doing it on paper. Like, well, how do I figure out, you know, the distance between geolocations, right? Without like typing it into Google or something, you know. And so you can derive those equations, right? Like what is the equation for that, or like how do you figure out the angle between two geolocations, right? Is there an explicit way to do that? Um, yeah. Anyway, so you know, the point is there's math all around us, right? We just have to want to do the problems. Let's see. People here in Brazil only learn about proofs. I math when they gets into a math or physics major. I believe it could be shown in high school, though, some trivial ones. Yeah, maybe. So there is at least in the United States, some high schools teach geometry, from basically Euclid's methods, as a high school course, and I've tutored high schoolers that were taking a class like that, and in some sense that is your best introduction to proof, in a non complicated fashion. Like you haven't taken any calculus, but you want like an introduction of how to do a logical proof. Doing something like Euclidean arithmetic makes sense, right? Because that's what that is about. Like the rules are you're only allowed a straight edge and a compass. Show me by drawing it out how to bisect an angle. So here's an arbitrary angle. I draw it on the piece of paper. Bisect it. Turn it into two. Here's your straight edge. Here's your compass. Those are the only two things you're allowed to use, right? Like this is a demonstration of proof, right? You're presented axioms, and then um, you have to do a proof from those axioms, right? Derive something new. Let's see. Integro differential equations where a function is derived and integrated at the same time. Um, okay. There are zillions of equations all the time. I have a formula that plagues me nightly that involves the derivatives of modified Bessel functions of the second kind of pure imaginary order, and one of them, and their derivative, and they're inside of an integral, and they're in an infinite series, and it's a multivariate infinite series and a multivariate integral, and yeah, that thing annoys me. I find it very irritating. Yeah. Method of Lagrangian multipliers meant to find the absolute maximum and minimum. Oh man, I remember that sounds familiar. That sounds like a Calc 3 topic, if I remember correctly. Lagrangian multiplier. Something. I don't remember it off the top of my head, but it's like a trick equation to help you find like maximum and minima. But I couldn't tell you off the top of my head. I'd have to look it up. Bobby, how do you calculate the irrationality of love? I don't know, man. Something to do with flowers and chocolates, right? Probably more chocolates than flowers. Something to that effect. I don't know.
I think that's
Um,
also it's also used in the media. You know, the media kind of use things like Valentine's Day, for
no.
example.
Yeah, certainly.
Like, oh, chocolate, ooh, chocolate. You gotta get chocolate. You gotta get a chocolate, or you gotta get that big ass ring. That costs like an arm and a leg, or stuff
Yeah.
like that. It's
Cer-
strange.
Yeah, certainly there's a big
Um,
push for diamonds, right? Because diamonds are weird to me because they're not rare, and
yeah, I was gonna say that. Yeah,
then we but we spend a shitload on them, and I'm like, why? Yeah, I don't understand that, And now we can grow them in the lab, so that's even weirder. So it's like,
oh wow,
well, that's what a zirconian diamond is, right? Is it's one that was grown in a lab using chemicals.
wow. I didn't
hmm
know you could do all that.
Yeah, they figured out how to grow diamonds. They literally can grow them, right? And so the here's the thing: the grown ones, they literally grow on a literal chemical level, right? And so they come out perfect. They literally have zero flaws. And so the criteria now is that if a diamond comes in and it has zero flaws, it's zirconian, and that means it's worth less than the ones with flaws. And
Yeah, I was gonna, yeah,
yeah, and they'll give you all
I was
kinds of
gonna,
bullshit. You get a special sparkle, blah blah blah, from all the little intricacies and special patterns. They won't call them flaws, right? But
yeah. It's
yeah.
it's just funny because I know, I guess it's like somewhat like off topic, but when it comes to perfection and then natural, a lot of people make them like they're the same thing, but I guess in the eye of the beholder, it's like it's not the same. I mean, there's like, how do I say this? It's like when you see like teeth, right? I think there's a thing called veneers, how people get like perfect white teeth.
Mm-hmm.
Um, when you look at them, when you see someone who actually has like perfect white teeth, it looks strange, like it looks
Yeah.
cartoony. It's like, ooh, like you can just tell, like it looks,
Sure.
interesting, but not in a good way. But when you see someone with
Yeah.
like natural teeth, right? I'm not saying that it got like crooked, and like not that like no teeth, but so there's something about naturality that I guess people kind of dig more. Now I don't
Mm.
know if again if that's just psychology
I
or just
no. I think it's purely a marketing thing, right? Because they don't talk about the metal that way. No one goes, "Oh, look at all the flaws in this gold. Isn't that amazing?" No one says that, right?
Yeah,
So
yeah.
like
So it's
it's
definitely
purely a
marketing
marketing
for sure.
thing. It's purely a marketing thing of like, well, these are diamonds that people died over, so that's special, right? So you're like, okay.
It's definitely special. Yeah, it's like just a false
Yeah.
claim or whatever. It's like, I guess, sure, why not?
Let's see. Will you ever do a video explaining the best way to learn math? Let's say you had to do it all over again. Best way to learn math. Um, I don't know. What would I do all over again? I don't know if I'd change much. If you like studying math all the time, you study math all the time. You get to know your spots. I had a spot at a Starbucks. I had a particular spot at a Denny's. Um, there was this little restaurant that I would go to for um, my master's program, and they had these really big tables, and so I had like, oh, they almost gave me like a plaque of like your name for this table, So they made good burgers, so that was, I don't know. I'd probably do it all exactly the same again. Um, would love if you made a video about that. Yeah, I know. I'd love it if I had a time to make a bunch of teaching videos too. I'd literally go through every advanced mathematics course I could do, but I only have so much time to work on these things. I'm sorry. If I can make this a full time career, that'd be pretty cool. But I currently have another career, so it's at the moment we got to share, right? And until this grows to some level where I don't have to worry about the other position anymore, right? Did Gödel incompleteness theorem really destroy hope for final knowledge? Absolutely. Yeah, there's no way around that. What are you gonna do? Yeah, there absolutely will always be statements that you cannot prove are true, but are true in arithmetic. So you'll never know if they're true. There's no way to fix that. Yeah. Unless Gödel made a mistake, but there's thousands of people that have read his proof. Doesn't seem like it's got a mistake in it. I mean, I don't know where the mistake would be. They also make SiC fake diamonds that are way more reflective than diamond. Yeah, they can do all the stuff nowadays. Good evening. Yes, good evening. Yes. In my country, we had proofs in how we did high school, but they were optional, and most didn't do them. There was one elective where were mandated and a part of the course if you took it. I gotcha. Yeah, yeah. Proofs. Yeah, proofs is kind of a separate topic. Yeah. Can you prove the derivative of e to the x using the limit definition, or do you need a series? Prove the limit of e to the x. Well, you got to tell me the definition of e, right? Um, so e is you got to tell me what the definition of this number is, right? And then I'd be able to tell you the derivative, right? In a rigorous sense, right? So if you take this number to be the limit as n goes to infinity of 1 plus 1 over n to the n, now you have a explicit value of what e is, right? So now I know what e is with 100% certainty, right? And so now, if I want to do the derivative with respect to x of e to the x, right? Since I'm using this particular definition, I can see that this is going to be the limit as n goes to infinity of 1 plus 1 over n to the n times x, right? Derivative. I'm going to put the derivative in the front. Okay. Now, technically, I skipped a couple of rigorous steps here, but in a calc class, we don't care about those, right? But the rigorous steps would be that differentiation is a continuous operator and e to the x is a continuous function, and so the limit can move around between those. But again, who cares, right? That's not really relevant. So let's go ahead and do the derivative of this. How do you do the derivative with respect to x when you get a power, right? So that's just a general thing that you have to know, is how do you do the derivative with respect to a power? And what is that? What is the derivative with respect to a power? Isn't it like ln of a times a to the x? Of course, I'm using e again, so you'd have to go prove this first before you could finish this proof, I guess. And that might be, I might be assuming the thing that I'm already trying to prove, so maybe I'm being a little not rigorous here. But yeah, we'd like to see a demonstration that this works out okay. So this turns into ln of 1 plus 1 over n times 1 over ln of n to the n times x, right? Times n, right? And then we know what this is, right? Because this is, the limit of this thing is just e to the x again. And so the real question is, what is the limit of the other part? So what's the limit as you go to infinity of ln 1 plus 1 over n times n, right? And I think that's like L'Hopital's rule or something, if I had to guess. So if I plug in infinity, I get 1 over infinity. 1 plus 1 over infinity is 1. ln of 1 is 0. If I plug in infinity here, I get infinity. So this is 0 times infinity. So this feels like a L'Hopital's problem. So we're going to do, we're going to leave the ln of 1 plus 1 over n up here. And then we're going to put 1 over n down here. And so if I plug in infinity into both of these, I get 0 over 0. And so I can use L'Hopital's rule, do the derivative of the top and bottom. So the derivative of this is 1 over n times the derivative of the inside, which is negative 1 over n squared. And then the derivative of the bottom is negative 1 over n squared. So it looks like those are going to cancel. And I have the limit as n goes to infinity. And that becomes 0, so you get 1, right? And so back to the original problem. We have the limit as n goes to infinity of ln 1 plus 1 over n times n. And we have this other part, which is well, it's the 1 plus 1 over n to the n to the x. And so the limit of each of these parts is known. This one is 1, and this one is, again, the definition of e. So we get e to the x. And so the derivative of e to the x is e to the x. That's my best attempt to try and avoid e, doing the definition rigorously. I had to make a lot of assumptions, so it wasn't clear what things I should be allowed to assume and what things I shouldn't be allowed to assume. This could trail off and become an incredibly complicated problem. Like if I had to go prove this, and I had to go prove L'Hopital's rule, and I had to go prove, like, so the point is there's always going to be stuff you have to rely on to demonstrate the thing that you have of interest, right? But yes, it certainly is the case. The derivative with respect to x of e to the x is e to the x, right? Yeah. Do you need a series? You can prove it with a series. If you grant me the series, like if you just tell me the definition of e to the x is the sum of n as it goes from 0 to infinity of, what is it, x to the n over n factorial. So if you just give me the series, then it's an immediate consequence, right? Because the derivative of this is the derivative as n goes from 0 to infinity of n times x to the n minus 1. Or 1, sorry, because the first one came out to a 0. and then over n factorial. And so that's the derivative, and the n's cancel. So you get x to the n minus 1 over n minus 1 factorial, sum as n goes from 1 to infinity. And since I'm starting at 1, that's the same as starting at 0 if I add 1 to these numbers. And so this is the sum as n goes from 0 to infinity of x to the n over n factorial. And that, again, is the definition of e to the x. So it all matters where your starting place is. If you tell me that this is the definition of e to the x, like you just declare, that's the definition of e to the x, you don't have to go prove that or anything. That's just what we're going to define it to be. Then you're done, right? That's the definition. Interesting. I meant but didn't specify that you want the limit of the derivative, but I see how the definition of limit of this equals this would now work. The limit of the definition of e. Sure, yeah, we could do it that way too if you wanted. The limit as h goes to 0 of e to the x plus h minus e to the x all over h. So I want to demonstrate that this has a limit and that the limit is e to the x. Kind of like what I did with the other definition. We know that the e to the x factors out, and we have e to the h minus 1 all over h. And again, you have to tell me what rules I have available to me, but I would assume doing a limit like this, we have L'Hopital's rule available to us, right? Of course, that's going to assume the derivative of e to the h, so that's probably a little flawed. So how else would you do this without... you probably have to do it with delta epsilon. I mean, how else would you do it? If you're not allowed to assume that you know the derivative of e to the x, that kind of makes things a little tedious. Yeah. Yeah, because if you have L'Hopital's rule, right, you just say, well, the derivative of the top is e to the h, and the derivative of the bottom is 1, and so then I can plug in the 0 and I get 1, and so the limit of this is 1, right? But how do you prove the limit of this is 1 if you don't know that the derivative of e to the h is e to the h, right? Yeah, that's probably going to have to be some type of delta epsilon proof, right? So I don't think that that's like an immediate thing. Maybe there's like a squeeze theorem in there. I don't know. I have to give it a little bit of thought. It's not going to be an immediate thing. What's the topic? It's just debate night. Whatever anyone wants to chat about. So if anyone wants to raise their hand and pop up, we can have a conversation. Sub in limit definition of e. Yeah, that might work. But so you're being a little, you have to be a little careful, right? Like if, it depends on, it always depends on the starting place. Like what are you defining e to the x as? If you start with one definition for e, then that would be the thing that you would use, right? If you want to use the infinite series, then that would be the thing. There's always going to be a starting place that you start at, right? Oh, did you mean here? We plug in e to the h here. Yeah, that might work. I don't know. Does it work? Then you're going to have two limits. It's going to be the limit as h goes to 0. I don't think that that's going to be super helpful. The limit as n goes to infinity of 1 plus what is it? H over n to the n, right? Minus 1. Or you can put it up there too. You could do n times h, and then that's all divided by h. I don't know. So what is then you got to do the binomial theorem here. So you do the binomial theorem, and then the 1's cancel, and then there's an h, and you could factor out the h, and it cancels with the h. Yeah, that would work. Yeah, you could do that. And then the h goes to 0, so the only thing you need to know is the linear term here. Yeah. Yeah. That's making it too complicated. I feel like it's getting too complicated. The sum of n choose k, 1 to the k, h over n to the n minus k. This is minus 1, and this is over h. So the first term, when k is 0, sorry, when k is, oh, I wrote it backwards, but so when k is k and n minus k. So when k is 0, then you get 1 here and a 1 here and a 1 there, so that cancels with the 1. And so you can rewrite this as the sum of k as it goes from 1 to n of n choose k, 1 to the n minus k, h over n to the k over h. And so since k is always greater than 1, you can factor out a h now. And so you get, this is horrible, k as it goes from 1 to n with an h out in front, n choose k, and then you have a h to the k minus 1, and you have an n to the k, and then that's all over h. So now the h's cancel, and now you have this horrible looking thingy, but h goes to 0, right? So since the h is gone, now you can have h go to 0, and all of these go to 0 except the last one, except the first one. So you get n choose 1 times by n to the 1, and n choose 1 is n, and so you get 1. Ah, okay, we did it.
You know,
Oh yeah, yeah.
looking at all this math, it kind of just makes you think of, how NASA, when NASA was trying to go to, the moon and everything, right? I'm like, dang, they had to do all because today in this day and age we have, like a lot of technology that helps us do many calculations like ASAP on the double. But back in
Yeah.
the day, that was, like that was rough. That was rough back then, and they still
Yeah,
did it though.
they yeah, I mean they also had different, they had techniques we don't use anymore. So they had log tables and things, and so there was, they just did things differently, right? Um but yes, it is true that like at NASA, they had whole, basements filled with people, mostly black women, right? Doing computations, right? They would do all kinds of computations. They were called computers. Um, so that's how they calculated things. Hmm. Yeah.
Yeah. I'm not gonna lie, like all the stuff that NASA did, I give them props. They did, they definitely gave,
Hmm.
they didn't just bring the country forward. They brought everyone forward. That was kind of cool. But I just think it's crazy how also in this day and age, so many people like want NASA to be defunded or think NASA is a waste of time.
Mm-mm. Yep. Yep. Yeah, that's true. So E is 1 plus 1 over n to the n, but if you, but that's another definition for e to the x, right? You can, so you can put the x on the outside because you can define e as the limit, but a lot of times we define this to be e to the x, 1 plus x over n to the n, right? So if you just take that as the definition of e to the x, then the binomial stuff works out fine. Yeah. Sorry. I'd say the typical Calc 4 course is a good starting point for quantum mechanics. Typically, start evaluating solutions. Blah blah. Yeah. Slang, fun. Yeah. Euler did not die 243 years ago for this proof to exist. Okay. I mean, Euler. Euler would have done something annoying. I can't imagine what he would have done. Something like drawn a picture and been like, it's obvious. You know. Okay, Zeno, you'd like to chat? Let's go ahead. I'll let
That's
you go
funny that you
chat.
say.
Oh, sorry.
That's funny that you say Euler would do some. Wait, like, what's the history behind that? Because I've heard of things like this before, where people would send him like letters, and they'd ask him to like, oh yeah, I think that's how like algebraic what's it called? What's the freaking thing I'm looking for? Algebraic topology. I think that's how it was. It started like the foundations. A mayor or something asked him, "Hey, I want to do this shape around this bridge and do it the fastest or something," and then Euler was like, "You can't," and then I don't know. But like, what's the history behind that?
Just some of the ways in which Euler would write things, and this isn't a slight against Euler. It's that the rigorousness of math hadn't really been developed, and the rigorous part didn't really exist till like the late 1800s, right? So like 1890s, 1900, 1910. That's when like rigor started to become a real, pain in everyone's side. There was even like this, in essence, depression period in analysis when they kept asking questions like, well, does every function do this? And then people would find a counterexample. Well, does every function do this? And then people would find a counterexample. Well, is every continuous function differentiable? No. Okay, well, is every absolutely continuous function differentiable? No. And like the point is that there was this pretty deep period of like, as they tried to refine the math more and more, they just started discovering more and more problems in it. And you have this whole hierarchy of like counterexamples to stuff and definitions. And anyway, I'm just saying math became more rigorous. But in Euler's day, things were a lot more of just like, but if you can do it and it works, then that's then that's
Valid.
fine, right? It's kind of like how physicists behave nowadays, right? They kind of do that. So like for you know um, Euler, if he was doing a limit, and he probably wouldn't necessarily use this notation, right? And he was just n plus one or whatever. He'd just plug it in. He'd just be like, well, infinity plus one is, obviously infinitely large, and anything divided by an infinitely large number is zero. And so that was very a fluid thing to do, and he would just do that. And so then you'd give him something like, the limit as x goes to zero of sine of x over x, and he'd be like, well, sine, you just plug in zero, right? So you get sine of zero, plug in zero, you get zero over zero. And so he'd look at this. They would have tables and stuff. They would call that like an indiscriminate. And they'd be like, well, that means I don't quite know what the answer is, but we could just figure it out from like plugging in a number or something, or through some other process, right? Um, and so they might even say, well, I know that sine of x, the Taylor series, is linear, so this is like probably a linear in x over x. And so they'd be like, well, the approximate linear equation over x, I just need to know the first coefficient of the linear equation, and the linear equation for sine is, what is it? It's just x, right? It's like x minus, I can't remember, x minus 1 over 3 factorial, x cubed plus dot dot dot. And so the coefficient of this is 1, so they'd probably just say like 1 over 1, and they get 1. But the point is that they didn't have any of the, you know, delta epsilon, rigor, carefulness type things going on. They just kind of talked about things being close or not close, or, you know, pick an infinitely small number or cut a circle up into an infinite number of pieces. And so math was just, it was a little easier to talk
Wishy-washy.
about, I guess. Yeah, but they wouldn't say it was that way, right? Because they didn't they didn't have any of the rigorous
Their
stuff
ego.
coming out later, you know.
Yeah.
So just remember, in throughout all of Euler's life, as well as, you know, many mathematicians after him, there was no concept of countable or uncountable. Like those two concepts alone didn't exist, right? Meaning that they didn't have
Really?
a they didn't have a rigorous definition of sets either. Sets were just collections of numbers, right? There was no, you know, they didn't have a concept of measurability. They didn't have a concept of measure theory. They didn't have measurable sets. They didn't have uncountable sets. Topology hadn't been invented. They had no idea of, like, you know, what is that famous theorem called in topology? But yeah, anyway, they were missing a lot of these things. So it was a lot more like the calculation is what it is, because when I plug in, you know, some numbers and it's close, then I can see what it is, or I have some other method to argue it, right? And so they would argue about things in a less rigorous sense.
Did things get better because of logic specifically, or was it just people like questioning things? Like, what was the reason for the evolution of
I
rigor?
I think it just evolved over time as more complicate, like more examples came about, right? Like there's a book I remember reading on famous incorrect statements made by famous mathematicians. And I can't remember the name of the book that did this, but they went through various claims that were made. So it may have been Euler. I don't remember if it was, but one claim that was made was that, like, if you have a sequence of differentiable functions, then its pointwise limit is also differentiable. Like this was thought to just be a true thing. Like, here's all the things that are differentiable. I take their limit, I get a differentiable function, right? Well, that turns out not to be true in a rigorous sense. And the issue, or I guess the way that they were thinking about it, was they were just thinking about limit very loosely. And it turns out that for functions, there's actually two limits. There's a pointwise limit and a uniform limit. And so that type of rigorousness came about later, right? When people were trying to be, like, very clear, like, exactly what do I mean by limit? Well,
Right.
you know, if I'm trying to be very clear on that, then I have to be careful of, like, oh, do I mean for every x the limit does the thing? Or do I mean the limit does the thing for every x, right? Like, putting the order matters, you know? And so when you start being really careful, then you start ending up with these counterexamples. First one is a counterexample that you can have a limit of differentiable functions, and it is not differentiable, right? Yeah, so, you know, tricky stuff. Did you learn about the history of math to help your understanding, or just for fun? Just for fun, you know. The you I learned a lot more about the history of math when I was in grad school, because in grad school you care a lot more about where stuff came from, like who figured out what, when did they figure it out, how did they figure it out, and especially when you specialize, you answer just a ton of you're constantly wanting to know history and properly attributing and how to write your bibliography and all that, right? And so you end up learning a lot of history. So I have an interest in it, but honestly, if you want to learn history of math, just get a good one of these good non-math books. So like one of these is probably excellent. I would say where's a good one where you just learn all the cool shit. This one. So Canigel, The Man Who Knew Infinity. This is an excellent book. It's not a math book. I mean, it has math in it, but it doesn't have homework problems or anything. It's mostly a history book. And you read that one book and you'll learn all about, like, what did Euler know? What did Gauss know? Who was fighting with whom? What kind of stuff was going on? Blah blah blah. Oh, this is Bobby's book list. This is my book list. So if you go to my Discord, I got a little channel on there that says book list, right? And you can have a list of all the books I own if you want them. It's actually only
You should have like a link tree where you could put like the merch and the book list and all that stuff. Put it on your Instagram.
Yeah, maybe. I mean, I have the buy me a coffee and all that on the Instagram, so it's on my profile and the YouTube video, and all the YouTubes are also tagged with the Discord channel and everything. So like if and the Instagram has the Discord channel in my name as well, or for my profile. So I'm trying to keep everything organized on the Discord channel. So if you go to the Discord channel, you can find all the content and whatnot. Yeah.
Also, it'd be funny if you. Oh, sorry. It'd be funny if you called the Gauss and the Euler mugs, if you called them donuts. That'd be a funny math joke.
Gauss and Euler. Yeah, that'd be funny. Let's see. Someone wrote, I've often seen visualized geometric description of a snail shell spiraling of Fibonacci series, but is there a way to assume paradoxical continuous Fibonacci sequence which details decimal x inputs? You'd have to tell me more, man. I think the Fibonacci sequence is related to the golden spiral, which is commonly shown on various things, right? I could go into why if you wanted to know. Basically, it's the simplest difference equation that you could possibly come up with. Like if you were attempting to come up with a discrete equation that does the most basic type of replicatory step you could possibly think of, you would have the Fibonacci sequence. And so anything that is behaving and trying to do replicatory behavior is going to exhibit the Fibonacci sequence, as well as its ratios, as well as its limits. Like that, this is just a benignly obvious thing. And so the idea that nature is filled with the Fibonacci sequence everywhere is like plainly obvious. But someone wants to come up chat. Hey, how's it going?
Hello. I didn't mean to interrupt that.
Oh yeah, no
That
worries.
hand- Yeah, no, I had a few questions actually.
Sure,
I have
sure.
one original question, and talking to Zeno for a second, maybe think of another question. I guess I'll let you pick which one you think might be more interesting to discuss. One of which was, I think I discussed with you in the past, what Gödel's incompleteness theorem exactly is, which might be an interesting discussion to have, in the sense that being able to not just read a Wikipedia, but talk about it and see things written down. The other one, since we were talking a little bit about quantum mechanics, gave me the idea of oftentimes we use eigenvalue solutions to differential equations, but I don't think it's really exactly obvious why that works when solving differential equations and how they apply to like linear transformations and things like that.
Yeah, we can talk about
We
either
use
of
it,
those. Um,
yeah, I don't know. I
or
don't know what would
both
be
of
more
them.
interesting.
Well, so the my hang on, let me restart the thingy. This is an unbelievable number of things I have to click to restart a stream. You know that?
What happened?
Oh, Instagram only lets you stream for an hour.
Of course.
Yeah, why? I don't know. Because
Well,
they just do it, you know. So anyway, so when you're every hour I have to restart it. Now the YouTube gets to stay up, you know, but the Instagram decides to end. So Gödel's
anything
incompleteness
more than an
theorem.
hour.
Oh,
Yeah.
sorry. So Gödel's
I was gonna make
incompleteness
a stupid
theorem.
joke.
So let's see. So Gödel's incompleteness theorem. So Gödel, let's see how to explain this. So when we're defining a logic system, there's a couple of different elements that go into defining a logic system. But for the most part, however you think of those particular elements, the main objective is to try to box the logic system, right? You know, maybe it's got like, it's an open box, right? The objective is to try to make a box where we put the logical stuff inside of it, right?
Right. We're not seeing where you're streaming. We're seeing your list of books.
Oh, geez, my bad. Knew I was making a mistake somewhere.
There we
So
go.
I was drawing an actual box, right? So this logic, right?
Sure.
So our objective is to make logic boxed in, and so we do that through a number of rigorous steps where we say, okay, well, let's first define a language, which is like a collection of symbols. Let's now define what we mean by a proper sentence, and so we come up with some rules that have to be followed to make a proper sentence. And then we go, okay, we're going to put those proper sentences into the logic box. Some of them, you know, we're going to paint blue because we will declare them as true. Others of them are red, right? Then we're going to come up with a notion of what it means for something to be proven in that box. And we'll tell you what the rules are for that or whatever, right? And so the box gets filled with some stuff, you know, some things for every x, you know, there exists a y such that, you know, p of x, y or whatever. So statements go in. Some of those statements are true, some of them are false, you know, some of them are axioms, some of them are theorems that get derived from the axioms, blah, 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 right? So one particular box that's very important to us is arithmetic, right? And so we're interested in arithmetic. And arithmetic can be defined in a number of different ways, but typically it's going to be, you know, everything that includes like the numbers, right? The symbols that define those numbers, addition, and like multiplication, right? And so the outside observer, you know, the mathematician, they are separating themselves from the box. They just want to talk about what's in the box. They don't want to. They're out here. What's in the box is in the box, and they're just trying to figure out about arithmetic, and presumably, the arithmetic that they've defined is completely disjoint from any preconceived notions that they personally have or whatever about how the world works or whatnot, right? Unfortunately, as the person is looking around in the box and they're like exploring patterns, you know, they're trying to categorize some of the theorems or whatever, they are going to start listing out those theorems. So they start sitting there and they're being like, hey, you know, I got this list of like, you know, cool theorems or whatever. And so they start listing them out. They're like, oh, this is theorem 1. Oh, that's kind of cool, or here's theorem 2. Oh, that one's kind of cool. So like all of these are categorized under that. And then maybe they have another list over here of like, semi-cool theorems or something, right? And so they start listing all them out, whatever, right? And so at first, they think everything's fine. They're just studying arithmetic and they're not even thinking anything of it. They're just looking at the equations and they're just listing out these statements and they're like, look at all these cool.
Can I interrupt?
Yeah. Sorry.
For theorems, what do you mean exactly? Like sort of relationships between the objects?
Yeah.
The arithmetic that you have defined instead of
yes. Statements about these symbols, right? So it could be 1 + 1 = 2,
Sure.
or maybe something more complicated like 1 + 2 all the way up to n equals n times n + 1 over 2 or something, right? Or is it minus? It might be a minus.
Sure.
In any case, different theorems, right, show up, and then you put them in different categories. And the point is that you feel that you've defined arithmetic in the box, and you're the user over here, and you're completely disjoint from the box, and you start exploring things about the stuff in the box. And then suddenly, while you're looking at all of these theorems, you start noticing that the statements that you're writing have a relationship to the numbering that you're using to categorize them. And you start looking at these and seeing that these have patterns to the symbols. And so a crazy person...
Mean numbering they use to categorize them?
Yeah, so the crazy person, right, Gödel, he was like, yo, I can categorize these in certain ways such that the theorems themselves talk about the patterns of their own numbering that I'm using, right? And that is
right.
an unexpected...
I'm a little bit lost.
On which part?
What do you mean by the numbering? I thought they were just these arbitrary, sort of unrelated, some semi-related theorems. But,
yes.
What is the significance of the numbering?
So there's a subtle thing that happened here. We had a box where we put numbers in it, and we used other symbols for those numbers. Mm-hmm. But then we went to talk about the things in the box, and we started numbering them with a list, right? Those numbers are not part of the box. They're my numbers. I have some numbers that I'm talking about, and I'm using those numbers to talk about the statements in the box, right? Does that make sense?
Okay.
And so what ended up happening was Gödel realized the numbers I'm using can actually be lined up and put into lists with the statements that are in the box. And he started realizing, wait a second, I over here, the mathematician, I can actually find functions that do crazy things, like take in a theorem and produce its proof. I can develop that, but not in some rigorous way, but simply because of how I align the theorems together. Because I can align the theorems so that, like, this is statement 1, this is statement 2, this is statement 3, right? And then I'm numbering them, right? And my numbering is going to correspond to how the proof of these is going to look. So my number might tell me about the proof of the theorem. Or my number might tell me about the theorem and its, secondary consequence or whatever, right? So the point is that my numbers might be able to tell me about the proofs or the statements or whatever of the things in the box, right? And that process of mapping out the relationship that these statements have with the numbers is this process that Gödel came up with was called Gödel numbering. And in some sense, nowadays we don't really think too much of it, because nowadays we all like know programming languages and stuff, and so the idea that like any program you write is, you know, in binary, and then every binary sequence you come up with is some natural number, some astronomically large natural number, but it is a large natural number. That's exactly what Gödel did. Gödel pointed out that every statement I ever write is some unique natural number, and that every number the mathematician uses is also just a natural number. And that in reality, anytime I was making a list of theorems or a list of lemmas or a list of whatever, I was always just making a list that was comparing lists of natural numbers to my own natural numbers. And because that was the case, I'm able to construct lists that have particular properties, such as lists that are able to find their own proof, or lists that are able to do, you know...
Well, I mean, that seems...
Yeah. So, sorry.
It just seems a little bit weird to me that, I mean, you're writing these statements using sort of these elementary operators. I would imagine there's a more underlying theme here regarding the elementary operators, like, you know, sum, where, you know, I mean, you could create a mapping, sure, but like if you mix 1 and 2, it seems like...
Well, you would
saying
agree...
the same thing. I don't know. I feel like the elementary operators are a little bit more fundamental.
Well, I'm just saying that you would agree that,
right?
like, we could systematically lift out...
I don't know. When you're writing 1 plus... No, sorry.
I mean, you would agree that we could systematically list out every possible statement we could ever create from these symbols, right? And, you know, maybe I throw in an equal sign there, right? Because there's a countable number of them, and
right,
we know how they're generated,
sure.
Right? And so there's a way I could write a program that writes up every arithmetic statement ever, right? And so that program, every arithmetic statement, each of these could be encoded, right? And hence that program is really just a sequence of some natural numbers. Like, it's just outputting a sequence of natural numbers. But more importantly, every one of those statements that's true has a proof, and those proofs are also made of these types of statements, and they too are also natural numbers, which means that every proof is also a sequence of natural numbers. And that means, and in theory, every sequence of natural numbers is some other larger natural number. And so the point is, every proof is a natural number, every theorem is a natural number, and every list I do as the mathematician is some list of natural numbers or lists of proofs of those natural numbers. And so I'm able to construct, and in some sense this is kind of like programming, I'm able to create a chip that can do things very weird, such as I input one of the statements and it tells me the proof for it. Or I input a thing and it tells me whatever, right? Based on particular lists or whatnot, right? And so this is where this breakdown happens. He ended up demonstrating that there's a strict relationship between the numbers that you attempt to use to list out the theorems that you're trying to talk about and the theorems themselves that are trying to talk about the arithmetic that they're attempting to encompass, which supposedly includes the numbers that you're talking about. And so because you end up with this recursive feedback, right? Like, what am I trying to say? This function that you think that you're defining on the outside is one of the statements in your list, because it's a statement about natural numbers, and you define the box to be the list of all the statements about the natural numbers, right? Does that make sense where we're going with this in the recursion? Like, everything that I define about the natural numbers here is also going to be a statement in the list somewhere.
It does make sense, but it seems a little bit weird, but yes.
Well, Gödel does it far more rigorously with, dozens and dozens of pages, but...
It just seems like, I don't know, a little bit, where's the...
Well, it's almost identical to the Turing issue, right? Like,
it just seems like it's a little bit of a simple mapping rather than, I don't know where the incompleteness comes in.
Oh, well, the incompleteness comes in from the particular statement that gets created, right? And I don't remember it off the top of my head, but it's you effectively have a function that does something like this, and it's going to be one of the statements in here, right? Or maybe it's the opposite. I come up with a function that says, it plugs in a theorem and it says, no proof or something, right? So it'll tell me whether or not a theorem has a proof or not. So it'll be like, this theorem has a proof and this one doesn't. But every theorem is just one of these integers. This function itself is one of these integers, so it's on here somewhere. And so you end up in a weird question of like, well, does f equal f? Like, what is this? Does this equal proof or no proof, right? And I'm not sure it's this particular one. We'd have to Google it. But there is a function that is in the list, and because it's in the list, it gets plugged into itself because it's a function you defined outside the list, but it's a statement about natural numbers, so it's also in the list. And so you end up in this weird recursion where you're like, well, what is f of f? And it's like, oh, you will be unable to resolve this unless you give up something, which is the fact that you could actually list all of the known arithmetic, all the how do we put it? The thing you have to give up is that you are able to actually produce a list of all of the true statements that have a proof. So that's what you have to reject. So if you assume I could list out all the true statements that have a proof in the arithmetic system, that is what ends up having a contradiction, because if you could do that, then there are some functions that would end up on that list, and you could demonstrate it, and then those functions would compose with themselves, and you end up in this contradictory state, right? And since you end up in this contradictory state, you have to reject that was possible. And so the rejection is, it is not possible.
That makes sense. Yeah. Using.
Yeah, so it is not possible for you to list all of the true statements in arithmetic that have a proof within arithmetic. And hence, if arithmetic is consistent, which we assume it is, then there must be something that's true that can't be proven. And that's Gödel's incompleteness theorem, right? Yeah. Anyway, so I'm glossing over details, and we'd have to go look it up to.
I don't know. It's still a little bit of an abstract difficulty. I don't know. It's kind of hard to understand, but
it certainly is. But the main thing, the main thing that is missed by people is.
I'm happy to see the details, but a lot of times get lost in this formal logic aspect of things. But the
Sure. Yeah, but the main thing is, and I think people get lost on that, is there's two different sets of numbers.
It seems that at some point, if you
Sorry, I thought you were going to say something. There will always be a statement that exists that cannot be derived from existing axioms. When you introduce a new axiom to account for it, you create the problem.
I'm thinking
Correct.
a little bit, but it seems almost if inside of this. Right. So at a certain point, it's like defining something with its own definition, effectively. At a certain point, it boils down to that. Right. I mean.
Yeah. Well, the main thing
if you were to sort of look at this object from a observer standpoint, you would effectively have to
the thing that
define itself with itself. Eventually.
Yes. Well, the thing that is happening is
no, that's not right.
The mathematician is attempting to enumerate statements, and the fact of attempting to enumerate them means that they are using numbers. And because the statements themselves are numbers, then every statement that they could make about the enumeration process itself is also a statement about natural numbers, and hence may also be a theorem about the natural numbers, meaning that it would also have to be in the list, since you're trying to construct the list of everything that's true about arithmetic, right? And so that's what is happening is when I attempted to list them, because the list is all the state is attempting to be
Very paradoxical.
all the true statements about arithmetic, that's what it's attempting to be, then any list I do of that, or any statement I can make about the listing of that, those statements must be in the list somewhere because they're statements about the arithmetic. So this is very specific to arithmetic. This only happens because of arithmetic. It's when you go to list arithmetic statements and they're being enumerated, then statements about the enumeration are also in the list of the arithmetic because they're the statements about arithmetic. So as long as you're not doing arithmetic, you may not have Gödel incompleteness happen. But when you're doing arithmetic, then you end up in this, recursive. Right. You end up talking about yourself, right? You're talking about your own arithmetic. Yeah. Mm-hmm.
Right, exactly. It's like defining yourself, right? And it's very, it's paradoxical if you try to do really anything using the statement of all statements to show a statement that is a subset of that statement. You know what I mean? It's just very circular, I guess.
Yeah,
I think I understand what you're saying. It's very interesting that he came up with that.
Yeah, we'd have to write it out rigorously. It'd be something like, suppose.
It makes sense.
Yeah, suppose I had the list. Yeah, suppose I had the list of all statements and their proofs, right? So they've all been proven. I have their proofs here, and I have all the statements of them. You then have to make a relationship of those. You go, well, do this function, the function that says that the proof of said statement is not the number on the right, or something. I don't know. Again, we'd have to go look it up, right? And then the problem is that whatever statement you make to try to make that relationship will also be in the list. And so then you have to ask, well, what happens when I reach myself and I'm trying to talk about my own proof, right? And you're going to end up with a contradiction. It's very similar to like Turing's thesis, where you can't have a program capable of figuring out if every other program is going to halt or fail. And the way you can demonstrate that is you can just assume that there is such a program, and then you can demonstrate that you end up with some type of contradiction. And this is very similar. Assume I'm able to list out all the statements about arithmetic, and they all have a proof, right? Then what would happen? Well, what would happen is you'd end up making some recursive relationship between them, which would be about natural numbers. And because it's about natural numbers, it too must be in the list, because every statement about natural numbers is in the list, and then you're able to make a contradiction out of that. Yeah.
I think that makes sense.
Yeah, we can always try.
It's weird.
A lot of
not what I thought what it is, but
yeah, if you Google it, they'll tell you that the thing that they'll typically
I think I get the idea.
Yeah, they typically tell you the thing that gets constructed in the words of what. Oh, sorry. They typically tell you the thing that gets constructed in the words of its meaning rather than like what it is explicitly. So normally the thing that gets constructed is some statement of like, this statement is true if it has no proof, or something like that. And I'd have to Google it, but like,
sure.
Yeah. Like what is the statement that is constructed in Gödel's incompleteness? So this
it's
statement,
like you can't make a logical statement.
you can't make a logical statement outside of the logical system without using the system of logic. Therefore, you're effectively just using the system of logic, right?
Well, so for normal logics, we do that all the time. We go logic, meta logic, meta logic, meta logic, and we have no problem doing the hierarchy that goes on forever. But when it comes to arithmetic, we kind of end up in a funky place because we thought that we were only talking about arithmetic statements, but then we figured out that those statements include all the statements that we could make about the arithmetic statements. And so, in some sense, arithmetic doesn't have a meta arithmetic, because meta arithmetic is also statements about arithmetic, because statements in arithmetic can be encoded as natural numbers too, so they would also be included in the arithmetic statements. So in some sense, Gödel ended up also demonstrating as like a side consequence, there is no meta arithmetic. You can't do that. So there's no meta arithmetic either. Like arithmetic just doesn't allow you to leave the system, you know. Anyway, so the statement F is it's equivalent to this notion, which is this statement cannot be proven within the system.
It's like 1 + 1 = 2, and maybe you want to use the proof. Well, that's because 2 - 1 = 1, or that's not right. Arithmetic.
Yeah, cannot be proven.
I get the idea. I'm explaining it incorrectly, but I think I understand. Well, I'll leave somebody else to give another question.
Yeah. No worries.
Yeah, I understand completely.
Hey, Axiom, is there a debate tonight? There's only a debate if people come and debate. I can't debate, I can't box with a shadow. Someone's got to show up with a controversy they want to discuss.
Yeah.
Oh, wait, no, my understanding of this extends beyond arithmetic. That's funny. Yeah, so that's Gödel's. What was your second one? Your one on something with eigenvalues or something? So what is it? So you have an operator, and it takes things to...
It's just weird. It seems like going in circles and circles and circles. Yeah, I don't know if anybody's interested in talking about that, but generally speaking, in...
Are you still there? Is it me, or do you keep going silent?
Yeah, I'm here.
Can
you hear me now?
Okay. I can hear you now. Yeah. The
Fantastic.
Yeah. No one heard any. Whatever the second question was.
Well, the second question, again, I don't know if anybody's really interested in this. We've been kind of going on for a little bit on this topic, but was oftentimes in mathematics we use eigenvalue solutions to solve differential equations, and that has a connection to how things transform under linear transformations. However, it's not exactly obvious to me how this works in solving a differential equation and why we can do that. Right?
Solving
Why
differential equations. So you mean
using eigenvalue.
So you have like
eigenvectors.
A differential equation, right? And that differential equation, you think of it like an operator, right?
Right.
So you give it a function, and then it produces an eigenvalue for that function, right?
Right.
And so the question is, if the differential operator exhibits a bunch of eigenvalues and supposedly eigenvectors with it, right? Then how does that help you find solutions to it? Is that what you're trying to say?
No, I think actually going through the arithmetic and using them to find the solutions is fairly, simplistic. However, it's not exactly obvious why that works. Right? So why can you do that?
I don't know, because the math works. Um,
Well, I mean, yeah, we solve it, by hand. We do it. We use the tools. Okay.
mm-hmm, mm-hmm.
Why do the tools work? So why do eigenvalue solutions work for a differential equation?
Eigenvalues
Right?
work for different. Yeah, I'm not
Does that make sense?
sure. Yeah, I think so.
Never
So
been clear.
there's a lot of unknowns about differential equations to begin with. I should point
Sure.
out, right? So, like for example, entire functions, the space of all functions you would ever want to work with, right? E to the x, sine, whatever, right? These are entire functions. Entire functions are wonderfully approximated by polynomials. We like to talk about polynomial differential equations. We typically like to look for differential equations that exhibit a basis that is orthogonal, that allows us to calculate out any analytic function we want, right?
Sure.
If I were to just give you that as a general statement, like differential equation is going to exhibit a basis for me. That basis will be, it'll have some eigenvalues. It doesn't matter what they are. And so here's my differential equation. Arbitrary differential equation. I want a basis. I want the basis to be orthogonal. And I then want to use this basis to write all other functions. So you give me any function, and I'm going to write it out, as n goes to infinity, in terms of this basis. So it'll involve some coefficients, and it will be in terms of this basis. So one, there's a relationship of these coefficients to this differential equation, right? And we could calculate that out if you want. But the point is, this very general understanding, if I were to just ask you, what types of differential equations can you have that allow you to do this, right? It might be incredibly surprising to learn they're heavily restricted. There's only a particular set of differential equations that work, right? And the answer is your differential equations are either order 2 or a multiple of order 2. So like there's only order 2 differential equations that do this, and then you can trivially just compose it with itself over and over again to give you more differential equations. But the base case is order 2 differential equations. So let me be clear. Since an order 2 differential equation composed with another one is order 4, there are no order 3 differential equations that do this. 0, none, right? That is an incredibly unintuitive result. That there is no order 3 differential equation that allows me to decompose all entire functions into an orthogonal basis.
It's a little bit weird because it seems,
Yeah.
I always thought that it only applied to, like, this works for any linear operator, right? So
we think of these as linear operators, but if you write your linear operators as differential equations, you're not guaranteed. And to be clear, all linear operators can be written as a differential equation. So those are synonymous when you're talking about functions, right? But when you say give me an order 3 differential equation that exhibits an orthogonal basis so that I can decompose every function in existence, the answer is none. There are none. Yeah.
It's weird. I don't know if I like that.
Yeah. So that I think that was figured out by a guy named Crawl, if I remember. Crawl did a bunch of work on stuff. So the statement is, there are no order 3 differential equations with an orthogonal basis eigenvectors. right? Incredibly unintuitive. Like, who would have thought that, right? That's just not something someone would know off the top of their head or
Yeah,
have thought
I'm
would
trying
be
to
the
think about
case,
it.
right?
I'm trying to think about where that wouldn't be the case.
Mm-hmm.
I'm not
Well,
totally sure.
so this also leads to just a selective set of orthogonal bases to begin with. There's only 3 categories of them. The only orthogonal bases that we know of, and more importantly, we can prove that they are the only orthogonal bases for polynomials, are the Hermite, Laguerre, and Jacobi. That is the collection of all orthogonal polynomials. So those are the only ones, right? There are no other ones. And so we know what their differential equations are. They're all order 2 differential equations. So we know all their differential equations. They're all order 2 differential equations. Those are the 3 basic differential equations that can exhibit orthogonal bases. The only thing you could possibly do is just like recompose those with each other and make them order 2, order 4, order 6, right? The same statement applies for odd order, by the way, 3, 5. You'll never find those, right? Yeah. Anyway, what I'm saying,
I don't like that.
Yeah, all I'm saying is there's a lot that we don't understand about the relationship between differential equations and our ability to decompose functions into other forms. In particular, differential equations already have crazy limitations on them that seem unexpected. There's a lot of other parts of this that we simply don't know either, right? There's many unknown problems about differential equations. Right?
Sure, something that's maybe not analytical. Right? That makes sense.
Well, so I'm not sure what you mean by that.
Well, I mean, for example, if you have a 3-body problem, or really just generally any chaotic system, you can't solve it analytically. There is no
what you mean. Yeah.
solution.
Yep.
Right?
Yes, correct. Yes. Yeah, it's that's a chaos theory problem.
Right. But it's just an example.
Yeah, and maybe that's related to this. That there's some type of stability that is required, and then all the other cases. There's cases that have to be skipped because they can't be solved or something. I don't know. Yeah.
Which in and of itself is a little bit weird.
The point is that anyone that goes to study like differential equations for a bit, you're like in this free mindset where you think that like differential equations are just equations like any other equation, and they can be freely changed to anything and can be manipulated and whatnot. And then if you study it over and over again, you start seeing like the same patterns repeatedly, and you're like, man, are there more complicated patterns than these? And then eventually when you start looking into it, you discover actually there aren't. Like, differential equations are like incredibly restricted. You just can't do arbitrary differential equations unless you want to have like no solutions or whatever. Yeah.
Sure. It makes sense. It's a problem that we have a lot.
Yeah. Oh, let's see. There were a bunch on I didn't read. I'm sorry. What is a metric space and what Banach added to it? I don't remember exactly the property for a Banach space specifically. A metric space just means that you can measure stuff in it. A Hilbert space means you have an inner product. And then Banach is probably something beyond that. Whatever the next thing is after inner product would be my guess. Did you learn about the history of math to help you understand? Yes. I read that one. Where can I find that document? Oh yeah, that's on my Discord. You can go to my Discord and get the list of books. That kind of sounded like philosophy to me. I might be an arithmetolian after that. That's funny. What is your response to anyone that brings any Aquinas arguments. I don't know. What did Aquinas say? He said something. Oh, Zena's going to teach me. All right, tell me.
Okay, so basically, Aquinas, he's basically just like a baptized Aristotle. So typically, what I find with Thomist is what they call them. They pride themselves in like, oh, we really try to stay away from the analytic philosophy. We try to avoid S5 modal logic systems. We try to avoid all these things. So when you ask a Thomist, oh, what's the Thomistic like contingency argument? What's their cosmological argument? They'll try to give you like stuff about God's natures, and they'll say like God has these like natures, and whenever you say necessary and contingent, you can't actually say that with Thomistic philosophy. You have to use their specific terms, and I don't know, maybe it's just me being like too critical or too fond of analytic philosophy, but to me it just sounds like they try to word salad their way out of logic because they know it can collapse really fast if you take it to, like logic systems. Like whenever you ask a Thomist, oh, well, how does the contingency argument not lead to modal collapse? They'll be like, oh, that's just because you don't understand the language that Aquinas is using. And then you're like, okay, but whenever we actually read Thomas Aquinas, he's using like literally just synonyms. Like he's actually using the same language analytic philosophers use. You're just trying to say, oh, but because the word isn't the same, or because he didn't have those systems back then, it's actually not. And it's like, well, it doesn't really seem to make sense because Aristotle, he was kind of like the pioneer of like the Boolean algebra, logic systems, like the yeah, he was one of the pioneers of like modern logic, and I don't know. That's been my experience. Maybe there's better Thomists. There's probably Thomists that have many problems with what I just said. But that's typically what they.
Can you summarize that in a sentence for me?
Yes.
Okay.
Let me think. Okay, well, it's not really going to be a sentence. It's going to be like a scenario. Analytic philosopher. 2 + 2 = 4. Thomist.
Okay.
Well, if you take the essence of one and you add the essence of the other one, then you get the divine essence, which equates to 2 essences. Therefore, when you add the divine essences plus the other divine essences, you get a total of quadruple divine essences. That's what it's. Yeah.
Interesting. Huh. Yeah,
Yep,
I don't know. I'm always against adding in a bunch of unnecessary vocabulary. Unless you gotta tell me why I need the extra vocabulary before I'm like, okay, fine. We'll use it.
Yeah, and don't get me wrong, they have like some things where they talk about like potency and actualization, where like something has the ability to be something, and that's kind of how Aristotle, if you read Aristotle's physics versus something like Galileo, Aristotle is very interested in what something could be and the state that something is currently in, as opposed to trying to make predictions about that thing. So like Galileo, he's not interested in what the ball is currently doing. He's trying to see patterns about what a ball is doing whenever it rolls down a slope or something. Aristotle would look at a ball at the top of a slope. I would be like, yes, it has the potential to be at the bottom, and what we can know is like what it's doing at the top, and then Galileo's like, oh, it has patterns and we can make predictions. That gets into philosophy of science and all that crap. So I don't know.
Gotcha. Fascinating.
So yeah, Aquinas. Best way to summarize it: Aquinas is like baptized Aristotle.
Baptized Aristotle. Okay.
Yep.
Keep that in mind. All right.
Did you make me a mod, by the way?
Yeah, you sent me a message about that.
Oh, thanks.
Right?
Yes,
You've been
thanks.
around a while. I was like, sure, why not?
Oh, cool.
Don't
My
abuse
cat's. Yeah, I'm gonna kick everyone out. No, I'm just kidding.
it.
Wonder if you can hear my cat.
No, can't hear the cat.
She just woke up from a nap and she's still like a kitten, so she's very, very clingy.
Oh, gotcha.
And now she's
have-
like trying to jump on me.
We have 2 cats, and when we got the cats, like they were little kittens, and man, kittens are cute, but like there's all these concepts that I didn't know existed, like the zoomies and stuff, and like they like look at you, and you're like, what are you about to do? And then they like run and leap onto the curtains, and then climb them all the way to the top, and then do like a
Yup.
ninja flip to the top of the, entertainment center. You're like, why? Like they're just looking at you. Oh, and then they get upset that they're stuck up there, and they start meowing.
Yes.
Meow. And you're like,
Yes. No, what mine does is she gets the zoomies and she hits herself so hard because she's so focused on where she's going, and then her behind will just get like hit or caught on something and she'll hit herself, and she tries to play it cool, and then she's like licking that spot 2 seconds later trying to see like, oh, nothing's going on here. But it sucks because she keeps hitting herself, and I'm like, oh my gosh, you're gonna knock yourself out one day.
yeah.
But anyway, yeah, cats are funny though.
Well, if anyone else wants to join the conversation, this might have to be the short stream because it's a Monday or something. I don't know if I can do this every day. Maybe for 2 hours. I don't know. If I try to do this every day, be like 9.
Yeah, it's not,
8 to 9 or something. I don't know.
yeah, it's nice. I mean, it's probably going to be mostly math stuff since there's a lot of math people in the Discord. So
Yeah. I'll have to give it some thought. But the channel's growing, so hopefully it keeps growing.
Yeah. You should get back on PNR soon, just for like clips, like that. That row echelon form guy. That was a funny character.
Oh, row echelon. Yeah.
Help you, yeah. It was like Bobby Goods or some like crazy stuff.
Yeah, I have multiple streams I haven't went and edited. A bunch of my streams I accidentally recorded an echo, and I had no idea the echo was there because apparently it wasn't broadcasting an echo, so no one knew about it. So yeah, it was kind of a anyway, the point is I can't do anything with those, so I skipped a bunch of them. But there's so much recordings. Every time I do one of these, it's so much recordings. It's just it takes so long to record them. I have in my queue, I have 60 shorts. So I was posting 10 shorts a day. But some of the platforms get mad at you. Facebook, they've effectively like banned me or something. Like every time I post, they just give me 0 views, and I'm like, I don't understand. Like that doesn't make any sense. And then TikTok has started giving me views. They used to give me like 5, but now I'm getting hundreds. And it's
nice.
TikTok, you have to be like really like careful, and like I think I cussed in a video, and I was like, uh-oh. So they took away 1,000 views or something. So
so the good thing
yeah.
with TikTok is that you could capitalize on the fact that you have a PhD in math, and you could do like very informative type videos. I know that's how Dr. Blitz does it, and he has like a little banner on his TikTok that says like educator or something. But of course, your videos have to be very like, oh yeah, why does this happen, or why does that happen, or why is this way in math? And they have to be, of course, very family friendly and all that stuff. So that's a potential route you could take it.
Yeah.
Oh yeah,
Certainly.
wait. I don't think you understood my math joke earlier. Not that you didn't understand it. I just maybe like you didn't hear or something. But I was
Mhm.
saying the Euler and the Gauss donut on your website because they're mugs, and I
Oh,
was
I
saying that
gotcha.
that's the
I
math
gotcha.
joke because of topology.
Yes. Yes.
And yeah, yes.
Yeah. Yeah. Those are genus one objects, right?
You know, I have a question that might it's a little bit more personal, I guess, but I figured
Sure.
I'd ask
Sure.
it while I'm here.
Yeah.
Nothing else
Yeah.
to do. I don't feel like doing analysis right now.
Yeah. Yeah.
um, um, so when you were a professor, did you have any students or anything? Like, did you advise anybody?
So I was a professor at a community college, so I didn't have any graduate students or anything. Also, I started my career teaching with my master's degree, and I was working on my PhD at the same time, and then I graduated with my PhD. And so
It's
the,
brutal.
the the yeah, so the point is you can end up with a professorship a little bit easier than having a PhD. Like there's lots of professors that don't have PhDs, right?
Yeah, my sister-in-law, she teaches at the community college for ASL and master's degree, and it's fine.
Mm-hmm. Mm-hmm.
I took physics. I actually took a lot of math courses during undergrad. Sorry, not during during undergrad at the community college, and they were better actually
Yeah, yeah,
at the
yeah.
college
The
and much cheaper
community
for the
college
same
is definitely
education.
cheaper. Classrooms are a lot
I like it a lot.
smaller. I did teach a couple of classes at the university, but you have like, you know, 150 students in a single class or something. Undergraduate classes.
Yeah,
I
I
that
did
was a
the
little much to me. I was like, I don't
I
know.
did the TAing, and we would have to run the courses with all those students, and you're running around, and you can never answer half the questions correctly too. It's pain in the ass. The
Yeah, yeah. At the community
what's the name of it?
college, you know, you get like a dozen students or two
I
dozen.
found it a lot more personal. Yeah.
Yeah, definitely a lot more
Um,
personal. I
but
like that.
but what I was asking, so right now I'm getting later into my PhD,
Hmm.
and the discussion has been effectively with my advisor, which was okay. Well, you're applying all these techniques, but you're not coming up with a technique,
Hmm.
right? You're not coming up with something brand new that we're not really using.
Mm.
Um, I don't know. Do you have any sort of advice or thoughts on that since you ended up doing your PhD as well?
I mean, in math, you have to come up with something new. I mean, I don't know what it's like in physics. I assume you have to come up with something new, but
That's what the
um,
advisor wants. But it's a lot more difficult than I originally anticipated. And getting past
yes,
that hurdle has been quite a challenge.
yes, coming up with new things is a pain in the ass, right? Because you know sometimes you don't even know the right question to answer. But yeah, I mean,
Exactly.
mathematicians are constantly accustomed to being presented problems and then being told to solve them on the without being told how to do it. So then they got to come up with like a clever way to do it or a clever trick or apply another trick or something, right? um so these books, this is an old habit of mine now, probably a decade old. I
Um,
bought a case of these, so I have like 100 of them, and I write shit down all the time because that's how I do math,
mhm.
right? I have dozens of these just filled with me thinking about random shit and doing stuff wrong and doing stuff right and doing other stuff. I'm just writing math stuff all the time, doing a random proof, just to make it nice or something. Um,
Sure.
so for my PhD, which obviously took a long time of just reading lots of papers and trying to figure out what it is I wanted to know, or what it is that's true, or what it is that isn't known, or whatnot. Um, that just takes an enormous amount of time. I read a
Yeah.
100 plus papers. I read a dozen books. Um, I think one big goal for me was there were things I would ask a question to myself like, how do we know about this thing? And then I would spend so much time trying to figure out how we know about it. And maybe we did know
Okay.
a lot about it, right? And then I would ask a follow-up question myself, well, how do we know about that particular case? And then that would lead down
Yeah,
the rabbit
a lot of
hole,
wisdom.
right? And eventually I
Mhm.
found the end points of a couple of things that weren't known, right? And so I was able to extend those. And so I had a dissertation with a bunch of new math in it, right? Yeah.
Okay, that makes sense. I think that's where I'm at. Yeah, I think I'm kind of doing that kind of thing. So
Yeah,
now we're
there-
probably not at that level of rigor, but that's our
Yeah,
part.
I mean, I don't know what it's like for physics, but in math, it's
Mostly the same.
it's probably quite a bit more cleaner with math because not knowing something is simply no one else knew that that formula existed or whatever, right? So, like for example,
Okay.
I found a new formula for the coefficients of any differential equation that has Hermite polynomials as
It's
eigenvectors,
impressive.
right?
Yeah.
And I actually hang on. I don't know if I should be revealing this on stream, but I got some business cards.
If you don't want to, then yeah, it's not a problem.
Yeah, that's fine.
Okay.
It doesn't really matter, you know. It's only going to be like a few more weeks of my anonymity till it's gone anyway. Okay, so I made some business cards for the stream. So let me see if I can.
Oh, sick.
But anyway, so this is one of the formulas. So I proved a dozen.
A little bit
things
blurry,
in
but yeah.
Yeah, it's a little blurry. My bad. But you know,
Whatever. I get the point.
Here, I'll write it down. Yeah. So
Yeah, I understand. You did your research, so you gotta show off.
yeah, you know. So
I
n
understand.
factorial 2 to the n.
I'm curious.
K as it goes from 0 to n of n choose k. Gamma k I to the n minus k. H n minus k of x. Sorry. There's an I in there. I times x. Is there an I in there? HK of x. So anyway, I had these business cards made up because I'm like, hey, I'm going to they didn't come out as great as I wanted them to be, but they're pretty good. They're pretty good. I like them.
Yeah.
They're fine. And so I'm going on the I'm going to Vegas, and I'm like, well, you know, I need to have some business cards so I can just pass them out randomly to people. Be like, hey, watch my stream, you know, donate, right? And so I was thinking about what to put on there, and I was like, I should put down one of the formulas I found. So like this is my formula. I found this, right? So this is the formula.
This for
So if you give me an arbitrary differential equation that looks like this, right? D to the n. So here's an arbitrary differential equation. So that represents every
Sure.
possible differential equation. And that differential equation has eigenvectors, k, sorry, because I used n in there. And its eigenvalues are gamma k. Then,
well, that looks higher order.
yeah, so this is the differential equation. It has Hermite polynomials as eigenvectors. It has some eigenvalues, arbitrary. Then the coefficients of the differential equation are this formula. Right?
Oh,
Yeah, you can calculate them explicitly. Yeah.
but based on our previous conversation, if you want to have an argument here, I'll probably lose it. I thought that you mentioned that I'll try my hardest. That higher order than 2 differential equations don't have any explicit eigenvalue solutions.
No.
Using
the
okay,
the base differential equation for the basis is order 2, meaning that this differential equation must be a composition of that order 2 differential equation, right? So it is, in some sense, I'm calling it arbitrary, but it isn't arbitrary. It has to be order 2, order 4, order 6, or infinite. I mean, you can make it infinitely large, right? But it has
So
to
what
be.
if it
Yeah,
the
it has
solution would then be if it's order 6, it would have to be order 4? Is it like a difference between the orders? I'm not, but that doesn't make sense, does it, when I look at that?
order 6, order 4. I'm not sure what you
It doesn't
mean.
make sense when it comes to the solutions. Yeah, I'm not sure what I mean myself.
Mhm.
Sorry,
Yeah.
say again. I mean,
So the smallest differential equation that has the Hermite polynomials as eigenvectors is an order 2 differential equation. And that means that any differential equation involving the Hermite polynomials is going to be a composition of that order 2 differential equation. And so while I may be able to say, give me an arbitrary differential equation that satisfies this, there's only a selective class that does, right? And is there a formula that would calculate out that selective class? Yes, here's the formula, right?
compositions. Can you give an example of a composition?
Of an order
Are you
2
gonna do that?
differential equation? Sure.
Yeah, to go to order.
I mean, I could do
6.
something trivial like d squared
Yeah,
times
something
d
trivial.
squared is d to the 4th, right?
Gotcha. Okay, that's what I
But-
thought.
But
Yeah.
if I do like d squared 2xd, right, and then I square that, it's not going to be immediately
And it would be.
obvious, but it's going to be like d to the 4th
I think
and
you're
then some other
d
terms.
squared times. Okay.
Right.
Yeah.
Yeah.
Yep.
Yeah. So let me put it this way: this will never have an odd order because it has an orthogonal basis as its eigenvectors. So this could never be an odd
Uh-huh.
order, right?
That makes sense. So this might be a little bit interesting. I would have to think of an example of this, but in quantum field theory, we oftentimes deal with imaginary order differential operators, which is a little bit weird.
Mm-hmm.
Yeah, so it's a little bit strange. So you're dealing with sort of like this imaginary dimension in your differential equation, which might be a little bit the same. I wonder if there's if you can actually build an odd order.
Do you mean
differential equation
like
from
to the I, or do you mean like ID? Because ID is, so there's
I may be mistaken. It might be fractional.
like 1 over D.
Yeah, I have to double check. I have to run down to my computer and actually double check that because it was either imaginary or fractional, but it was definitely something weird along those lines.
ID is effectively is basically equivalent to a Fourier transform. A Fourier transform with an x, an additional x in it. So the rigorous way to write that out is like if I go to do a Fourier transform and I have x times f of x, right, and then you got the stuff over here, whatever it is. What is it exactly? I times xy dx.
That's not what I'm talking about. I know what you're doing. But go on while I look up what I'm trying to find.
Yeah, so this turns into an imaginary derivative, and then it becomes the Fourier transform again. And I'm probably off by a negative or something, so I'm going to put a little roughly equals, so don't,
Sorry, it's loading for a second. Did you add that as a coefficient or as the order of the derivative?
The coefficient. What? I'm sorry. What?
Like a coefficient, like I don't know.
This.
Sorry, it's loading on my computer, so it's kind of a little bit weird. I can't see exactly what you're writing.
Oh, gotcha. All right.
Can you just say it again? Like exactly, are you doing like I times D or something? Like I times f
Yes,
of x
yeah.
times D.
So if you do a Fourier transform and your kernel is getting multiplied by x, that's equivalent to doing like I times the derivative of the Fourier transform. So you get an imaginary component showing up there. Right?
That makes sense. Yeah. Yeah.
Yeah. And so this becomes polynomial like, meaning that you can put, a polynomial here and it's equivalent to doing a polynomial of ID. So there's an imaginary value that shows up in the polynomial. So like any polynomial can multiply by a kernel, and it's the same as doing a derivative with a polynomial derivative, right? So ID kind of has a meaning. It basically means like multiply the kernel of your Fourier transform by x. So it's in a non-trivial meaning, right? Some of these other ones, the meaning becomes quite a bit more difficult. The other meaning that is well known is e to the d. I don't know if you know what e to the d is. So you can put any arbitrary
You'd have
value
to solve
there.
it with a Taylor transformation, right?
Yes, you can, right? But it has a known simplification that's very, very cool. It's
very difficult when you exponentiate operators. It happens very often in quantum mechanics, but it's obviously not the easiest concept to understand. I still don't understand it. I just do it.
Yes.
But,
well, so the point is that the operator has a weird symbology, and the actual application of it is weird because it would be effectively Taylor series and then blah blah blah. But the point is what does it actually do? It takes a function and it shifts it, right?
Right.
And so we have a name for the shift. If you want to shift a function, it's the exponential differential operator, right?
Right. Yeah, it looks like like a Taylor series.
Yeah.
Or Maclaurin series rather.
Yeah.
Centered at alpha.
Yes, correct. Yep, that's exactly what. Yeah, exactly, and that's why it is the shift operator. Right.
Okay, so I think I got confused here. Again, I'm going to actually do a little bit of read through on some of these sections on renormalization in some of my books here. But I think I might have gotten confused with the dimensionality that the operator is acting on rather than the actual order of the operator.
Yes. So there's a difference between the dimension and the order of the operator. So there's also a difference between functionals versus operators, right? So a functional is an object, we'll call it capital F, that takes functions and maps them to a real number, whereas an operator takes a function and turns it into some other function, right? And so functionals, those are what are used to define dimensionality, because if you give me any operator, then I can, if I have a if I have any operator that is a linear combination of functionals, that's going to be explicitly related to the derivative, the dimension, because if they're independent of each other, that's going to be the amount of dimension you get on the other side, right? But differential operators, they are automatically infinite dimensional, right? And it's because assuming that they're non-trivial, and and I should be clear. Okay, hang on. A finite differential operator is automatically finite differential. So finite means finite order. So I have to put order in here. A finite order differential operator is automatically infinite dimensional. And that sort of makes sense, because just take like the standard basis, right? If you give me a differential operator, the standard basis increases in degree forever. The operator's fixed. you're going to get every possible exponent that you can get in your polynomials. And so the input dimension is all the basis elements. The output dimension will be all the basis elements, right? And so the input and the output are both infinite dimensional and all possible polynomials. So as long as you have a finite differential operator, it's guaranteed to be infinite dimensional because it maps to everything, right?
Yeah, it makes sense.
But functionals don't map to everything, right? Whatever linear combination they use is what you map to. So like I can make an operator that takes a function and sends it to f of 0 times x plus f of 1. See, these are functionals, and I did a linear combination of them. So this becomes a linear operator, and it's a linear operator that's a combination of functionals, right? But the output dimension is only dimension 2. It'll only ever output a linear equation. So no matter what I put in here, I only get a linear equation out of it. And so the output dimension is dimension 2, right? And so this operator can't be represented as a differential operator, or it's not going to be a differential operator. It's a
Makes sense. Seems almost encoded in the name differential, right?
Sorry, I got to keep correcting myself.
It seems almost coded in the name.
This is not a finite order differential operator. It can't be, right? Because all the finite order ones are infinitely dimensional. Because this one is finite dimensional, this cannot be a finite order differential operator. So if it is a linear operator, it necessarily must be an infinite order one, right? Yeah.
Oof. No, I think I lost myself there.
Yeah. Yeah, if you attempted to write this out, with derivatives so that it always output a linear equation, it would automatically have to be an infinite order differential operator. It would have to be.
I'm lost, but that's okay. I mean, I'm in class now, apparently. Back to class again.
Oh, no worries.
Okay, sorry, I've been gone for like the past 30 minutes discussing that financial issue I'm having, Bobby.
Oh.
So, yeah.
Was it able to get resolved?
Well, so, okay, I hope you don't mind me going on a little like rant, if that's cool. Like 2 minutes, 2 minutes. Yeah, so like, okay, basically the issue is the issue is that, you know, I was planning to take out private loans to cover the remaining balance for my tuition, and my grandparents were like, "Oh yeah, sure, we'll help out," but you know they've had some difficult credit with the past few years because my grandpa had some health issues. But anyway, the point is that they couldn't do it. Their cosign thing got denied, but apparently. And you know, I'm like trying to ask my mom, but my mom unfortunately doesn't seem too keen on helping me out. They think, oh, you know, you're just some like you're just going through a stage of liking math. You didn't like math in high school, so therefore, you know, you can't possibly be like it. They think it's like some kind of like prank or something. I don't know.
Do you mind if I interrupt with what you're saying?
Yeah. Go ahead.
You know, I think I don't like that. I mean, I'm not saying your parents are wrong, right? I mean, I guess I'm not insulting your parents in any way. But I mean, when I was in high school, I had a 1.6 GPA. I didn't do anything. I really at all. I had no interest in this stuff. So I'm kind of in the same position that you're in right now. What really helped me, as a matter of fact, was, you know, going to community college. Doesn't really cost anything. You can get a very good education for your first 2 years.
So yeah, I'm core complete. I took college classes in high school. And what's it called? Yeah, I'm core complete now. I don't have to do any core classes. As a matter of fact, at my university, I could get away this one semester with just taking 1 second. Hold on 1 second. sorry, the cat went into the garage, so I had to take him out. Anyway, so I could totally get away this semester with just taking calculus, but in order to qualify for like help with housing, FAFSA things, like I had to be full time. So I took like philosophy of religion, my language credit, and what's it called? And yeah, philosophy of religion and my language. So had to be full time. And the reason I want to be at a university is so that I can just like truly focus on the whole plan was get the loans, you know, just truly focus on doing math, being in my little cave, and, you know, not having to deal with, because there's a lot of issues here at home. And that's what my grandma was advocating. She's like, no, just go to university, get away from the town. You need to be able to study. I'll help you out. And I was like, oh, cool, you know, good plan. And then the loans got denied. So anyway, I was talking to my grandma about that, and she was like, well, you know, I have a little nest egg I might be able to take out of. And she's like, I don't know, I'll go tomorrow and see. So talking about that, I'm trying to convince my mom to potentially co-sign as well for the private loans. And
Do you explicitly need private loans? Have you done FAFSA stuff?
yes, unfortunately I do. At least for this semester. The main thing is I just need the housing, and I would totally be fine commuting, even if it was like 2 hours a day, because I'm not taking many classes, and the Spanish one is completely online, and well, I'm fluent in Spanish.
Sí, entiendo eso.
Yeah, and what's it called? So the point is, I wouldn't mind commuting, but the problem is the university is 8 hours away, and it's still in the same state because I'm in Texas, and Texas is freaking huge.
Yeah, it's a bit of a trip.
Yep. So, I mean, I could even get away with, you know, skipping calculus one, because I mean, I know calculus one like the back of my hand, but like still, I want to have that good relationship with the professor so that next semester he could be like, oh, I recommend the student for tutoring in the math center, and then, you know, then I can get some money and I can help and other math students, and then, you know, that could be a good source of income, and I could get like scholarships or something next semester. But I don't know, it's just so freaking stressful. And thank you guys for listening. Like, I know I've been yapping way too long, but
I've been there.
Yeah.
I've definitely been there.
If you have the means of taking community college, I of course recommend that as well. I did multiple years of community college before I went to get my bachelor's degree.
Saved me a lot of money.
It did save a lot of money because community college is effectively free or near free. I mean, it's not perfect.
It really is, and it's the same education.
All the same books.
I actually liked it a little bit more.
Yeah.
So, of course, yeah, like worst case scenario, I'm just going to continue going to the community college near me, and I'm just going to be like, yeah, like just going to be in my books this whole year, because it's not like I'm taking many classes anyway. So the only thing I'm worried about is my grandma already signed the lease for my apartment. Like I was like, oh yeah, go ahead, sign it. Like, so I don't know if I can cancel that. That might be a separate issue, but yeah, I don't know.
Do you have half your credits done?
Yeah.
You said you have a lot of credits, so you would need to do 2 years, or would you need to do more?
Yeah, I'm core complete, so I would just need like two years. Yeah, pretty much 3 years. 3 years max.
Oh, that's good.
Yeah. So okay, the bachelor's in Texas, I don't know how it is in y'all states, but it's 120 hours, and core is 44 hours, and I already have my 44 hours mixed from me in high school and, you know, me doing some community college classes last semester. So I just need like, what, is that 76 hours or something?
Yeah. Is Ted Kensick a good mathematician? I don't know. Maybe. In-state tuition. Less than, but value-wise greater than. Gotcha. What's the big deal in mathematics these days? I don't know, man. We got
Riemann zeta function.
The Riemann zeta function. Oh, geez. I'm sorry. Unkno is raising their hand. Let me give Unko a chance. Sorry.
Hello.
Hey, how's it going? My bad.
Hey, how you guys doing?
I guess Jetstream also wants to come up and speak. Okay. We'll just put everyone up on stage.
Were you guys having a debate earlier?
Unkno? Am I saying your name correctly? I don't know.
Yeah, you're good.
Yeah. I mean, I guess you're newer. Everyone else has been here a million times, so if you
Yeah, I
wanted
just
to,
joined.
if you wanted to ask something, feel free to. Yeah.
Yeah, I was curious. I was wanting your guys' input. I know you're a mathematician.
I am. Yeah.
And I have a few friends who are quants, and I was just wondering your input on a few things. They specialize in like commodities and energy, and they're quite like, I would say like down, like they're pretty close to like the frontier AI models. Like they kind of understand a lot of
Okay.
like, how the models are performing and like what's like new and shit. And I'm just like, I'm currently in college, right? But I think that the scaling laws of AI, I mean, it's just like more compute and like whatever. But I do think there's gonna be a point near the end of 2026 of like, it's kind of gotta be clear that like there's like skepticism with like AI is gonna take your jobs, but I think that's not true. But I think there's gonna be such an abundance of like intelligence that they're like college degrees won't really mean it won't really be substantial. And I know it's kind of like radical to say something like that, but I just I mean, it's just like this year alone the models have like 20-30x, and then there's also a lot of news about cybersecurity and shit like this. So I'm just curious what you guys think about scaling laws of AI.
It depends on what you mean by 20 or 30x. I've gotten in multiple fights with Grok or ChatGPT or Gemini, because they regularly say things that are false, or they don't know how to do this, or they miss a negative when they're trying to write up a function for me in a formula or whatever, or write a program. They write a program incorrectly. So like maybe they'll get better. Maybe they'll eventually be better than humans at some point. I don't know. But the idea that there won't be any human intervention, I don't think so. We see some of the data coming in. There are a lot of companies that have participated in things like trying to get rid of all their staff and do everything with just AI or whatever. Like AI does all their scheduling or something. And some of them have lost, 10, 20% of their business because of things like that. Not because people were protesting, but because the AI just did a shitty job, right? And so, in general, I don't know exactly what the future is going to hold with AI, but human beings are clearly always going to have a place, right? Whether the AI is there as a convenience for us or as a big calculator to simplify a lot of the things that we need to do that are mundane, um, the humans are still going to be there at some point, right? I mean, it's hard to imagine that the humans are going to disappear. There's, so much more new things to figure out. There's more robotics and more calculations and more stuff to do, So, I don't know. Like, I don't see it. I don't see that ending anytime soon. I don't see I don't see human jobs ending anytime soon.
I do agree with you, like how like these models they still hallucinate, and you probably still need like you still need to be like, hey, like that's not correct. And like for the more like it needs a human like supervisor. And I feel like when there's a lot of pushback on like the dangers of AI, because there's been a few cases that like with ChatGPT, and it's I think it was pretty blatant that like the chat model literally hacked Hugging Face's servers, and then they Hugging Face, you know, like some shit happened, like some security breach. So obviously AI needs a supervisor, but I feel like the actual economic incentive for companies to kind of lay off their employees is going to be disproportionately higher than actually having an employee and paying them $40,000 a month. Because if you're paying $2,000 a month with, I guess, credits or tokens, then as a business, your kind of incentive is to, you know, make the best decisions possible. But I just think it's got to be like kind of
Yeah. So
like a bad decision just economically.
yeah, so businesses operate on the you know, their they operate on the local level to themselves, right? Meaning that they operate in their own best interest. So like the objective of a business is to make as much money as possible. So they're going to make decisions that make them as much money as possible, right? The job of society, and in particular our government, is to ensure that there are rules and regulations in place such that the outcome, you know, the best outcome for humans is what is put forward when people attempt to, you know, operate these businesses, right? So, like, I have no problem with businesses, you know, doing what they want to make as much money as possible. I think the onus is on the government to ensure that there's proper regulations so that that desire that they're after is as beneficial to humans as possible, right? So, like for example, we're talking about like corporations cutting, you know, jobs or whatever. Um, I that should probably just be flat out illegal. Like plenty of other countries have already done that, right? It's weird that America hasn't, and I don't know why that's the case. I think that it's just kind of strange. And so the general rule would be, right, if your corporation is making money, you can't fire people. Like, and that just seems like boneheadedly obvious that that should be a regulation, but for some reason we don't have that in the U.S. There are plenty of other countries where that is the case. Like your company made money last year, okay, you can't fire the people that made you the money. Like that's just ridiculous, right? But yeah, in the United States we don't have that, right? You know. But yeah. Oh, sorry.
Oh, you're good. I was just gonna say, like with like regulations, you were talking about that earlier. Honestly, I do think that the whole regulation system is like kind of like ancient in the sense of like it takes like a lot of time. But with these models, it kind of doesn't really act on those, you know, paces. It's kind of non-linear, which is obvious, like what we're seeing. But there are things that we don't know, and I think you need to have some like you know, just
so,
like
so there are things that may need to change, right? So in general, we should all be against things that are particularly bad for the market and for people. So things like fraud and you know, price fixing and whatever, right? But in the stock market, that also comes into play. There are plenty of rules that are just, you know, not okay, right? Because it doesn't, you know, it puts people in an unfair advantage, or I mean, it puts detriments in the market in weird ways that shouldn't be there, right? There's a whole reason why, like like if you start a corporation, right? There's a reason why it's illegal for you to just open up a corp and walk around and be like, buy my stock, it's the best stock ever, and just walk around town trying to sell it to people. That's illegal, right? You can't do that. There's reasons why we don't allow that, because we're not supposed to be allowing fraud, right? Some of this has gotten away from us, obviously, because crypto is a clear example where lots of people have lost money, and it's because it's a thing that has no dividends or returns or anything along those lines, and it's and it's rife with fraud, right? So there may be things that need to get changed, right? Especially when AI is put to the measure and its outcomes are hey, here's all these micro manipulations I can do that basically achieve the same thing as fraud, right? Um, and so then we're like, oh, well, you know, how do we deal with that, right? Because the AI is just going to get better and better and faster at doing those things. Um, so yeah, it's certainly a non-trivial question, but as long as people stay in charge, right, we can always regulate and change things such that it's as beneficial to people as possible. Like, I'm all for the businesses that are incredibly greedy and take up everything, right? Like, put Walmart in the middle of town. Awesome, great. They should be paying so much goddamn tax that all of our schools are funded and our roads are paved and everyone has, a little bit in their pocket and they can enjoy their vacations and whatnot, right? Like that would be fine. Like, imagine you were shopping at Walmart and you were like, wow, I love shopping here because it pays for all the schools that my kids go to. That'd be a great thing, right? But we don't have that. Instead, we have, greedy ass corporations trying to get subsidized so that they don't fuck over people, and then literally paying their people so little money, these people then have to apply for food stamps, and then they're told while they're working
Yeah.
2 jobs and 60 hours a week that they're the lazy pieces of shit that need to not be in the United States. Like, I'm sorry, this is just like a ridiculous joke. Like, people come first, corporations come second. Like, I don't give a fuck about corporations, right? I care about people more, right?
That's
Yeah.
true. Yeah, I mean, like, but like the
Yeah.
incentive, like
Yeah.
the incentive with like like taxing all these corporations is like kind of like,
Yep.
I think it kind of like distorts the idea of like, hey, let me take a risk, and I feel
Mhm.
like there's a heavy like
Sure.
penalty for being taxed like that, but there should be like obvious
What
like
penalty?
certain thresholds to like more taxes, or like more like
We're-
if you pass a certain like EBITDA, then you probably get more taxed or something like that.
We're-
But
we're like-
I do think with your point with
Yeah,
with like
but we're
low
like
pay,
the lowest tax country in the world. Like, we're literally dealing with like Middle East stuff right now, right? Like, go look up the taxes of oil companies. Like, 60% of all of their profits go straight to the government. That's why their people have frickin' every single person has food or housing, right? Like, it's the idea that like corporations in the United States are taxed too much. This is just silly, right? Before Reagan, it was 70%. And before that, I forget who it was 90%. It was like 90% corporate tax rate for like whatever it was, 40 years, 30 years in the United States. And then Reagan, and then it got lowered to 70%, and then Reagan was the one who cut it in half. And then Trump cut it in half again, and that's why we're at like 19%. It's fucking ridiculous.
do you not like Trump or something?
Do I not like Trump?
That's fine.
Yeah,
Then.
no, I don't like
That's
Trump.
good. That's all right. Yeah. Just
Do you, sorry to interrupt.
Sure.
Correct me if I'm wrong in assuming how I'm able to add here. Because normally I would just listen, but this is actually the field that I think maybe I can offer some stuff here, but maybe not
Sure.
from the perspective you're talking along.
Right.
So at least with what you're talking about, Cheers, the perspective that I maybe can lend as well is one from a psychology background. I currently actually work with a corporation and am personally invested in trying to get time with the CEO to actually discuss this, I think, broader idea that you're touching on. And a lot of it stems, I think, from also like systemically how people work. So at least from my observational data and also what I understand about how like people function, like you're talking about this idea of risk. People have driving mechanisms in terms of what their behaviors are, and not all of them realize what they are. The really obvious one is like this fear of losing your job, right? And so when it comes to the information that maybe is presented to a CEO in terms of the decisions they're making with regards to AI and what the initial information was, in a similar vein to sort of crypto initially, right? In terms of how it's presented versus functionally what's actually going to happen. There is this fear, what if I invest too late? What if I'm behind the curve when it comes to this new technology that everybody is saying is the way of the future. And
Yeah.
you guys probably know of the obvious, you know, economic situation of like the major 7 corporations and the one
Oh,
point
yeah.
something
Sh-
trillion
sh-
dollars.
Yeah,
Yeah,
definitely.
right. We're all on that
Definitely overinflated.
page with
Yeah.
like, hey, the numbers don't add up and they're on
Yes.
borrowed time.
Yes.
Sure.
But in terms of, you know, even outside of all the ethical concerns you may even have with like how we produce AI, there's like another layer on top of that, which I have not encountered anybody so far in discussions amongst the space that I'm working in right now for their consideration, which is not even just the automation aspect of jobs, but it's also ties into the cognitive de-skilling, misskilling, and unskilling. So at least there's 3 categories of cognitive impairment that comes as a result of AI now, and like maybe future research will like simplify or unify or even show us that there's even more ways in which interacting with these LLMs sort of like influence how our brains work. But it's also not that they're influenced in the time that we're using them, but it extends beyond that. And so even trying to have a conversation with the CEO to say, hey, for the workforce that does stick around that you don't automate out, what is your plan for their long-term professional skill development so that your company can have employees 10 years from now that are able to do even more than they already can? And that's not even on their radar, right? So even if we keep everybody's jobs, there's going to be a growing divide in terms of cognitive skill between those who, whether by choice or by virtue of their work, are forced to interact with AI. And unfortunately, the long-term effects that we know so far are going to be happening cognitively, and then those who are able to resist it. And so like that's, I think, another layer to sort of understanding, well, how do I go to a CEO of a corporation and talk to them about this? And the short answer is I go, hey, do you want to be a business that like exists in 10 years? Because financially you won't be if you've moved your whole organizational structure to using AI, then it suddenly costs more and you don't have employees who can shift you back.
Sure, sure.
I have
But-
a question for you, Funk. Oh, sorry.
Oh, I was just going to say, but at the end of the day, let's suppose that doomsday is not the case. That as they automate more AI, their base becomes more valuable, and they just gain more and more, right? And then you have more businesses
100%,
that,
yeah.
like we literally have all these grocery stores that are all completely automated, and they're all competing for the lowest price, and now prices are literally on the order of the cost to grow them. So you have tomatoes, going for like a penny each because it costs nothing, and the corporations are making so much money, right? Like I don't understand why that wouldn't be a perfectly fine world. You just tax them at 90%, like, and like there's
well, also true.
And that would be
I
great.
also fully
right?
agree
Like,
with you.
I would be happy with that. I have no
political
problem
implications of what you're talking about, though, I think exist outside of capitalism. Is the short answer. But even if there is a way to set it up within, I think also what you're touching on anyway is, like we're talking generally, like then we're talking more in the realm of like universal basic income, for example.
Yeah. So what?
And then also like you mentioned, sorry, go on.
Well, what I'm alluding to, or just to be clear, right, is the regulation should be in place to promote capitalism. If, for example, AI is being used to like suppress all the competition, that's like anti-capitalistic stuff, right? So we would want regulations in place, laws in place, regulations in place, and sufficient taxes so that there is the competition that we expect should be there, because competition and capitalism are benefits to us. And so we want to promote those things. And so we don't want there to be, everyone using AI to try to destroy each other's company. We want AI being used so that like no one has to work,
Yeah. Hey, Funky. I have a question.
Yeah.
So you study psychology, correct?
Have done, yeah. Not the field that I'm actually studying right now, but sure.
Okay. So I was just curious. Do you guys like look at like kind of like the kind of like behavioral, like ancient type like things of like why we act a certain way, or like is it more or less like restricted to like, you know, like loss aversion, or do you guys talk about like how if everyone's more loss adverse? Because if you were, you know, if you like lose your like fruits, for example, like kind of like 99.9% of like all humanity's like life, like if you like lost a fruit, like you would be more
Yeah,
at
you
risk.
die.
Yeah, exactly. Okay. So
Yeah,
like,
yeah,
do you
yeah.
guys,
So
do you guys
mm.
oh, nice, that's cool. Okay.
Well, so that's the framework that I am trying to, I guess, especially when talking with, you know, people outside of this field. I think it's very helpful to understand sort of like driving forces behind behavior, especially within people. Like I think it's hard to know all the ways in which you act and behave without knowing biases, right? So my first like exposure to this was in the different kinds of biases and developing ideas on biases within humans. So it's like you've got confirmation bias, in-group bias, large group bias, and like you're saying, like evolutionary psychology is sort of a means through which some people try and situate explanations for the development of these cognitive shortcuts in a survival Darwinistic like framework, right? And then importantly, like understanding that within a modern society is like I think the most useful thing. It's like whether the explanation for why it's there is right or not, understanding then like, okay, why is it that we fear social death? And how is it that those things influence our behavior? But what you're touching on as well, I think, in terms of, and maybe this ties a little bit more into what you were saying, axiomatic as well, like whether we stick within a capitalist framework or whether we suggest, hey, there's another proposition in terms of like how we could structure government and society to resolve this issue, like the fundamental issue, I think, that will face humanity regardless of how we sort of resolve AI's integration into society is still actually always going to boil down to, so far there doesn't seem to be a safe way for people to interact with it without it making our brains worse. And the only snippet of evidence I've seen so far in the continuing like field is with regards to sort of guardrailed AI in education, where it seems to perform as well as people not having AI at all, which is in terms of learning outcomes. And that really calls into question then, well, what's the point of it there then if it's as good as no AI? So there's some very cool like narrow lens applications for LLMs in like, and you guys probably know more about this than I in terms of, you know, connecting very distant fields of mathematics for things that would seemingly be unrelated to certain conjectures and then being able to show and connect those ideas. It's like the breadth of knowledge that an LLM can sort of hold and connect ideas between is greater than an individual human. But like you've also mentioned, axiomatic, like it takes a human on the end to actually vet that. And that was my experience in, I used to work in sports science, and it just can't put ideas together with like a degree of like reliability.
Yeah, on the research level, it's a lot more than just interpreting. It's you have to be actively involved in the entire research process, like telling it what to do, then telling it the next thing to do, then telling it the next thing to do, then telling it the next thing to resolve, and then telling it did the first thing wrong and to redo it. You know, like so like it's not like a trivial thing where you're like, oh, let's just see if it'll figure out, you know, the
sorry, I worded that badly. Yes.
Yeah, no worries. It's the question is, how far has AI come so far, right? And the reality is, so far AI has achieved the level of finding trivial examples that no one had written the program yet to go look for, right? And so that's what we see some of these coming out, and they sound like splashy headlines, right? But it's like found counterexample to thing that would have been found in 5 seconds if someone had known to write up a program to go looking for that counterexample, right? And so that's currently where we're kind of at the status of AI. There are much more complicated examples that I think are more interesting that involve like really clever and complicated sequences of steps done by researchers in conjunction with the AI to get it to do a thing that then gives them insight into a problem but doesn't necessarily solve it, right? And so that I think is more of interesting examples than like the AI solved a thing on its own. But anyway, the point is, how far is AI going to go? And I honestly don't know. I don't feel it can go much farther, right? I mean, you can only double so many times, and we're already at, $100 billion or whatever. How much are we fucking spending on this shit now?
No, sorry to intervene with that. The models for January 2026, the largest model was around 4 billion parameters, and you kind of think of like intelligence with parameters. And
Sure.
Currently, we're at a model of I think it's Kimi K3 with 2.4 trillion parameters. So that's nearly like
That's
a big number increase. And
that's
with,
tenfold, right? Or that's 10.
More.
That's 10 doublings, right? Because
yeah,
because a billion
two,
a billion to a trillion is multiplied by 2 to the 10, so that's 10 doublings, right? So
yeah,
they had, yeah, so in other words, you had some amount of resources, and then they doubled it, and then they doubled it, and then they doubled it, and then they doubled it,
Yeah.
and they did that 10 times, right? And
Yeah.
that's huge, right? That's huge. But how, like, do you think you could do another 10? Like, we're gonna go to a trillion. What is the next one? A zillion? We're gonna go to a zillion? Like,
I mean, in theory, it
maybe.
is possible. It's just a function of compute and energy. And China has
Sure. But if you're building,
but
let me put it to you this way: if you're building data centers on the size of 5 football fields, how much space and money would it take to double that 10 more times, right? Because you're talking on like trying to build a data center half the size of Montana or something. That's never going to happen. Like
that's pretty big.
yeah, there's a physical limit here, right? Like there's you can only double so many times before, like, we don't even have the silicon available to even attempt that. We barely even have the silicon right now. Who are the two companies that just announced that they're dropping their data center contracts and now they're trying to offload them? Well, because like they're trying to build them, but they're not finished, so now they're trying to sell them to other people. Because they don't.
Probably ran out of money.
Yeah, they ran out of money,
And
or
ran out of
they
capital.
realized they're never gonna fill those data centers with the chips. Like that's never gonna happen. Like there's not enough.
Yeah,
Unless they go build them
I mean,
themselves,
there's a lot of supply chain, shit shows. So, but
Yeah.
I think it's just it's like the incentive. I mean, also the whole AI infrastructure got really tanked I think a week ago. It was kind of obviously overvalued. People were just overhyping it, but I think it's kind of slower, like
Yeah.
infrastructure wise. But
Well, it's still insanely overhyped. All the PE ratios are, the entire market feels like a big gambling session. And what was it? Was it
Yes.
Korea? Korea just had that massive crash. They've
It was
literally, I thought it was South Korea just had a massive crash. They were posting memes of, trading in Korea is equivalent to gambling, right?
Yeah, it's like people are just more or less looking at the macroeconomics of the situation, not really, the actual
Sure.
statistics. But
But
I mean, that's just
where's the money going to be made? So this is something I tried to have someone brainstorm with me, right? I was like, look,
cool. Let's do it.
what's the value of the auto industry right now? So just like take the United States for example. What's
Okay.
the entire value of the auto industry? Like, I don't know.
So-
It's we Google it. It's, let's say, $5 billion or something. So it's a $5 billion a year annual thing, right? And we all experience that because we're all a part of it. We all have $10,000, $20,000, $50,000 invested in auto stuff, right? And so we kind of have an idea of like how much each of us is invested in it, and how valuable it is to the United States, right? Well, when you have AI saying, "Oh, this is $1 trillion industry," right? Um, I look at that and I go, how much do you think each person in the United States is willing to sacrifice their salary towards AI, right? Because when you say
Way
that
longer.
when you say just put it in terms of a factor. When you say AI is 50 times more valuable than the entire auto industry, you're making a claim that every family or every person is willing to spend $100,000 or $250,000 on AI. And I don't ever see that even being remotely possible. Like, I don't ever see anyone going above and beyond a $10 a month subscription. Like, are you like, try to convince someone you need to spend $500 a month? I don't, I can't ever imagine that in the slightest. Like,
For a
do you
consumer,
imagine?
no.
Yeah, across, you need it to be across the United States to reach, $1 trillion valuation, right? You need every single person to say, yo, I need to be spending $1,000 a month on AI in order for me to stay a competitive person in the market. And you need everyone across the United States to make that exact same commitment. Then it will be $1 trillion business. I agree. But like, I don't see that happening, right?
I told
Yeah,
my mom the other day I was spending like $20 a month for Claude, and she looked at me like I was crazy. Because most
Yeah,
people just don't know the value of AI. So I mean,
yeah.
Yeah.
But
yeah.
again,
I was gonna.
if Claude turned around tomorrow and said, "Yo, it's $1,000 a month," are you going to be like, "Oh, I
No.
need it"?
hell no.
Hell no. Yeah, hell
There's other
no.
models that will offer like
Yeah,
2019, so that will never
yeah,
be an issue.
yeah.
Um,
I know,
but
which means it will never be $1 trillion industry.
Yeah, I was gonna say that the
So,
problem with the model
I have
is
to
that
pass.
it
Yeah,
assumes that like what Barry was saying, like, oh, everyone would be down for AI, but
yeah.
that's just not realistic. And also, that's if everything goes perfectly fine. That's not even talking about the politics that happens or the events that happen in the future. So it's like you can't really rely on future outcomes made by AI. It's not realistic in a way.
there's and tell me if my audio quality is really bad. I can always come back later. There's a whole extra layer to that though that I think is missed out, which is we already have data that shows that people, the more they become informed about how AI works holistically, the less they want to use it. Right?
Mm-hmm.
It's the equivalent of understanding what smoking does to your lungs, basically.
Yeah, yeah.
So not only are we talking like, oh, if Claude suddenly goes to $1,000, or would you keep spending that? And you might be like, oh, I'd go find another cheaper version. But the second question is like, cool, if you spend 3 years using AI and you start to understand what that's going to do to you cognitively, would you even consider continuing to use it? And the research is going to become clearer and clearer that it is basically destroying your brain.
It is. I mean,
Yeah.
like there's like plenty of research papers you can look at, like MIT or Stanford, just some like two notable ones where like they found that the brain activity like with a task and then like autonomously on that task rather than like looking at like an LLM for a few weeks, they found like a significant decrease in cognitive
How are they
brain
measuring
activity.
that though? Because like
It's pretty clear.
there
What do you
there
mean?
are plenty of skills that have been dropped by humans over like decades, right? No one, I doubt anyone on this call could tell me how to do a square root, right? Now, how do you do a square root on a piece of paper? That was common knowledge in 1900, but then they invented the calculator, and now no one knows how to do that, right? And the same thing goes with a number of other skills that are just gone. No one memorizes phone numbers anymore. Gone. That's no longer a skill. Now, some people, if you try to measure that, like, oh, well, that was an important skill, so let's measure how well that preserved. Of course, you're going to get a stat that says, oh, well, the human brain went to shit because it can't do that skill anymore, right? And it's like, yeah, but is that skill important or needed? Like we seem to have done fine with the fact that no one knows how to do a square root manually, right?
What's your point?
I guess I'm not sure that it's necessarily the case that it's a bad thing that people start using AI as a calculator, or you know, find it useful and keep using it, and it removes some of the tasks that they need to do mentally, right? You know, I'm not sure that that's necessarily a bad thing, right? Because we've seen that happen many times, is what I'm saying.
Let me know again if you're really struggling to hear me. So I'm in a very bad space to talk about this. But very briefly, actually, I've had to have this argument with another professor before, and not really an argument, but sort of to explain an extra step, which I think the easiest analogy I found is this idea of when we introduce a calculator to a student in the first place, which is that there's a step before they get the calculator where there's a degree of understanding that they need of what addition or subtraction, multiplication, division are, right? And then we can add the tool on top of that. But the ideal is they maintain the system beneath, even if they're automating that process, because the system beneath is the thing that allows them to understand higher level things. And then the automation obviously gives them the speed through which they can do more complex things faster, right? What I would say from my understanding of literature so far is that the overall thing that AI is de-skilling is general intelligence. That is to say, critical thinking, our ability to do any degree of formal reasoning. And not only is it stopping us from developing it if we're younger, which is that the effect is far more pronounced in younger people, so 18 to 25 by far the most impacted. But beyond that as well is that it also de-skills people who've already developed that. So it's like you might be 40 years old, and instead of between the ages of 40 and 50, the trend that we would hope is that you not only maintain those critical thinking skills, but maybe they get developed even slightly further. But instead, the prediction from like current research is that that will actually go backwards.
But again, I'm asking, how are you measuring that? Like, you're calling it general intelligence. So general intelligence is going down. How are you measuring that? Right? Because if the way you're measuring it is, here are skills that people did before AI came about, and those skills are now being lacked because AI is now here, then I question whether or not that is in line with what you're like. I question whether or not that's actually a bad thing, right? Like
take a test.
Like if you're calling it general intelligence, that you're categorizing the thing that you're trying to show, right?
Yeah, like you're touching on, right? This is tied to the evolving research. So it's hard to say with a degree of certainty this early on. In terms of like the things that I've seen that make it seem that way across the evidence. So I think Arno was like talking about this in terms of recall. So we've had studies where basically we get people to write essays with or without the assistance of Google AI or by themselves. That the cognitive debt that comes from using AI persists beyond the initial task of using it, so that even if you then get them to write an essay later on without the assistance of AI, their capacity to recall is still significantly reduced by virtue of using it in the first place. And like significantly, like it's crazy how big the deficit is. And so like you're talking on, it's like 100%, it's a circular reasoning.
Yeah, that sounds
and so we're basically trying to measure, well, so this is how fluid intelligence works in the first place, right? It's like always we're trying to create measures by proxy. And so this ties more broadly into like the research on cognitive development in the first place. So you guys may or may not be aware of the recent literature that was coming out about Gen Z. They're the first generation to cognitively regress rather than go up in IQ. And that's basically tied, it seems, locally to the introduction of technology in schools, generally speaking. And the best explanation for that evidence I've seen so far.
Yeah, but maybe we're not measuring it correctly. Maybe we need to start measuring people with the assistance of the AI that they're trained on, right? Like I I hear what you're saying. It's just
Correct. Yeah, yeah, yeah.
I see prior examples of this same phenomenon. Here's an example with me personally,
100%.
right? And so this is anecdotal, right? But like one time, you know, I most of my life I have wrote literature on computers. So in general, you have available to you the ability to move sentences around instantaneously, the ability to have them error corrected, the ability to look things up on the fly, you know, the ability to click something and look up a thesaurus, right? And look for other words or whatnot. And that has been so naturally ingrained in my ability to write any email or any essay or any document or whatever it is that I need to do, right? And I didn't have AI. I'm just saying I had that type of technology available to me, right? One time I was in a situation where I had several hours and I needed to compose an essay, and the only thing available to me was a pen and a stack of papers, blank papers, right? I sweated my ass off trying to properly write an essay. How the fuck do you figure out all your sentences? How do you put them in the right spot? How do you like make a brainstorm bubble? I had no skills dedicated to that. That was an incredibly painful task to do, right? Was I a deficient person because I didn't have that skill? The skill set of being able to write an essay, organize it, and articulate it correctly, and being able to do it manually in such a fashion? I don't think so, right? I think that if you were to measure me on that particular aspect, I think it's that you're measuring me the wrong way, right? And I'm not sure it's a
100%,
detriment,
yeah.
right? I'm not sure it's a detriment if people are trained on particular outcomes. So we could imagine this the other way. You could imagine that someone is an artist, right? And they practice all this, you know, how to draw foots, how to draw faces, how to do all the stuff. And they're an amazing artist, right? And they have skills, right? And we measure those skills based on their ability of what they can do, right? But then you have another person that, for all intents and purposes, you might say has less skills than the first person, but they have trained themselves on their ability to interact with an AI model. And they give it something, and then it gives it to them shitty, and then they do a better prompt, and then it gives it to them a little better, and they play with this thing like it's a toy, and their artwork becomes so incredibly refined, well and above and beyond the first person, right? Yet, you put the two people in a room and you attempt to have them draw something, and the first person wins every single time, right? Do we say that person has become deficient? Or is it that they're within this particular environment and they've acquired new skills that the other person doesn't have? And those skills are how to interact with this massive calculator correctly, how to properly prompt it, how to get it to figure out what's in your head and properly put it on the screen, right? And that is in and of itself an
100%.
important skill, right? Yeah.
So I understand where you're coming from, and there are some things like everything I'm about to say. It's like there's only a certain degree of weight we can give the evidence for the time frame we've been able to look at things for, right?
Sure.
I guess the couple of extra things that I think are really concerning, at least from my perspective, that like are going to push back against this a little bit. So the first one is like the ease of, or the lack of friction that AI effectively introduces, and how this like connects more generally to sort of technology in the school place and what we see in terms of technology's influence on brain development. So there's a recent study that's just sort of come out looking at the development of white matter in 3 to 5 year olds, and basically the more screen time that they get, the less white matter that they have, which is obviously seriously concerning to understand that like the screen time has a direct influence upon like brain development before schooling even begins.
Well,
Another step as well, like that ties more broadly into what I was saying earlier about technology being introduced into the school environment. The then reduction in like overall cognitive like IQ in terms of how we're currently measuring it. And you're right to also then ask this extra question of like, does that mean that students are performing worse, or does that mean our test is like missing something that they're developing that we're not testing for? And so that's like an extra, I think, like meta question. But in terms of like the current idea behind sort of the regression that we saw is tied to the misequivocation of attention and learning. So basically technology was introduced, and rightfully so, people have realized that when people stop paying attention, they stop learning. But in order to reconcile that, then attention was made easier to give through how technology was used. And in doing so, reduce the overall friction. So like we know that the most amount of learning happens where there's high friction. So lectures in a university course actually result for the smallest amount of learning that a student does, because unfortunately there needs to be difficulty for us to have like qualitative learning occur. And so basically the extension from at least my assessment of the evidence so far is that like AI just goes another step beyond that. And a really good paper to look at is like the immediate amnesia that experts have with regards to AI output. So we've had like a study where experts will look at an AI summary on something that they're expert in, like you've encountered, you read it and you go, wow, this is a bunch of rubbish. It's saying things that aren't real, etc. And immediately you get those experts to look at something that the AI has produced that they're not expert in, and they immediately accept it. It like, this seems really great. It looks really good. And like that is, oh, that study I'd have to actually find.
Yeah, I'm just curious if it was like 2023 where the models were like really poo. And, with your point about
I'll look it up right now.
Yeah. And then just to touch on your point with like how like students like like they lower scores with technology, I think there's like a proxy where obviously if people have their devices, like if they're not getting enough like the sufficient sleep, and memory or like learning doesn't actually like and, like kind of process, because like if you learn like a lot of material and like for you or with your paper, and like you had to like rush to like finish that paper, and like that's like your hands like sweating and stuff like trying to finish an essay, right? Probably you wouldn't actually retain a lot of the information if you didn't get sufficient sleep, which is a direct correlation between students and like them waking at like 6 a.m. for the bus and stuff like that. And I do think that there's really like grounding principles to like just reason off, like just reason. Your brain is operating on ancient firmware in a modern society, and with these like kind of like relationships, your brain's rewarded for the conservation of energy. So if you're choosing to do a really cognitive task that requires a lot of mental resources, or scroll on my phone, you would rather scroll on your phone than rather to try to retain and learn the information. I think that's just like like just 101 like biology. But yeah,
just your point too, just a little bit of a side tangent. There's a lot of medication that's been developed in order to actually like sidestep that, which is quite interesting. Like ADHD medication in general is meant to deal with that particular problem, and we've been seeing more and more of the diagnosis over time. It's been pretty steadily linearly increasing since like the early 2000s. These diagnoses and prescriptions.
It is kind of sad, like people are becoming more like dependent on all of these medications. But I mean, if you kind of need it to like function and learn, probably a good decision. I mean, but it is sad that we're seeing this with schools, and the fact that like the whole like high school, for example, like you have to wake up very early, and it's kind of odd. Like I think you would want your students to be well rested and get sleep, but typically people like scroll on their phones to like 2 a.m. But the thing is, darkness actually creates melatonin naturally, and we actually perceive light as sunlight, so we wouldn't actually um, generate any melatonin because of how our ancient firmware brains operate. It's pretty funny. But yeah, I'm just curious when that paper was, funky.
Yeah, I am looking for it. I also unfortunately went through the patch of the train line where my internet just died, so I missed half of the beginning of what you were saying as well. I'm very sorry. So you might have to give me a moment to I guess keep looking as well, because my browser was also not loading. But I guess like on what you guys are also just generally saying in terms of like seeing this advent of like increase in like ADHD diagnosis, etc., or like tying sort of even just like general technological habits to like trends that we're seeing. And this is like obviously like the part of psychology that gets really, really hard, which is like what is something that's like causative versus like just a byproduct of a bigger problem. So like the ADHD diagnosis rates is actually realistically like exactly in line with what we would expect to see based on like increasing quality of the system as a whole. So it's not that we're seeing a greater increase in ADHD. And that's also tied more generally to the literature that sort of exists out there with regards to the genetic component of it, which is ADHD is already in the process of being reclassified as a disorder with regards to energy deficit and having a whole bunch of like other systems involved in terms of connective tissue and immune system stuff. And like I say that as somebody with ADHD, and like I am very fortunate in certain facets that I have like just dodged the bullet on a lot of very complicated systems at times being involved. But then the inverse of that being that like I struggle massively with energy, and that reclassification like makes a lot more sense. And if I looked at sort of my screen time growing up, for example, and the negative impact that had, for example, on my sleep, and the fact that I was given access to a device as somebody with a dopamine issue, it's like, yeah, I can look at all of that and also go, okay, this was problematic from a behavioral perspective. And, you know, the ADHD that I have lent into then a pattern and a habit, but you wouldn't say from the pattern I developed ADHD if you understand mechanistically that, okay, the ADHD is a genetic thing. Like it's always been how my body has been. There's, at least from my end, a lot of genetic things that make it very, very clear that that's the case. And then what makes it really hard is that a lot of people are missed by the system in terms of early diagnosis, especially women. So if we're addressing like, cool, like how are we looking at the system as a whole in terms of access to screens and the diagnostic process that we have for things like autism or ADHD, and addressing the fact that like women are far more often missed than men are because of how we socialize them, and then tying that in as well more broadly into like this overall question of like how the education system does or does not effectively like accommodate those people. You know, you get a very, very complex set of systems, and beyond that, like I think really would struggle to say much with certainty. So within like the framework of AI, I think there's like a degree of confidence that I have, at least with my familiarity with like the current research, to say, hey, like this is what it looks like. But you know, that is also the scientific process as a whole, which is that we haven't been looking into this for, you know, all that long. The paper that I was talking about with regards to like Gen Z, for example, that was a 10-year longitudinal study. And it's only in light of that study that we are starting to look at, okay, well, what was technology doing, at least in the school environment, that is like causing this regression rather than improvement that we've seen, generally speaking, for the last however many generations.
Again, you just have to be careful with the measuring method, whereas the Gen Z measured while using the technology that they're accustomed to. Because I imagine that they were given the same STAR exams as the previous generations, and they were told to sit there with a pencil and do the same bubble thing that other, like, so the point is that what they are learning is in a different direction because of the technology than prior generations. The testing of that needs to be different. Like the question,
Sorry, just to cut you off for a moment. I guess like maybe I've misexplained this, or maybe also you've got like a more broader opposition to what I've said, because I might have missed that. The testing that we were looking at with Gen Z is IQ. So IQ has a lot of problems, by virtue of it not being this perfect measurement of this concept, fluid intelligence. But it is at least in best practice trying to do that and be separate from crystallized. And you could like call into question methodology, whether or not people have experienced the test before, the socioeconomic influences of all of that, right? But if then we're assuming that that's equal across all generations, then actually the point is that methodology shouldn't be impacting, because in theory it's not something that any prior experience should be affecting. And like you're 100% saying, maybe that's still something we have to reassess in light of this information. But at the very least, like the history of improvements in generations IQ is largely currently tied to improvements of time and quality in our education system. That is to say that basically, okay, the longer you spend in school, the more you're able to reach your ultimate cognitive development capacity. But you're still 100% right. There's like always this extra layer to look at and then go, hey, is our testing wrong though for how things have shifted? And if we create another really rigid means of testing this, are we going to see that difference disappear entirely? And if that's the case, then I think you're 100% right.
We have to be aware of that when we do these comparisons, is what I'm saying. Because if you're not testing it correctly, then you're testing it against old things. And unfortunately, we don't have past experience to test this sort of radicalization, right? Like when the calculator was invented, the United States was also dealing with like delinquency rates that were at like insane levels, we didn't even make it a requirement that children didn't even have the right to be educated until, what was it, the 1890s, 1910, right? Like it was part of that whole beginning part, right? So the point is that if I talk about the calculator again, I'm not sure we even have the data of, hey, how were people doing with their arithmetic before the invention of the calculator, or how was their IQ doing before the invention of the calculator versus after the invention of the calculator. I mean, we might be able to hypothesize that a little bit on the little bit of data available, but I don't think we have the sheer volume of data like we do today. Today, data is incredibly, it's huge amounts of volume, right? And so...
Yeah, 100%.
Yeah.
Sorry, there's one extra thing I wanted to add there, though, which is like, at least in theory, like IQ was roughly developed sort of in the 30s, and the way obviously like this, these models are created is you create batches of questions and then you assess their like statistical power, and you look at then individual questions within that and you go, okay, this one is very predictive, this one's less, and you take them out or you put them in. And that's obviously been going on for a very long period of time for us to have at least a decently reliable psychometric. Like IQ is technically one of the most reliable psychometrics we have now, but it doesn't mean it's perfect. But what you're getting on there a little bit is sort of IQ, but my understanding generally would be that, okay, the process through which we outsource this extra step of familiarity with like arithmetic and subtraction and multiplication, division to a calculator, maybe there is something lost in how our brains are developed. and you're 100% right in terms of a time frame for when IQ was starting to be measured and how well it was being measured, and when that sort of was happening, sort of maybe not giving us a powerful enough data set. But I guess like conceptually, I think the thing that like I'm seeing this from in terms of a larger framework is tied sort of to these broader ideas in terms of like what fluid intelligence is trying to look at, which is effectively this weird combination of like speed and recognition and working memory, right? Like in a very basic sense, right? We sort of test them in most models will have like 4 or 5 categories that they test that across. But most of them also won't, will either to some extent be localized to the culture that they're testing, generally speaking, or will be generalized enough that sort of like environmental experiences in theory aren't going to be influencing people's ability to perform. And that's not to say that there aren't variances on any one day, but more so that I just don't see at least enough evidence for any indications so far that AI is functioning in equivalence in the same way that a calculator might be from the data we're currently seeing.
All right. I mean, yeah, I obviously would be interested to know the outcomes of these types of things as well. I mean, if it is a detriment, we would probably want to know that. I'm always skeptical that Juvenoia is showing up in a lot of these, calculations that people are trying to do. And so I'm always concerned about that, because I'm like, I find Juvenoia very annoying. And so,
can you define that term for me briefly, actually?
Juvenoia is it's the standard psychology that every generation thinks that they are smarter than the generation that came before them and wiser than the generation that comes after them. And so this is a known thing called Juvenoia.
Mm.
This is why you can pull up literally articles complaining about the stupidity of children and how they spend all this time
it's like the Dunning-Kruger effect.
So like,
no, this is different.
No, it's different.
Well, I mean,
it's different because it's
okay.
The point is that like you can pull up articles from the 1920s where people are, because children had just been given basically the right to learn to write, and so everyone suddenly knew how to write, and then before that no one knew how to write, right? And so you have this era where like you have people writing articles about how annoying it is that these children don't know how to do anything normal. They can't even sit and have a proper conversation like normal people. They're just passing notes all the time, right? You could literally pull that out and put it side by side with a complaint of parents and kids text messaging all the time, and it's identical. Right, it's like basically identical.
You can do it for every generation.
Yeah, you can do it for every generation. Yeah, every single fucking generation complains about something that the children are doing, and complains about how stupid their parents were who didn't know shit. Right, and that always happens. And so, I'm always skeptical of a lot of these comparison things of the generations, because we know that biologically there's incredibly little difference, right, from generation to generation. And so there's always a concern about how we're measuring the cognitive ability of people from generation to generation, because like it isn't like they physically changed, right? It's it's entirely environmental, right? And so we always got to be measuring that correctly,
Hey, I have a question. Anaxomatic. Did you grow up before the calculator? I'm just curious.
Did I grow up before the calculator? What kind of fucking fuck off, dude? No, that's a big fuck you. That's what you get from that. Jesus Christ! Before the calculator. When do you think IBM? I'm sorry. When do you think IBM was started? Like when they were, doing computers, right?
That's rough.
The 80s? Did you say the 80s?
No.
No, yeah, it was.
No,
it was
I
much
don't. I
earlier.
don't know if anybody said anything.
Yeah. Oh, I thought someone said the 80s. Yeah.
Just
Anyway,
inquired.
yeah, the calculator was invented a long time ago, right? And before that,
How
it was
far?
log books. You know, people just got really fast with the log books. They'd be like log, and then look up the exponential. They wouldn't even want to do addition, right? Like who does long form addition anymore? That's stupid. You look it up in the log book, right? So yeah.
That's why I kind of appreciate listening to these conversations, because you're not
Yeah.
dealing with those biases. I mean, you're talking about, you know, measurables and what
Yeah.
are the biases that are involved in these measurables over time, and
Yeah. So
et
to be
cetera. Very
to
interesting
be
to listen to.
just to be clear, my entire calculus series that I took personally, I had a TI-89 the entire time I was doing it, right? And that's still considered one of the top line models for doing, you know, calculus stuff. I think they have slightly newer ones now, maybe with like a colored screen or something.
Yeah, I have a little fancy one.
Yeah, but it did it all.
But
It
it's
did
still good.
symbolic. It did symbolic reasoning. It did derivatives and integrals for me. You know, it did all kinds of shit.
That's fine.
Yeah.
Don't be just in the back of the book appendix either. We still use that to this day.
Yeah.
Figure out how to do these things.
TI-89 is still considered pretty standard. And I downloaded assembly programs, and one of them was Mario, and I could play Mario on my
God.
freaking calculator. Mm-hmm. Yeah.
Sick.
Had no sound, but you know, that's okay.
Funky, can I ask you a question?
Mm.
Do you have a
Sorry, I'm
background
also
in-
just looking up this thing, but yeah.
Yeah, that's fine. While you look it up, do you have a background in psychology or anything?
Yeah. So, if you're talking formal education, technically, I don't have a degree.
Oh no.
You're talking the jobs that I've worked in. I've been involved in clinical diagnosis in psychology. I've worked in sports science. I've worked in ethical philosophy, and I'm currently sort of shifting into policy writing for politicians here in Australia, and then also dabbling in maths basically and physics at the moment.
Oh,
that's
no.
cool.
Yeah, no, I just want to make a comment. It's very interesting to listen to, you know, professionals in the field discuss these things. Oftentimes, I'm fairly skeptical.
No, I'm
a lot of
I wouldn't even
analysis.
call myself a professional, but I guess
Yeah,
that's.
It seems like
I guess the difference.
It sounds like you're a professional. If you ask me.
Well, I guess I want to make that clear in that
Your job.
well, it's not. That's specifically what I want to make clear. It's not my job. It's like I can't pretend I'm not really smart, but I also don't want to pretend like I've been qualified or achieved a certain degree, etc. Like there are people far more expert than I am. It's like the one benefit
Sure.
I've got is like I hear something once and I can remember it. So when we're talking like if I see a random string of 20 numbers, it takes me like five goes to remember it, right? Something like that.
Right,
Talking
right.
letters and numbers.
But my
So-
point is, if you don't mind, my point is that it seems like with your profession, you actually have to, you know, understand the measurements and the data that's being applied in any sort of decision that's involving a psychological perspective. Oftentimes,
Oh no, I do AV for my job.
exactly. Yeah, that's my
No, I'm
point.
not paid to do any of this.
Oh no,
I'll do it for free, bro.
you're insane. That's my diagnosis. If that's the case.
I am insane. You know, this ties a little bit generally to what we were talking about, just in terms of like the education system, as well as like the societal structures that were in place when I was being educated, weren't set up to like let me succeed. So like I was in a household where like all of us were like victims of domestic violence, and
Sort of,
in a schooling environment where like there was a brief moment of consideration for like acceleration for like my older sister and myself, and like neither of us got that. And so like most of my young adulthood was like processing trauma, and that's why I ended up being very aware of like the research in psychology, because that was very helpful. and then like now that I understand that how my brain works in terms of like the ADHD and everything, it's like, oh cool, like
Sure.
I should actually like focus this very very intently on the things that I care about, and most of what I care about is like solving very difficult problems. But then like on that, and this is why I was interested in listening to you guys talk, is like I'm very new to at least going back to mathematics. Like I feel way more confident with philosophy and language, but formal reasoning in terms of like mathematics and stuff like that, I'm like, oh, well outside of my comfort zone. And so I, like, and stats in science is like, oh, you can tweak them in any way to make any study look like it has significance.
Sure.
I'm sorry. I push back on stat statements.
Hey, funky.
That is me jokingly generalizing. Sorry.
No, that's fine. That's
Well,
fine.
an interpretation
That was not a weighted. That was not a weighted.
Yeah, it's
Yeah,
just
sorry.
to someone that knows a lot of stats, right? Like I hear that a lot. Is people go, "Can't you do anything with stats?" For every stat, there's a liar or whatever phrase you want to do, right?
No.
And it's like, and in reality,
Hmm.
there's bad stats and there's good stats. So some people might incorrectly apply stats, right? But when stats are correctly applied, you can make phenomenal headway on incredibly complicated things, as is regularly done, right? Like stats are used all over the place, from how you assess that a model is fitting a particular data set to how you do stochastic gradient descent in terms of, neural networks to, how you get a machine learning model to converge based on some data or whatever, right? And anyway, all I'm saying is stats is incredibly important and incredibly useful, but there are bad stats out there, and normally it's not this. And to be clear, 99.999% of the time, it's not the statisticians or the research that is incorrect. It's the sensationalization of it when it's put into the media and how they portray what happened or how it happened or what the stat says, So
To that point, there's 2 points I want to make. One I want to argue with you about, but the other one is very interesting. Is that back in our experiments, which are fairly large, now because of the point that you're saying, a little bit not exactly related to what we were talking about before, but we have to start actually going through large committees in order to get plots approved and things along those lines, because of that very reason of a news agency taking something, sensationalizing it, and then that would effectively start doing some sort of impact on our funding, which is very unfortunate.
yeah,
But
that's dumb. Yeah.
as far as the bad
Sad.
stats go, there are times that typically occur, and hopefully these things get filtered out through the process, like the peer review process.
Yeah.
But you still end up with things like biases in your data. Like if you were to do some sort of event selection,
Sure.
which is going to bias your data, so you might have
Sure.
some sort of chi-squared that looks good,
Mhm.
right? But even then,
Yeah,
you have a
but
bias to make it look good.
yeah, and
that some
that's
people
where
might not notice.
but it's still part of the scientific inquiry, right? That's like
Sure.
saying Darwin put forth a model that turned out to be kind of shitty, and we have plenty of other mechanisms that explain biology better, and he didn't know anything about DNA. Well, of course, right? Like the scientific inquiry is, testable, reproducible predictions and such. So, like, if you make a statistical prediction based on the data, and then no one else is able to replicate that, then you end up in an isolation where it's like, well, why is there something that's going on, right? Maybe there's some particular bias that was in the data set, and that needs to be investigated or looked at. So like I don't consider that like bad, right? That's just part
Well,
of
it's
science itself, right?
Yeah, I'm not considering it bad. I'm just saying there's a little bit of an imperfection there that
Certainly.
I guess not really arguing too much, but
Yeah.
something
It's
to be
just
wary of. So
it's just
statistics aren't perfect, right?
Yeah, but it's the same imperfection that you get from anything. Like someone puts forth a physics model, maybe it gets overturned in a few years, right?
Mm-hmm. Sure. or you compare to global fits, etc., like what you're saying, which is typically what happens.
Yeah.
Can you teach me what a
Yeah.
contour integral is?
A contour integral?
Something I don't want to do.
Didn't we do this the other day? I thought we did contour integral the other day.
Not with me.
So there's
If you
different.
do, that means you could find.
So the mistake I made last time, there are different kinds of contour integrals. So we have to put that caveat out there, right? So there is a contour integral of a real valued function. So a real valued function is one that maps to the real numbers, right? And typically of interest is you think of the contour as mapping in some space, right? In 2 space. And you imagine that there is some value on the contour as you travel along it, right? And you want to know the total value that the contour acquires as you travel along the contour, right? And so this is very well understood. The way that it's done, and this is the symbology you use, I want to integrate along the contour using the function f. So f is supposedly a function defined everywhere. So you can think of f as like a vector field, like it's representing the magnetism, and then this is some particle trying to travel through it. Or f represents the density of some water, or the flow of some water, and then this is something trying to travel through the water. And so you're attempting to find the cumulative amount of force or magnetism or energy or whatever, right? And that's what the invention of the problem is for. So the definition of this is that you want to integrate whatever the definition of the contour is. So the contour is going to be some interval. Typically we fix it to 0, 1, but you could use technically any interval. And it maps into the plane. So each point on here is some point in time. So like this is t equals 0, and then this is t equals a half, and then this is t equals, 3/4 or whatever, and then this final point is t equals 1. And so that's what a contour is. It's a map of some path through 2 space or 3 space or whatever. So 2 space in this case. So if I want to integrate along that path, the way that that's done is you integrate along the domain of the path. You plug the path into the function, and then you have to multiply by the length of the path, which is the derivative of it in magnitude. So dt. And so that's the definition of contour integration. So some take this as literally just the definition. That is how we define contour integration. You could also go through an argument about why it should be this, and that's kind of a separate discussion. But for the most part, you can just take this as the definition. The definition of integrating a contour, the definition of integrating along a contour for a function is to plug the contour into the function and then multiply by the length of the contour, right? Now, the length of the contour is a little tricky to consider. The contour is a function of t, and it goes into 2 space, so that means it has 2 components, an x of t and a y of t. And so there's 2 issues going on with the length of the contour. One is you have to consider what does it mean to take the derivative of the contour, and the other one is you have to consider what it means to find the length of the contour, considering that its output is always some point in the 2 space, right? So since it's always outputting a vector, you have to know how to take the length of that vector. So we should point out that definitionally, the derivative of the contour's length is the square root of x prime squared plus y prime squared, right? And so now you can do any problem you want as long as you know this definition of what the length of a piece of the contour is, And as long as you have any contour defined over any variable, then you can always do the integral along that contour given any function, right?
Nice.
Yes.
Beautiful.
Hmm.
Now, as soon as we change the function
And then
to the complex numbers, then all that goes away. And we change it. Right?
So this, I'm trying to recall back. Does this also? I'm assuming this is non-conservative fields you're dealing with.
No, this doesn't matter. So what you're referring
That's okay.
what you're referring to is that if F is a conservative vector field, then it turns out that its contour integrations are path independent, meaning that it doesn't matter
exactly.
what path you take, right? But the definition of contour integration doesn't care if it's conservative or not, right? So you could give me a
Right.
non-conservative function, and then this is the definition. So like what I'm pointing out is how do you compute it, right? I'm not invoking any special theorem, right? Yeah.
Right, that's encoded in like the square root of whatever, because you're looking at effectively the differential at each point.
Yeah,
And looking at a change at each point.
this definition shows up because, so this is how Euler would do it, right? You zoom in on a little part of the curve, right? Because you zoom in and it's infinitely small, then this is effectively a line, right? And then you ask, well, how do you figure out the length of it, right? Well, it has two points here. The first point is, some x0, y0. And then the second one is, x1, y1. And essentially he would argue something along the lines of, well, this is, going to be the difference in the y, i.e. it's going to be y prime. And then this is the difference in the x, so i.e. it's going to be x prime. And hence the length of the contour at any particular section of the contour is the Pythagorean theorem. It's the square root of the square of the two sides, right? And so this then becomes the formula for the contour. That's a very hand-wavy argument, but that's
Sure.
That's how it would be.
This is fun. It's bringing me back a while. A lot of things that you tend to forget, and you're effectively just summing over each of these little changes.
Yep.
The function at that point in each of these changes. That's cool.
Yep. Yeah, you're adding them all up, and each little section is multiplying by the value of the function at that point. Yeah. So for complex, right, complex functions that map from z to z, even though this is two variable to two variable, in reality, complex functions are one variable functions. It's one variable to one variable. It's just that they're complex numbers. So this is a univariate contour integration, and that makes it, somewhat more special. So contour integration here is almost the same, except that in complex variables, we don't care about the length of the contour. We care about its value with respect to complex numbers. So we're not interested in doing literally its length. We're interested in doing its difference with respect to the complex numbers, right? So if you gave me a contour and over time it is producing some numbers, z, right? It's producing complex numbers, right? So we'll just say it's mapping into C. Then how do you define the contour integration? So it's going to look almost exactly the same. It's going to be the integral over the domain, f mapped inside of it, but rather than the length, we're just interested in the derivative of the value of the contour at that point, right? So in other words, rather than calculating the distance between them by the individual components based on thinking of them as two vectors, we're instead thinking of these as just like, z0 and z1. They're just two numbers, and I just want to know the delta, the distance between them, the delta z that's going on here. and the delta z is just the derivative, how quickly the contour is changing from one point to the next point. And so that's the definition. So anyway, they look almost identical, right? That's the whole point to point out. They look literally identical, except one is interested in the real valued length because the output is a vector, and the other one is not thinking of it as a vector at all. It's thinking of it as outputting complex numbers, so it's just a straight multiplication. So the integral here may not even come out to a real number. It might come out to a complex number, right? Whereas this one, the answer will obviously be a real number, right? And so this is complex contour integration. And this is real valued contour integration.
I don't recall it being that simple for me. You have to do contour integration when dealing with poles. I don't really recall.
No, this is definitely
No,
it.
it's just-
I have Marsden.
Really, it's that easy.
I could pull Marsden out. I don't.
It's
no,
a
I
difficult
don't have
concept,
here.
but it seems easy when I look at it here.
Yeah, well, it's certainly non-trivial. I mean, here, watch. I could do a trick for you.
Yeah,
Like,
let's
we could
do
just
one. Let's do
we
one.
could just do one
Let's
for
do it.
fun, right? We're going to integrate around the unit circle, and we're going to integrate 1 over z, right? And so this here it is in the complex plane. We're going to integrate like this, right? So I need to come up with a function for this integral, right? So the function c. It has to take a point and it has to map to each of these numbers, right? And so what am I going to do? I'm going to do e to the 2 pi t, right? So if I plug in 0, I get 1. And if I plug in, what is this? A quarter. So I plug in a quarter, I get I. And if I plug in, I need an I in here. Oh, my bad. So if I plug in 0, I get 1, and if I plug in a quarter, I get I, and if I plug in a half, I get -1. If I plug in 3/4, I get this one. And if I plug in 1, I get that one, right? So this is a function that is successfully from 0 to 1 into the complex plane, and it's the unit circle. So that's the contour that goes around the unit circle, right? So I'm going to integrate this function around the unit circle, right? So how are we going to do that, right? Well, we're going to do my piece of paper. Integral contour 1 over z. Contour is e to the 2 pi I t. Okay, so let's do this. So the definition: the integral is 0 to 1, because that's what the contour is. Plug in the contour, so 1 over the contour times the derivative of the contour dt. That's what it is definitionally, right? So we just got to plug in the things. So it's 0 to 1, 1 over e to the 2 pi I t times, and then what's the derivative? The 2 pi I comes out in front, times e to the 2 pi I t dt.
So-
These cancel, and I get integral 0, 1, 2 pi I. The antiderivative of a constant is just t, and t of 1 minus 0 is 1, and so we get 2 pi I.
So with this, we could take, if we're dealing with some sort of pole, you can go into the complex plane and then do a contour integral to deal with the pole. By
well,
using
yeah.
the
Yeah.
Oh, okay. I never understood that.
Well, the contour never went through 0, so like I didn't give a
Right.
fuck about 0. It's just it happened to come out to 2 pi I, right? That's all.
Oh, mm.
Yeah. So what
'Cause,
you're
maybe it was,
so here I think the thing you're trying to talk about is the residue theorem of complex variables.
exactly, yes. Yeah.
Which is that, so this is a theorem of complex analysis. If you integrate on any contour of a function and the function doesn't have any poles, and the contour is closed, so let's make sure we have that. closed contour and function no poles, then the answer is always 0. So this is a very magical theorem. You can integrate on any contour. You will always get 0 as long as the contour is closed and there isn't any poles. This contour is closed. What does closed mean? It means that wherever you started, you ended at, right? So the contour did this, and it made a closed loop. So because it makes a closed loop, that's a closed contour. And so the point is that this problem is special because I integrated on a closed contour that had nothing to do with the fact that there was a pole in the middle, right? There's a pole in the center, right? And I see that the answer is not 0. And so that's special. It's special that I did an integral and I got not 0 even though the contour was closed. Because in general, the integral of any analytic function is going to be 0 if it didn't have any poles, right? And so in some sense, when we did this integral, we detected that there's a pole inside of the contour, even though the contour didn't go anywhere near the pole, right? Yeah.
But typically, yeah, I think that's what I remember if I'm doing, I don't know, some sort of contour or some sort of integral, and I have to avoid the pole. Then I go to the complex plane, do a contour, and kind of hop over the pole and do this. But I guess it's not closed in that sense. It's still, it would be.
Oh, you're trying to integrate through a pole? Because normally that's done with
Yeah.
limits when you get near it. Like if you have a pole and you go like this.
I'm trying to go back to what I can remember back to. Yeah, exactly. That, yeah.
I know what you're thinking of. You're thinking of these shitty integrals that are like, I'd have to think of one off the top of my head, and like e to the x over the square root of e to the x plus cosine x or something. I don't know what it is. I don't even know if that would work. But you do some weird funky thing and you're like, how in the world? This is such a shitty one. Oh my God, don't do this. Okay, hang on. We got to put like a -1 here. Maybe we make this a 1. Yeah, like e to the x minus 1 or something. So if I plug in 0, I get a pole, right? So this in the real line, this looks like some crazy function, and you're trying to find the area under it. And you're like, well, how the hell could I do this, right? So then they tell you this trick where they're like, okay, think of the complex plane. You're trying to integrate along the real line. So instead, maybe we could do something kind of cool where we integrate up to some number, and then we hop over, right? And then we integrate to some other point, and then we'll connect this with a big arc, and then we'll try to talk about each of these 4 pieces. Because we went around the pole, we know that the integral of this is 0. And so if I know something about this arc and I know something about this arc, then I would actually know the integral along the 2 lines, because I know the sum of all of them has to be 0, right?
So what would be the difference between the two then, or something along those lines?
Exactly. The sum of these 2 would be equal to the sum of those 2, right? And so the point is, I don't have to integrate along the real line. I can actually integrate along these arcs, and I would get the same answer, right?
Oh, thank you. This is a topic that I always run into and can never really. Nobody explains it well.
I don't know if this is a good example of one, but there's some that look like they look like this. They're really shitty.
They come up nonstop in E&M and quantum mechanics and everything all the time.
Yeah,
we just do them and complain.
Yeah, there's weird. Yeah, there's residue. Yeah, so this is like residue theory, but it's more like residue theory tricks, because you're trying to do a real integral. And then someone's like, but what if we go around the singularity so we don't have to fuck with it? And it's like, oh, so we have to go into the complex plane to do that. And, we hope that there's some trick that these other parts, work out nicely, right?
Mhm.
And if they do, then we can figure out what the integral is, right? Yeah.
It's cool.
Mm-hmm.
Killed everybody with my math question.
Dude, like, Bobby, I don't know how, like, I don't know how you just you explain things from like first principles. Like, it's
You're
not
doing a
just,
very good job.
yeah, like, it's not just, oh, here's some damn, like, just facts about like this, like, just memorize it. This does this. No, it's like you actually build the Legos from the ground. Like, that is so damn cool.
Thank you. I try.
I don't know what it is. I shit
Yeah,
you not,
like-
dude. The amount of times that we've gone over this topic and nobody understands it is very. It's every time. So it's pretty cool.
Yeah.
Man. Thank you.
Yeah, this trick, mathematicians do this trick a lot. I read a paper by E.O. Tuck. E.O. Tuck. And man, I would have loved to work with E.O. Tuck, but unfortunately he passed away, so that didn't get to. But anyway, he wrote a paper on doing transform inequalities, and we don't know a lot about transform inequalities, but he pointed out, he goes over a couple of tricks that are interesting where he's like, well, let's say we wanted to know if something is positive, but we want to know if this cosine transform is positive, but we can't tell, right? It's, the kernel part has all this oscillation in it. I can't tell if the oscillation cancels out or not. It's like not possible. So it would be possible if we could somehow get the kernel decreasing, right? But the kernel is not decreasing. So what do we do? And so a trick is he takes the entire integral and shoves it up into the complex plane until he hits a singularity, and it forces it to be decreasing because the singularity made it go up to infinity. So like the original function looks like this in the kernel, and then as it moves into the complex plane, it becomes steeper and steeper and steeper until he hits the singularity, and then the function looks like this, right? And then he's like, oh, now it's decreasing. So now we know that it's going to be positive. All the oscillations will cancel out, right? And so that there's a trick of like literally moving the entire integral into the complex plane and forcing it to be at a singularity. So it's like the opposite of this. Rather than avoiding a singularity, he forces it to be at a singularity so that we can guarantee it's going to be a positive integral. Yeah. Anyway, it's a good trick.
You lost me at kernel. That's been that's another difficult topic.
Oh, what is a kernel?
Green's function. Kernels and Green's functions and a lot of that stuff is pretty common in physics and difficult to understand.
So when a function is defined in terms of the integral of another function, typically that's cut up into two parts. The first part is typically of a variable that's going to be integrated over, and then the second part is a function of two variables. One is the variable of integration, but the other one is the variable that's producing the function that you're defining. So anytime you do this, where you have a single variable function that is being integrated with, and then a two variable function, this is called the kernel, and then this is called the transformer. And so classic transformers are e to the ixt. That's called a Fourier transform. Another transform is like cosine xt. That's called a cosine transform. Right. Another one is e to the xy. Oh, sorry, e to the negative xy. That's called a Laplace transform. And we can keep going down the line. There's a Mellin transform, Laplace transform, Bessel transform, blah, blah, blah. The point is you have transforms, and then the thing you stick here is called the kernel. So like we integrate kernels and we turn them into other functions. So like we integrate we do a Fourier transform of a function, we turn it into another function, or we do a Laplace transform of a function and we turn it into another function. And so this general form is given this name. So you got a kernel and you got a transformer, right?
Yeah, this is all way above my head right now. So
Hey, you want to do
Oh,
quantum
no
field theory? You better fucking learn it. So,
yeah,
'cause we haven't, so you get a head start.
Yep. I mean, I'm running it down, so I mean, like, give me a few months, and I'll be able to
Yeah.
hang.
Well, there are plenty of functions that we only know based on their integral forms. Like we don't know them in any other way other than an integral representation. And
Seriously?
yes, and the classic one is the gamma function.
Oh yeah, duh. Okay, I should know that. I'm gonna
So-
smack myself.
So the gamma function is I forget what it is. It's like 0 to infinity of, let me guess, e to the t to the n, e to the minus t. I don't know.
I literally had the gamma function up like 5 minutes ago.
T x is the
Let's
x
see.
go
What the
here?
hell is it? Like, here.
I don't
wrong.
remember what it is now. Uh-oh.
It's wrong,
I thi-
dude. Like,
where's
it's wrong.
my
You lose
X?
the argument.
I
You
know.
lose the debate.
Where's the x? Oh shit. No. Okay, hang on. I think there's an x over here. Maybe it's like t to the x and then dt.
No.
All right, someone help me. No one's going to help me? Okay, fine.
It's
Yeah.
t to the what are you integrating over t? So it's t to the x
What is
t to the x minus 1 and then e to the minus x.
T
or
to,
minus
t to the x minus 1.
T to the x minus
And-
1, e to the
Hang on.
minus x. Yes.
I'm only off by
E to
a
minus t.
single minus 1. Psh, yeah. Screw that. Yeah, that I was close enough. That's fine. That's fine. For just trying to remember it off the top of my head, I'm happy. That's
Come on,
good
that doesn't
enough.
look like the table. At the
I
back
knew
of the
this
book.
part
You're
was
looking
wrong,
for.
so I corrected myself, and then I put that. But I got the 0 to infinity right, the minus t. Yeah, off by a minus 1. That's not bad. If anything, that's just 1 over t, so that's like the integral of the gamma function. So I figured out the imaginary integral of the gamma function rather than the gamma function directly. So that's good.
Here's a little fun fact, Zero, about the gamma function. It's a generalization of factorials to all real numbers. That also extends to complex numbers. I'm
It
correct?
does, yes. Yeah, you put x.
No shot.
X can be any complex
It's a
number.
pretty cool thing.
Right?
Mhm.
Yeah.
Whoa.
It's just a factorial, really.
The gamma function? Well, the
I
gamma
think it's a
function.
generalization of the cap factorial.
Yes,
I remember-
correct.
Yeah.
Yeah, I mean it's isn't it like +1 or something though? Like this equals
maybe.
x plus 1 factorial or minus 1.
Yeah, something along those lines. I don't remember exactly.
When x is an integer, or sorry, not an integer. When x is a natural number.
I think it's x times the gamma function. No, sorry. Don't worry about it.
Well, what you mean is, I know what you're talking about. What you mean is that the gamma function satisfies the following equation, which is that x times the gamma function is always equal to x plus 1. And that's true for all x in the entire complex plane, right?
Some sort of identity.
Yeah, that's a special identity of the gamma function, right? Which means that a shift of the gamma function divided by itself always comes out to a linear. It comes out to x.
Well, funnily enough, to cycle back to what we were talking about before, where I was talking about weird dimensionalities and differential operators. Maybe this is somewhat related, but I was doing some reading after that just to kind of refresh my memory. But and there's some renormalization techniques in quantum field theory where you end up making it possible to do integrals if you're integrating over some sort of parameter space to, in fact, integrate over the dimensionality of d being some arbitrary dimension defined by some sort of expansion at some point in time earlier down the line, minus some small epsilon. And both of those can be complex, and the solution to that involves some gamma function of the dimensionality over 2, which is very interesting, I think. But it's not obviously obvious why that would be the case. But anyway, the point is, yeah, we were discussing weird dimensionalities and differential operators, and that's where I remember it coming up. And we were talking 3 hours ago or something along those lines, if you can recall back to that.
Yeah, the gamma
Wait.
the gamma function shows up everywhere, right?
Yeah,
Yeah.
it's pretty useful.
Yeah, the last session I pointed out, someone asked me something about special functions. The gamma function is the ratios of the gamma integrals of ratios of the gamma of products of the gamma function in different different shifts. Precisely defines all possible special functions that you could ever derive, which in essence is basically all possible solutions to all differential equations, right? And so that's called the Meisner-G function, right? So it's in my opinion, it's a basically useless thing because like you could never use it, right? But it is a thing. There it is in its full glory. You have all possible,
Sure, but I'm talking about the gamma function being a solution to an integral of some arbitrary complex dimension that's not necessarily an integer, but it can be any real number or any complex number with dimensionality. You can solve it, and the solution is a gamma function. So long as the dimensionality holds, depending on some weird conditions. But
yeah, you'd have to write it out for me, man. Yeah,
I would, but it's hard to find.
Yeah, the gamma function has poles. By the way, there are numbers you can't plug into the gamma function, or it fails. Interestingly, 1 over the gamma function is infinitely differentiable everywhere and has no poles. Meaning that the gamma function has no zeros. There is no complex numbers where the gamma function equals 0. So 1 over the gamma function is infinitely differentiable everywhere. It has no poles. Meaning 1 over the gamma function has a Taylor series at every single point in the complex plane.
I will write it out, but I'm going to butcher the fuck out of this. So,
yeah.
Yeah, I'm looking at the graph for it. Holy moly.
Oh, the gamma function? Yeah.
Yeah. I don't know why when you said whenever you started when we were talking about like residue theory, I don't know, the way you just explained the functions and like you immediately like showed the graph after, and like I don't know, it just kind of like opened a new door. It's like, oh my gosh, I forget functions are literally like just graphs. Like,
yes, they are graphs.
I don't know if that makes sense. I don't know if that makes, but
yeah, there's lots to learn. Yeah.
Like it's so trivial, but like when you think about it, like I don't know, the way I always got taught, it's like, oh yeah, functions, graphs, two different things. You do this with graphs, you do this with like the algebra.
I left out I left out the variable, the x. Imagine an x there.
In the dx, is it dx?
Yeah.
Gotcha,
X being any just general. There we go. Solved. Ignore what I put.
Oh, I see. I gotcha. Interesting. Okay, so you're doing like a fractional derivative.
Yeah.
And that like produces okay. Yeah, so when you put little thingies on the differential part, what you're really talking about now is fucking around with the measure theory, right?
Okay. What is that?
So measure is how we do arbitrary integrals. So like if you give me a function and you want to integrate it, normally you put a dx, right? But who says you have to integrate with respect to so dx essentially means that in whatever space you're talking about, if you're at some point and you move to some other point, then you're talking about this distance here, right? That's what dx means, right?
Sure.
But
yeah.
who says that I have to measure by doing some straight line between 2 points in the space? No one said I had to do that. And so you can integrate with respect to an arbitrary measure, like so, right? And so this is measure theory,
Right, but
now,
it's
right.
It's a very difficult concept to understand a dimension that's, not integer based, right? It's really weird.
Absolutely,
It doesn't really make
yeah,
sense, but it somehow
yeah.
works out that
It the point is that like when you start messing around with this, then what you're really talking about is you're messing around with how you're going to measure distances inside of the space. So you're not doing Euclidean measure, right? You're doing some arbitrary measure, or you're fucking around with it a little bit, right? Yeah.
I don't know
So
what
you're
that means.
changing your
Arbitrary
metric.
measure.
Huh?
I just don't even know what that means. Arbitrary, like, I don't know.
I will try this. I'm going to make an attempt, but you're effectively changing how you define distances between points, being that you're looking at separate something called a metric.
Yes. Yeah. Measure's technically more complicated than metric, but they're for this conversation they're the same, right? So when you have a space like here, we're in R2. There's a question about how you talk about distance in R2. And that's very important if you're going to talk about contours in R2 or integration in R2, because you have to know what distances mean. And so if I pick 2 points and I draw a line between them, that's called Euclidean measurement. And we can even explicitly say it, right? The distance between the 2 points is defined as the square root of their coordinates. So if this one is x1 y1 and this one is x2 y2, then it's x1 x2 squared plus y1 y2 squared. Now, in order to measure distances, you have to satisfy certain requirements. Like, you can't just give me any possible function, right? Only certain functions are allowed to do measurement, right? So what are the requirements? There's a list of them. Every 2 points you measure has to have a distance greater than 0. You have to respect the triangle inequality. So what does the triangle inequality say? The triangle inequality says that the distance between 2 points always has to be the shortest path. So that if you were to go to some third point, the sum of those 2 distances is always going to be greater than the distance that you traveled. And that has to be true of any measure. So if you gave me some wonky measure that did some crazy shit, whatever it does, that crazy shit it does to get to some other point better take longer than to get back to the first point. Like, this distance better be shorter than the distance of the other 2, right? Otherwise, it's not a real measure, right? So this is a metric, and it's the Euclidean metric. There are plenty of other metrics. Another famous one's called the taxicab.
I've heard this too.
Yeah, so the taxicab
No
says,
idea what it is. But...
Well, here's what it says. It says that if you want to go from one point to another point, the only way you're allowed to travel is on horizontal or vertical lines. So the distance between these two is defined as the sum of those 2 lines. So this line plus this line, line. So you just add up those 2 lines, and that's their distance. So for example, under the taxicab metric, if I have the point 0, 0 and I have the point 1, 1, then their distance is, what would it be? 1 and 1. So it'd be 2. So the taxi cab distance from 0, 0 to 1, 1 is 2. Right?
Oh, okay.
Yep. And you can prove it's metric. Right? So.
Nice.
Zeno, have you ever heard of the topic of regularization or renormalization?
When's the last time I heard that? Yeah, I mean, if I can't remember the last time I heard it, probably not. Let's just assume no.
Well, I mean, you're probably coming into this if you're hearing like quantum field theory. If they want to do a calculation, you end up with sort of infinities. They use this method to sort of subtract out the infinities by changing the dimensionality and then subtracting some weird integral at some weird dimension to deal with those infinities. And you're doing effectively this. So normally you're integrating over like momentum space, right? Which has some sort of it's really K vector space because you're in a Fourier transform, but you're it's 4-dimensional, and you end up with infinities when you do quantum field theory calculations. And by using these methods, you can effectively subtract out those infinities. I still don't understand it, but that's effectively what they're doing by this measurement theory, apparently.
This is
different metrics.
Yeah, this is why I'm pretty much just gonna, as a physicist, just try to become as much of a mathematician as possible without calling myself a mathematician.
My mathematician friends who end up doing physics stuff are the only ones that understand the topic. But I understand a little bit more today.
That's very funny. Yeah. Yeah, no. I mean, of course, like this stuff is way too much for like a first year, but you guys make me kind of understand, understand it.
I mean, don't put yourself short. I'm asking basic questions about contour integration in real space. They're not easy to understand, these topics. It's easy to get lost and forget things.
Well, there's certainly they're certainly non-trivial. There's dozens of theorems that have been skipped, right? I mean, Cauchy's integral formula. Oh, we should do that just for fun because I love this formula. So remember how we learned about the Taylor series, right?
Oh yeah, I'm the one that asked that. Yep.
Yeah. So what is the Taylor series? It's that if you give me a function and you want to know its series, magically, out of nowhere, there turns out to be an explicit formula that allows you to calculate all the coefficients so that you can center the Taylor series. Whoops, let me put a Z there. Like these are the coefficients, and so you can calculate them. And we're like, oh my God, that's so amazing. Isn't that cool, right? Well, it turns out that the Taylor series can actually be calculated not with the derivatives, but with the integrals of the function. And so the way that that's done is rather than doing this, you do...
I think we lost him.
Oh, he disappeared. Where'd he go?
You might have DC'd. Shoot a message.
So these turn into, what is it? N factorial 2 pi I integral of a contour that goes around C of...
I've never seen it put this way before.
Yeah. So f of some other variable divided by z minus that variable to the n minus 1 d zeta.
What are you integrating over?
The other. Sorry.
What is gamma?
Huh?
What is gamma? Is that?
No, there's no gamma.
Is that some contour?
Where?
What are you integrating over?
I'm integrating f of I'm using like some other symbol that's not z, so it's just a squiggly z.
Your integrand, is that just sort of general?
Oh, it's the integral.
Domain?
It's the integral over a contour that goes around the
That's what I was
center,
wondering. Gotcha.
right? And then and you integrate zeta minus the center. That's the bad part. That's the part I messed up on. Times z minus c to the n. And so this doesn't involve any derivatives of f at all. No derivatives. It involves integrating f over a contour. In fact, this means that I can calculate a Taylor series using the values of a contour that go around the center without even touching anything in the center. Oh, Zeno. Hey, Zeno, you're a mod.
Yeah.
I think you can right-click yourself and promote yourself to the top.
Oh, that's what I thought, but I didn't want to I don't know.
Impose. No, that's fine. That's fine.
Yeah. No, my phone died, so unfortunate.
Oh, no worries. No worries. Yeah, so
It seems a little bit more difficult than actually just, making an approximation saying, I'm going to take it to order 3 and that's good enough. Right?
True. If your function, if you know the derivatives of your function and you know the derivatives at the point, but what if you have no access to the point and you don't know the derivatives? Well, then this
How would you not know the derivatives?
I don't know. Some alien force is preventing you from knowing.
I thought you always know the derivatives.
For some reason, you don't know. You don't have access. So
we don't think about that.
We don't think about that. Why would you not know the derivatives of a function? I don't know.
Yeah, just do it.
Yeah. Just do it. That's funny. So this means that I don't have to know any derivatives of f, and I get the exact same numbers as what you get over here, right? I can't remember. Oh, you know what? I don't think this is supposed to be there. My bad. You put the 1 there. You put the n factorial over there when you equate them. So it's 1 over 2 pi i. In general, this is, you can write fk, the derivative at the centers divided by n factorial is equal to 1 over 2 pi I integral of a contour that goes around the center, integrating along that contour of f, and then integrating the fraction that has a singularity at that center, n minus 1, right? And so this is known as Cauchy's integral formula.
That's a name I have not heard since Calculus 2. Oh my god, that was so long ago.
Calculus 2? They don't do this in Calculus 2.
Yeah.
Cauchy's integral formula. 4 derivatives. 4 derivatives.
No, that was Calculus 2.
No.
Yes.
Complex integration is Calculus 2.
There's
never.
Cauchy's integral formula.
There's not a single.
You
could never give me a calc book that's got contour complex integration.
I'm learning Calc 2. I'm learning Calc 2 right now. You're barely learning integration techniques. You're learning integration by parts.
Yes.
I'm gonna pull out my Calc 2 book. I'm going to find one that has Cauchy's integral formula.
Show me.
Be
I would remember this.
I will
for real numbers. Okay, we're not dealing with
for Cauchy's integral formula for real number. How do you have a contour integral in real numbers? This necessarily means it has to start and stop at the same point.
I think I'm going insane here now. You guys are tricking me.
Yes, we actually had a private message before this. How can we trick Bobbin today?
That's what I thought that you're doing right now.
Yep.
I don't know. It's I can't find my book because somebody took it from me.
The old can't find book trick. I got you.
I thought it was Cauchy's.
Understandable. I know.
Maybe I'm thinking of something else. Cauchy something or other. Cauchy comes up here and there.
Yeah. Oh, yeah. Cauchy's got all kinds of stuff, I'm sure, but this specific one is the Cauchy integral formula for derivatives, and it's contour integration, closed contour integration, and it's the exact formula that demonstrates that you don't have to know any derivatives of an analytic function to guarantee it has a Taylor series, right? And that's just a ridiculous thing to think about. You have to know. You do not have to know any derivatives of a function in order to guarantee that it has a Taylor series, as long as it's analytic, right?
Yeah, because that's how I even like asked you about Taylor series, because I was expanding and I'm like, wait, these look like derivatives, and that's how.
Yes.
But then now you're telling me
Now
you don't even need to know that. That's so cool.
Yeah, they're actually integrals of the function around the center, right? Using contour integration. So another you were trying to take a function, right? And you're trying to expand it at some center to understand the function, right? And I'm basically telling you, well, if you go into the complex plane, you actually only need to know the values around the center, and that's sufficient for you to calculate the Taylor series. You only have
Son
to know
of a gun.
Yeah, you only have to know the values on a contour in the complex plane that goes around the center. Yeah.
See, I was telling Bobbin this earlier. I'm like, it's like this. It's like this in violin too. Whenever you give me like a more complex subject, that actually motivates me to learn like the subtopics of it like way more, and I understand it way more because I understand how it all builds and connects together. Versus when you just tell me like, oh, here's integration by parts, here's here's the complex numbers, you know, whenever you get there, figure it out. No. Like I don't know. Sometimes jumping into the deep end is like way better for me. I don't know why that is.
No, good. That's good. Oftentimes, if you want to study physics, you'll encounter the problem where in physics, you're just kind of thrown these things and just told to use them, and really nobody understands it.
Yeah.
And it becomes an issue.
Yeah, and then we just ask Bobby to explain it, and then it's all good.
And he tries his best, you know. Maybe he forgets a minus
Cauchy
one
integral
here and there.
theorem. Okay, so. You're right. I actually probably remember it from graduate level electromagnetism.
That sounds about
a few
right.
words
Yeah.
from. Maybe there was some sort of sum in calc too that I'm trying to think of. Some sort of series that involved Cauchy. I don't know.
Yeah, all of calculus is usually in the integers, the natural numbers, reals.
Yeah, the real numbers. Yeah, you don't do any complex variables other than so. When I taught Calc 2, let's see. Do I even have? Maybe I shouldn't have, but there. So in Calc 2, you spend a lot of time learning. You learn a bunch of integral formulas, and then there's a whole set of integral formulas dedicated to trig substitution and various things like that. And you have trig substitution, you have trig functions and their integrals. You then have hyperbolic trig functions, and they have like this same similar pattern, right? And then you have other things along those lines. Yes, exactly. Yes, those types of things, right? And then it turns out that secretly all of these things are like related to each other, right? That hyperbolic trig functions are trig functions. You just got to rotate them by 90 degrees in the complex plane. And exponential functions are trig functions. They're summations of them, pairwise, right? And logarithm the point is you get all of these weird combinations, and so the point is as long as you throw in an imaginary number, suddenly like this whole why did a logarithm show up when I was doing a trig calculation over here? Like that doesn't make any sense. And it all of a sudden it sort of makes sense, right? I don't know if I have that anymore. Let me see.
Yeah, this is the stuff I hate most about undergraduate mathematics right here. Is all these stupid little identities you have to memorize. And Bobby's telling me you don't actually have to know these. You can just like derive them once you're cool enough of a mathematician. And like that's what I'm trying to do.
Well, you
Like
do
look at
want
this.
you do play around with those enough. You do want to know those, but
Yeah.
let me
Weirdly enough, I
see.
don't want to say that it's not going to be important, but it will.
Uh,
Not if you're an experimentalist, so you should become an experimentalist. Then you know.
No. He will not convince me.
It's cool. You get to play with cryogenics.
That is kind of cool, I can't lie. Oh, and like superconductors and stuff.
I haven't done superconductors. They use them at CERN.
uh,
We had to get training on them.
Oh, that's awesome.
I didn't.
here
We
go.
don't do anything. I didn't do anything. I do neutrinos entirely.
They have a superconductor at Texas A&M. It's like 2 hours from me.
Is that what you want to do? Or you want to do?
Oh no.
theory?
Definitely want to do theoretical, but I know they do have a superconductor.
It's a cool field of study. I really have a lot of theory friends that I usually pick their brain nonstop.
Yeah, hopefully when I become that, maybe you can pick my brain on stuff. I hope to be that cool.
Maybe.
How do I?
But you'll also get smarter, so.
Nah, come on.
Oh wait, I can do this. I can switch to
Smarter. We're sitting here talking
desktop,
about basic contour intervals.
and then I can put this.
I didn't remember anything.
I know like I don't even know the first thing about contour intervals other than what you guys have showed. So
When you do it, it'll probably be fairly simple for you.
All right. Oh, this sort of fits. Okay. So this was a cheat sheet I gave my students that relates all the relates the exponentials, the logarithms, and the hyperbolic trig functions and the trigonometric functions together. So when you're doing integrals and derivatives, some stuff starts to make sort of sense, right? Like, why is it that, the derivative of cosh is sinh? Well, because they're summations of exponential equations. Well, why is, the derivative of sine negative cosine, right? Oh, because they're also summations of exponential equations, right? Or these relationships, like what happens if you take a cosh and you put in an imaginary number? Oh, it turns into cosine, right? So cosine and cosh are the same, right? Yeah. Anyway, this is what I was thinking of. I thought I had a slightly different page, but this is the one I found. Oh, got to zoomed in.
If you're gonna do physics, memorize this.
I took a screenshot just now.
Understand it very well because we will not stop using it.
Yeah, well, I don't even know what the H is. Like I've seen that, but
which H?
It's
the cosh.
These are called hyperbolic trig functions. So the H stands for hyperbolic. So what you do is you add a little ch sound. So you go cosh. So rather than cosine, you go cosh. Or when you have sine, you do sinh, or tanch, or sech, right? And so that's the hyperbolic versions.
Hyperbole.
Sorry, I'm itching at my arms to talk about this, but these are really cool because these are all all this is a cone's intersection. So picture a cone's intersection with the x, your xy plane, and it's sort of that like projection on the xy plane, how it interacts with that plane. And if you were to rotate that cone, you can rotate it in such a way where, at one point it looks like a cosine function, and at some other point it looks like a cosh function, and it sort of changes. These are conic intersections. They're really cool.
What?
Yeah,
I'm learning right now, like two-sheet hyperboloids from Calculus 3. I'm learning the like the cone and how cones are like actually two cones in the 3D brain. And now you're telling me that they can be like That's
Yeah,
insane.
they're conic sections, so it depends on how your plane is sort of intersecting with a cone, and that's how you can connect these two things in a more complicated manner. I mean, there's an algebraic way to do it. That's
Well,
pretty
the-
simple, but it looks a lot cooler if you do it with a conic
Well,
section.
the circle, ellipse, parabola, hyperbola, those are conic sections, but those are not the trig functions, though, right?
Right, but if I can go between the trig functions like a cosh and a cosine via the conic sections, so you do this sort of like transformation.
You can do a
Right?
Via the conic sections, how?
Maybe.
Right, you're
I've
transforming
never
your
heard that.
cone, you're sort of remapping it.
You can remap
So-
the cone into trig functions?
Yeah. So you can go between it. Yeah, was how it. Because I thought that because if you were to take if you were to look at your conic sections, so you have your circle, ellipse, parabola, hyperbola.
Mm-hmm.
If I remember correctly, oh Jesus, this is pushing back. But if you go to your circle and your hyperbola, so your circle is your cosine, sine, tangent, etc. And your hyperbola is your cosh, secant, sinh, all that kind of stuff.
Oh, okay. You mean
right?
I got you.
So if you were to transform it into
you mean the coordinates because the x and y coordinates of a circle are like sine and cosine, and then the various geometric ways that you move off of a circle produce the other trigonometric functions. And you're saying, these other conic section objects, they turn into the hyperbolic trig functions, right? And
right, exactly.
I agree. Yeah.
So I mean, I'll just post a couple screenshots here of these things off the page.
Why are they described that way? Like hyperbolic? Like, what does that mean exactly?
Why are they called hyperbolic? Because it sounds cool. I'm not sure. Yeah.
Hyperbolic paraboloid. Yeah, that does sound cool.
So hyperbolic has been used as like a word to talk about extending something. In polynomial theory, hyperbolic means that a function has, or a polynomial has only real zeros. So a real zeroed polynomial is called hyperbolic. So that's like a graduate level term. Huh?
Real zero? What does that mean?
So a polynomial has zeros, meaning which are values that make a polynomial equal 0. So like x squared plus 1, there are numbers that make this 0. It's I and minus I, right? But like x squared minus 1, that has numbers that make it equal 0 as well. It's minus 1 and 1, right? And so this is a real.
Sure. Okay. Yeah.
This is a real zero function, or real zero polynomial, and this one has complex roots. We would say it has complex roots. Complex roots. This one is called a hyperbolic polynomial. But that's not a term you'll see anywhere unless you read Polya's special work on polynomial theory and something like that, or get
new buzzword learned.
Well, yeah. In other words, this is very much a specialized term used for polynomials for people that study roots of entire functions. So if you're in the graduate work of studying roots of entire functions and you're reading Levin's book, you might see the word hyperbolic, right, used for polynomials.
Okay, that's what I thought you meant, but I was just like making sure because there was a lot of new terms that were foreign to me, so I was like, okay.
Yeah.
Can I ask just to be sure?
They're always foreign to me. Don't become like us physicists. Listen to these mathematicians. You'll be happier.
You'll be happier.
You'll be able to. 'Cause we just make things up. It's like fuck it, it works.
Mathematicians make up words all the time. I make up words. I'm like, because you're doing a thing, and you're like, well, I did a thing that needs to do a thing that needs to do a thing. I'll call it the sinal addition coefficient, right? People are like, what does that mean? I don't know. It's the thing you do.
It's fine. We have a fart detector.
Fart detector.
The forward array, something or other, radial something, radial trigger system, something like that.
Oh, that's funny. Oh, that's amazing.
But no, we tend to use like a lot of the terms mathematicians use very sparingly. We'll just use them. Whatever, fuck it. It's fine. It's good enough.
That is hilarious when you're like, when would you ever not know the derivative? I'm like,
yeah,
that's a good point. I don't know. When would you not be able to simulate this on a computer? Like, obviously you know the derivative. This is so fucking obvious. Yeah. I
can
guess
read it right here. It's numerical. Even analytical, not knowing an analytical derivative still seems a little bit of a weird. Not knowing a derivative analytically seems a little bit of a weird concept. It's not something that you run into really ever. Maybe at the higher end, outside of what I do, but
you only run in well for a mathematician who does transform analysis all the time. That happens to me all the time. I have a fucking function. I only know it in terms of like I know it in terms of it's a solution to this particular differential equation, but I can't tell you what any of the coefficients are. I can't solve it. I can't solve for the coefficients of the differential equation itself. All I know is that it's a solution to it. So, like, is there other ways I can get access to the function, right? And there are there are formulas that allow me to try to fuck around with it and figure things out about it without me knowing all the properties about it, right?
Right, yeah. In our case, we would just say that the coefficient is this, right? Depending on what the function is.
Well, you'd simulate it. You'd approximate it, right? You'd just be like, well, I don't know. Let's see what the fuck happens when I plug in some points, right? And then you could see what it looks like, and then you're done, right?
Yeah, to an extent. I mean, it depends on the application. I mean, if you're doing some sort of numerical calculation, some sort of numerical method, some sort of computational method, then yeah, I could see your point. But if you're doing some sort of physical model, then not exactly, right? Going the other way, determining the coefficient would obviously be something that exists inside of your differential equation, and I don't know. Usually, don't start with.
My advisor told me one time he always thought that this was a joke, but he would always tell this as a funny story. He'd be like, one time the physics department asked me to solve an integral for them, and they sent it to me, and I stared at it for a really long time, and then I discovered it diverges, and I wrote them a beautiful proof, and they never emailed me back. And he was like, apparently that wasn't the answer they were looking for. I proved it doesn't exist. They were like, no.
I think I discussed it here before. I had my quantum mechanics professor in graduate school was a dual appointment. He was my quantum mechanics professor for Quantum 1 and Quantum 2, and he had a dual appointment in mathematics. We hated him for everything, like the worst thing ever. Oh no, you can't Taylor expand a operator. It's like, well, I can. I did it, and it works. It's like, no. You have to do 3 other steps in between it to do it. It's like, no, what are you talking about? It works right here. Look, I got the right answer.
That's funny. I had that. I did the same thing that a physicist did, so I had this differential formula, and I was like, oh, because there's like these two phases to discovery, right? There's the discovery part, and then there's like trying to prove that it's actually true, right? So like you figure out a thing, and I was like, oh my god, this pattern actually works, and it's this differential function you have to do, and I was like, yo, these are the same. And my advisor was like, well, how do you know they're the same? And I was like, well, we could just take the differential thing, we can expand it, it turns into these terms. And he's like, you don't know that like, you don't know that any of that convert, like, that isn't even like a convergent function. What are you doing? You know, and he had like a cringe moment. And I was like, well, I know I want to be rigorous, but like, we know it's true. You know, so, but
I think Zambo's got his hand up.
Zambo's got his hand
Okay.
up. Yeah, my bad. Yeah,
I've done that, and I get in trouble for it. Actually, I do more often than I should.
Yeah, I know.
They don't like it. They don't like it, which is good. That's part of the learning process.
The finding a proof wasn't really that hard. It was the discovery that the thing is true already. That's the important part. But yeah,
you get excited and you want to show it off, and then
I know,
bastards.
But the point is,
reminds me.
Yeah.
Oh,
but
sorry. Go ahead.
Well, what I'm saying is when you go to do research, you do bastardize the symbols like that because you're trying to figure out what's true. So you're like fuck it, you know, and you're like minusing derivatives from each other and like, well, what if I raise it to the 0th power? I don't know. Like, and so you're doing shit because you're like, I don't know, maybe that'll work, you know? Because if you end up getting a thing and you're like, oh, that looks interesting, then like the rigorous part, you know, is like, you know, you'll figure that out, right? Like once you know the formula is correct, then you just have to go figure out how to like show that it's correct. But not knowing the formula, that's such a pain in the ass, right? So
sure.
Yeah.
Of course, especially if your professors write their own problems and make it as hard as possible. But yeah. In addition, yeah. But anyway, yeah, sorry.
I was gonna say that one of these stories reminded me of when I was taking Real Analysis 2, and I sat next to one of my fraternity brothers who's double majoring in physics and math. Mm-hmm. And we'd be going through a problem and doing a proof, and the math professor would come around and he would like look at his work and be like, no, you can't make those assumptions. And he's like, but I can make them in physics. And he's like, no, not in this class. You know, and I'm like, it was very funny. I'd look at him and be like, get with the program, buddy. And it would annoy him because he's, you know, making these leaps and bounds and things and assumptions that you can make easily in physics. And it works. But in a math setting, it's like, no, you gotta go through the process. You gotta grind it out.
Yeah.
Yep. I hate it.
I guess it's gonna be something I'm gonna have to deal with.
Stumbling upon an idea that seems original and then looking it up and then later finding out, oh, it's been done before. It's happened to me a few times.
Yeah.
It's very annoying.
That happens a lot.
Yep.
You kind of like Zombo. You kind of sound like just a little bit. You sound like Jeff Bezos.
He's Jeff Bezos.
Yeah, that makes sense.
No, Jeff.
You ever heard Jeff Bezos speak?
I like a little bit. I think I can see the comparison. That's pretty funny. Although I look exactly like John Belushi, so that's a little jarring.
Yeah, I don't hear it.
That's funny.
No. Okay, maybe it's the clip I saw, but there's a clip of Bezos talking about him wanting to be a theoretical physicist, and I don't know.
Really?
There's a lot of resemblance. Well, he was at Princeton, and that's what he was doing, theoretical physics, and then
Really?
Yeah.
I didn't know it.
Wow.
And in that clip, well, it's the entire story is funny. He's like, yeah, I was doing this partial differential equation, and me and my roommate were like stuck on it for like 2 days, and then he goes to his friend, and who was like from Bangladesh or something, and he shows him the problem they'd been working on, and the friend solved it in like 2 minutes because he had seen something.
I've seen this story.
Oh.
Yeah. And
That's
then Jeff Bezos like, yeah, theoretical physics isn't for me. he drops out and starts Amazon.
That's how I knew I didn't want to do theoretical physics after I took quantum mechanics in graduate school. I said, "Yep."
I have at least 2 different times in my life, been cornered by people who I would consider physics professor and a high school AP physics teacher who is basically a professor, and they both cornered me, and they're like, "Why aren't you in my next physics class?" And both times I'm like, "I'm studying math." Sorry to disappoint.
It's okay. You're afraid of the real world. It's fine.
Maybe I should have gone into physics. Probably not, though. Probably not. I love math and everything about it. What Bobby does actually interests me greatly. I like transforms and polynomials and analysis and that kind of deal.
Yeah.
I could not do I could not do group theory or representation theory or anything like that.
Well,
I walked into
how related the two topics are.
Yeah. Screw all that stuff. Yeah. Analysis.
I walked into a professor's office hours one day, and he had these like intersecting scribbles that look exactly like alien language from a movie, and I'm just like, what?
Feynman diagrams?
No, not even Feynman diagrams. This is like a new type of scribbles. And each intersection of the line was like represented some kind of operation and all this other stuff. And
sounds like a Feynman
I'm like, what does this even mean? And he's like, well, this is what this means and this means. And I'm like, okay, so what do you use it for? And he's like, I think physicists are using it to store data in quantum computers, but I have no idea. Not at all. And it was just super wild. I met some great professors who specifically study representation theory, and I could not sink my teeth into that field. That's wild stuff.
Representation theory is kind of stupid. I mean, I hate it because it's really dumb. Because in physics, effectively, when you're applying representation theory, it's more so like it just works. Why? What's the actual reason why we're using it? I don't know. We haven't measured it otherwise. so there you go.
It's like, well, this problem boiled down to linear algebra, so here we go.
I hate it. I've asked some very, very good theoretical physicists about it, and they're just like, I don't know, dude. It just works. It's like
that's
so far we haven't found a case where it doesn't. So therefore, it's true. It's like, oh well, thank you.
Oh man.
Use it for, and physicists are like, well, it works. I know what to use it for.
All right, I gotta go to bed, but it's been fun.
Night, Bobby.
So I'll probably be on Saturday. I'll have to schedule some more lives and things. I know. I'm sorry. I do have to put in work hours, or they'll get mad at me at some point.
Employments.
Anyway, thanks everyone.
Night, Bobby.
Good night.